Can you? Yeah, it works. Okay, so I would like to welcome everyone to the RTC.On Conference, the first edition. Hopefully not the last. I would like to thank everyone that came into Krakow to visit us. We still have some people still not registered, so we're delaying it a few minutes if there is maybe like the last tram arriving, but yeah, we would like to start with Łukasz Wala, who will be talking about Jellyfish and the history about what we've been trying to build in Software Mansion for the last year or so. After the first 4 talks, there will be a coffee break. But if you want, there is also coffee and drinks outside. You can just go out there. Yeah, I will just leave this to Łukasz. So, thank you.
Hello everyone. Like just Marcin said, I'm going to give you a little overview of Jellyfish, which is a multimedia server that we've been working on at Software Mansion for the past few months, which is built in Elixir, powered by Membrane and Phoenix, like the slide said. And before that, my name is Łukasz Wala. While I work here at Krakow at Software Mansion, mostly on multimedia and WebRTC stuff. You can find me on GitHub and on Twitter. So, what is this talk going to be about? I'm going to give you a little introduction to the concept of media server and protocols involved in networking and multimedia stuff, because I know some of you might be not familiar with this stuff. Then we're going to do a basic overview. I'm going to tell you about the basic concept of Jellyfish. Then we're going to do a brief look under the hood of Jellyfish. There's going to be a little demo at the end. Let me get this mic on. 1, 2, does it work?
Sorry for that.
All right. All right, so let's get going. What is a media server? So basically, as we understand it, media server is simply a piece of software that you run on your backend that takes some incoming media, obviously. Sometimes does something with it, but not necessarily, and then sends it somewhere else. It's as simple as it gets. If you've ever worked with WebRTC, you might have heard the abbreviation SFU, which stands for Selective Forwarding Unit. And the name is quite self-explanatory. It selectively forwards some media traffic. And this is exactly what Jellyfish is. And you might be asking, well, similar solutions already exist in the market, so why are you building this thing? And before I answer this question, let me give you a little introduction to some of the most common protocols and standards used in media networking. And the first one is WebRTC, which is a standard developed in the last decade, and it's basically used in all of the big video conferencing solutions like Google Meet, Microsoft Teams, WebEx, Zoom, etc. It was designed as a peer-to-peer standard to peer-to-peer communication, but nowadays it's also used with some servers and central units that forwards the media, like the SFU I mentioned before. And it's based on RTP. It has a very low latency. And usually, when you use WebRTC, there's communication, and there's two-way communication. So you receive and send media. For instance, in a video conferencing solution, the participant in the meeting could send and receive media. And on the other side of the spectrum, there's HLS, which is a broadcasting protocol. So it is used, for instance, in video-on-demand solutions and live streaming. For instance, Twitch uses HLS. It is based on HTTP. It basically works as follows. You have your video in format that is similar to something like MP4, then it is sliced into segments and simply served with HTTP. Because of that, the latency is quite a bit bigger than in case of WebRTC, and it used, like I said, it's used mostly in live streaming and video on demand. And the last protocol that I want to mention is the RTSP, which is, I think, not as interesting as the other two, but nowadays it's mostly used by IP cameras to basically send the stream. If you ever looked at an IP camera feed in your browser, for instance, from some city, there's one on the Krakow Old Town. It's probably uses RTSP. And I'm talking about these three because these are exactly the protocols that Jellyfish supports. So when usually solutions in the market, other media servers focus on one thing, like the WebRTC. We wanted to create a very extensible solution that can bridge different types of standards and protocols. I'm going to show how we can achieve it in just a moment. But for instance, with Jellyfish, you could create a video conferencing solution when you also compose all of the streams into one and then serve it via the HLS. So, but before the examples, I need to explain the basic concepts of Jellyfish. And these are rooms, peers, and components. And rooms, which is quite telling, these are basic containers for other types of elements. So when you are talking about a video conferencing solution, room would usually mean something like a meeting. Then you can use the rooms to group peers and components. And peers and components, there's a crucial difference between these two types, and I'm going to mention it in a moment. But now let's see an example. The only type of peer that we currently support is the WebRTC peer. Going back to the web video conferencing solution, WebRTC peer would represent like a participant in the meeting. So the usual flow of using WebRTC peer with Jellyfish would be something like this. You have your video conferencing app, and there's the client, your app's front end, and your app's backend. Client joins, so participant wants to join the meeting. He will send some kind of request to your backend, and then backend can take care of calling the Jellyfish API to add the WebRTC peer. Jellyfish will usually respond with confirmation with the peer token that you can see on the third arrow on this slide. Then your app's backend can have to somehow pass the token to the client, and client can open a signaling channel, which is under the number 5 on the slide. The signaling is necessary for WebRTC to establish the connection because there needs to be exchange of some metadata that is necessary to then start sending the media. And like I said, the WebRTC peer would usually mean, for instance, maybe a participant in a meeting in your video conferencing solution. On the other hand, we have the components. And there's two types of components at the moment. There's the RTSP component, which you can use to receive the RTSP stream. So let's say there's some IP camera that uses RTSP to transmit its feed. You can add the RTSP component to Jellyfish using its API. And then you simply have access to the feed from the camera, and it can be then forwarded to other types of peers and components. There's the second type, which is HLS component, and it's exactly opposite of RTSP. RTSP only produces media and streams. On the other hand, HLS consumes all of the media, all of the streams from other WebRTC components and RTSP components, and composes them into one single stream. And how the composition works, I'll talk about that in a minute. And then Jellyfish takes care of serving the HLS stream via HTTP. All right, so here's the most basic example that shows how you can combine different types of Pearson components. Here we have the usual video conferencing solution. You have your participants, you have your meeting. You add each of the participants as a WebRTC peer. So then each of the WebRTC peer can see every one of the other peers, as usual in the traditional video conferencing solution. But then you can add the HLS component, which will take all the streams from WebRTC peers, compose them into one single stream, mix the audio, and serve it via HTTP. All right. Here's the second example, which is RTSP to HLS. It's very similar, but instead of using the WebRTC peers, we use the RTSP components. So let's say you have a network of surveillance cameras, and you want to show the feed from the cameras in your browser, or maybe access it on your phone. You can create a Jellyfish instance with a single room and add all of the cameras as RTSP components to Jellyfish. Next, you can add the HLS component, which will, just like before, mix all of the audio and compose all of the video into one stream and serve it via HTTP. All right, so this was the basic examples of how Jellyfish can be used. But now let's take a brief look under the hood and how does it work. Like I said, Membrane is based on Jellyfish is based on Membrane, which is the framework we have built at Software Mention that you can use to create multimedia pipelines. So basically, this is a screenshot from a tool that we use to visualize these pipelines. The blue rectangles are the Membrane elements, which basically are, simplifying a bit, basically these are processes or threads that consume some kind of data. It doesn't have to be media, but obviously in this case it is, and then produce some kind of data. All of the blue rectangles on the screenshot are the T components, which simply multiplex the data. So they take one input and produce multiple inputs with exactly the same stuff as in the input. The green rectangles are Membrane bins, which are basically containers for other elements. I'm going to show you how you can expand this green rectangle to see what's inside on the next slide. But basically, this is a screenshot from a single room in Jellyfish. And there's all the different types of Pearson components that I mentioned before. This is the RTSP component. So like I said, it only produces. So it takes a stream from some kind of IP camera, let's say. And then the stream is forwarded to all of the other types of components. In this case, these are the WebRTC peers and HLS component. This is the HLS component, which consumes the stream from all of the other types of elements. So it takes the stream from WebRTC peers and RTSP components and creates a single HLS stream, which is then served via HTTP by the API layer of Jellyfish. And the last one, this is the WebRTC peer, which can consume data from other types of Pearson components and also produce media. For instance, your participant in your video conferencing meeting will usually produce some kind of audio, for instance, from his microphone and maybe a camera feed or some screen sharing. And all of this is forwarded to other WebRTC peers in Jellyfish room and the HLS component. This is how the HLS pipelines look. This is the expanded green rectangle from the previous example. In this case, it's very simple because it takes only one video and one audio stream, so the composing and mixing part doesn't really do anything in this case. And as you can see, it really is a pipeline. So there's different elements, and they do different stuff, which I can show you here. And this is basically how it works with other types of Pearson components. So WebRTC and RTSP uses RTP, which is a protocol based on UDP. But to use it in HLS, we have to somehow take the payload out of the RTP packets. we can use the RTP dpayloader membrane elements. All of the rectangles on this example are basically membrane elements. After the media is depayloaded, so we can get to decoding. In case of WebRTC and RTSP, we have different types of encoding that we can use. In case of video, it might be VP8 in WebRTC, or maybe H.264 in case of RTSP. These are simply different types of video codecs. And in this example, I used AAC, which is an audio codec for both WebRTC and RTSP. Then all of the media from video, all of the video goes into the VideoCompositor, which is an element that mixes, or rather composes, all of the videos onto one single frame. And I'm going to show you in practice in the demo at the end. And all of the audio goes to the audio mixer, which simply mixes all of the audio streams. Then the video and audio is once again encoded, and the CMAF, which is a type of container used by HLS, which is basically the sliced up segmented MP4, takes care of payloading it, and then the API layer of Jellyfish serves it via HTTP. So that was the multimedia part of things, but I guess the API is as important. We use REST, a simple HTTP REST to enable adding and removing the different types of elements, so rooms, peers, and components. And usually your app's backend would take all of this. And also we allow to receive some kind of notifications from the Jellyfish. So for instance, Jellyfish can produce notifications about room crashing, or maybe that the peer has just connected. And you can use the WebSocket API to simply receive the notifications. There's also the API for the client, which in this case is mostly used by WebRTC for the signaling channel and the metadata exchange. You can see it on the number 5. And obviously doing all the requests and HTTP and WebSocket stuff by hand would be quite tedious, so we've created some SDKs. In case of the backend, so the SDK for creating rooms, receiving notifications, we have SDKs in Elixir and Python for that. And there's also the client SDKs in TypeScript, React for mobile stuff, iOS, Android, and React Native, I believe. All right, so before I get to the demo, I also need to mention the dashboard, which is a tool that we've built to make it easier to develop the application. It basically can do everything that the SDKs can do, but it's nice web app format, so it's easy to debug when developing stuff on Jellyfish. And the last thing I want to mention is the load balancing. We wanted to make Jellyfish very easily horizontally scalable. So the basic load balancing is the first step in this direction. You can create clusters of Jellyfish instances, and then when you want to create a room on a single instance, this instance will ask all of the other instances for some feedback with resource usage, and then decide which instance is the most suitable to create the actual room. It's usually the least used one. All right, so I have this little demo. Maybe let's start with that. For internal meetings and membrane teams, we use this app that we developed. It's obviously based on Jellyfish. Let me run it real quick. I have to host it locally for this example. So this is the app that we use for our internal meetings. And basically, simple video conferencing app. And I want to show you an example of manually adding the HLS endpoint. So we can stream the meeting by using the HLS. So here I have the meeting. You can see it works just fine. I'm sorry, I have to, let me just join to the same room maybe. Okay, so I'm joining from the demo. I do the same thing here. Right, so this is a simple video conferencing app. But now we can use the API, which I have here on the presentation, to manually add the HLS endpoint to the instance of Jellyfish. So what we're going to do is to install the Jellyfish Server SDK, which is necessary to do all of the requests. Then we're going to create a client struct, which is basically a struct aggregating all of the information necessary to create the requests. We know that there's only one room on this Jellyfish instance, so we can use the getAll call to somehow obtain the ID of the room, and then we use the addComponent function to add the HLS component. So I'm going to do exactly that here. As you can see, this is exactly the script that I was talking about. And I'm going to call it with Elixir. As you can see, there's this URL printed. Let me copy it real quick. And we can use some demo HLS player for, in this case, this is the HLS.js example to play the stream. As you can see, this is exactly all of the composed streams from the meeting. So in this case, it's just me. But usually when you have maybe multiple tracks, it will dynamically compose all of the videos onto a grid. And that was basically it. So this is Jellyfish. I hope you now get the basic components and know how to create basic solutions in multimedia apps with Jellyfish. Thank you.
Thank you, Łukasz. Are there any questions? There is another mic somewhere there on the back, if anyone wants to ask any questions. Yeah, okay, so.
I can speak loudly. Where's the name Jellyfish from?
Maybe you've seen the membrane logo. So Jellyfish was supposed to be initial name of the project that we're supposed to rebrand it further on, but it's basically stuck on, so it's probably going to be Jellyfish forever now.
Yeah, okay. John?
Hey, great talk, thanks. Very impressive software. I have one question about the horizontal scaling thing. So once the rooms are made, they're pinned to the instance and they don't move, even if they're like modified. If you will add more components, it will not reevaluate the resource usage and then move it maybe? This one works? No.
Yeah. 1, 2, 1, 2. So at the moment, this is the only thing that we support. We're working on doing rooms that can span multiple Jellyfish instances, but that's still in progress. So basically now it's only the ask other instances for the resource usage, and then choose the least used one and create the room there. But we've planned to do some more features regarding the scaling.
Thank you.
I just wanted to follow up on that. So how do you do discovery for all the Jellyfish servers? And are they connected in a full-blown mesh where each Jellyfish server is connected to every other?
Yes, because this is all built in Elixir. We use the Erlang distribution. You have to create the clusters manually, so you have to, when creating Jellyfish instances, you have to pass the addresses of all the other instances, and this is basically the full mesh. So the instance that is receiving the call to create a room will basically ask all the other instances for the resource usage at the moment.
Thank you.
Okay, so I saw on the diagram that you use protobuf for signaling. There's an option to use a different type of data, as it's really tricky to use it on the front-end side.
At the moment, no, but we plan to also add the support for webhooks to make it easier to use with some cloud services. So now basically you have to use the protobus.
Anyone else with the questions?
Any other questions? All right, Thank you for listening.
Okay, so thank you, Łukasz. Okay. Saúl, right?
Plug and play.
Oh, he's coming outside. Yeah. So Saúl, Ibarra, Corretgé. How do I read this?
I'll show you now.
Yeah, we'll be talking about his and probably not only his experiences with connecting WebRTC with React Native in Jitsi. So, Saúl, you have the mic? Yeah? Okay.
I do,
So,
I think.
yeah?
Test 1, 2. Yeah?
Okay, so, yeah, leaving the stage.
All righty. Thank you very much. Well, welcome everybody. Good morning. Today, I'd like to talk about WebRTC on mobile and our little journey using React Native and some unconventional things we did. So as he said, my name is Saúl. I work for 8x8 on Jitsi and other ancillary projects like React Native, WebRTC. Hopefully, I show you something you didn't know today. A quick Jitsi primer for any of you that might not be familiar with it. It's a set of open source projects. It's basically a turnkey WebRTC platform. In a way, you kind of saw it now with Jellyfish, but Jitsi has everything built in so you can use it. You can also take the lower level components and build something on top, but in general, it is something you can just take it as is and run it. Runs on the web, on mobile, pretty much everywhere. You can host it yourself. We make it easy to self-host. We have a hosted service that helps sustain the project. And if you've seen a screenshot here and there, you like them, this is sort of how it looks like when the marketing people give you a cool screenshot. So how does it look like sort of on the inside? Last I kind of checked, our, in a way, architecture on the client side look a little bit like this. So we've got our standard WebRTC APIs at the bottom. We use XMPP for signaling because when all you have is a hammer, everything looks like a nail. And we've got our signaling layer. We call it a low-level library, but if you compare it with other APIs from different vendors, it's actually higher level, called libjitsi-meet. We do all sorts of signaling, handling, stream management, simulcast, handling on the layer suspension and switching. So it's a pretty comprehensive library. It's reasonably beefy, and it is written in JavaScript. And then our front end bolts on top of that, Jitsi-meet, and it's a little bit bigger than the other thing. Why is this sort of relevant to you at this point? Because when we made the decision of going mobile back in 2016, that's roughly where we started. So we had all of that built, that separation was done. However, Jitsi-meet is, it's been in some battles, and it was built with jQuery and other things. We had to migrate to React. That was sort of the guidelines. Let's begin by migrating to React. Then we're going to use React Native for mobile, and we are going to leverage all of that code that we had already written, all the business logic, your middlewares, your reducers, everything would be shared, except we would branch out when it comes to rendering. So we would use React Native components. On mobile, we would use the DOM on the web, and everybody would be sort of happy. That was the plan. This effort started in 2016, and the first public release on the sort of stores, Play Store, Apple Store, was on the first of, somewhere in March 2017. We started out with React Native 0.27. Any React Native people in the house? A few. So if you've been around, that was a while ago. And important as well is that in this journey, there has never been what in a way you would call a real mobile developer around. I'm as close as you can get to one, I guess. In our team, I've been working on this side for the most part. However, I wouldn't consider myself a mobile developer insofar as I've never shipped a native mobile app. However, I've worked on this thing and all of its teeny tiny inner goings for a really long time. Now, if you want to build a mobile app with React Native, and you need WebRTC compatibility, we needed to go on a little side quest of, yes, there was a React Native WebRTC library, but no, it was not in a shape that we could consume it directly. So we started contributing to the project. Eventually, we became the maintainers of it. Then we tried to build a little community around it. So now we've got the React Native WebRTC GitHub org with a number of plugins that add functionality. And in general, if you want to build a WebRTC capable application with React Native, this should probably be the plugin that you want to use. I gave a presentation at Dance Conference ComCom earlier this year. You're welcome to check out that talk. It goes deeper into how we build React Native WebRTC. Today, we're going to use it and build on top of it and see how our mobile app turned out. So, beautiful diagram here. When we designed our SDK, we modeled it after the SDK we have for web. And it's also somewhat unconventional, even though we've seen more people in the industry take the same approach. Our approach is to be like full-frame SDKs as a high-level option. So all that green stuff, that's what you get, the full view. That's your SDK. On the web, we do that with an iframe. And we have an API to control everything inside, and you can change things in the UI and layout. However, what you get out of the box is this thing you can plug into your existing app, and it now has like certain meeting capability. Why do we do this? So in general, what our experience has shown is that when people want to add a certain meeting capability to their applications, what they care the most about is their own business, their own whatever it is that they really do. Imagine this is some kind of telehealth organization. Imagine this is, some lawyers, some psychologists. What they care is their practice, their customers. The meeting is just a means to an end. So they don't want to spend, I don't know how many man-hours in building a meetings application. They want to focus on their thing. So that's why we give them this frame you can plug in, customize, make it sort of branded so it matches your app, and then you can focus on, growing your business and the other things that are more important to you. And I hear the younger generation call this low code or something like that, but kind of this is where we started because we had all the background in doing exactly the same thing successfully on the web side of the things. We still have like Live Jitsi Meet for those who want to go in the lower level and build their own user interface. But in general, what we've seen in running this as a service is that customers will prefer the full frame option in general. So our first target was to build a native iOS and Android SDKs because we used to be part of Atlassian, now 8x8 for a few years now, and the corporate mobile apps were native, and they wanted to integrate with us that way. Now remember, we had built a React Native app, so we needed to take that into an SDK. So, kind of inspired in a way by, for instance, the Google Maps and the YouTube SDKs, which have a similar full frame style or partial frame API, that's what we set out to build. In iOS, it's actually relatively straightforward. In general, you would have one target for your application, which is everything. Now we would add another target, which is our SDK, a framework target, and we would put all the React Native bits in there. Then our app would depend on the SDK, and that's kind of it. Our UI view, that's the Jitsi Meet view, would be the API that we give you. You could build a simple controller around it and then present it when you want, and that would be it. Then there is a singleton for wiring up with, for instance, everything your activity delegate, like, when a URL was being opened because you're navigating through a calendar link or something like that, deep linking. In order to integrate easily, we added a little wrapper so that you could plug it in your app delegate. You don't really need to focus on the code that I'm going to show, just listen to me. This is just the concepts that we needed to do to sort of get there. So I said, first, we want to take all the logic related to integrating React Native and put it into our framework target. an interesting thing we have done later is that we have a lightweight SDK, that removes some of the fat-ass dependencies we have. And that's why we need to get a bit creative there with some manual linking. But in general, just putting all the things React Native related into your framework target would suffice. This is part of our Jitsi Meet view. And in general, the way it would work is you have your React Native bridge that takes care of all the communication between the views and the React Native engine, if you will. And you have a root view that's the only sub-view of our Jitsi Meet view. So all you get is one view fully covered with the React Native stuff. This is a sample of like the type of things you would want to do in the singleton. We would have like a reference to the bridge that controls the React Native engine. And this would be, for instance, the delegate method for handling, when you open a URL, what do you want to do with it? Since we have like Dropbox integration, might be a Dropbox link. Then we try, is it the Google sign-in link? No. Is it the link for our SDK then? We handle it. So this is how we, with a little bit of this code, how we sort of took the React Native part and turned it into a native SDK that was using, anecdotally, React Native on the inside. The result on iOS is that the SDK is sort of hidden because the resulting framework is actually statically linked and everything is inside, and we only depend on two other frameworks that we link with, one of them being WebRTC, for example, because it doesn't support static linking. So it's a pretty self-contained thing you can just consume. Now let's look at my least favorite platform, Android. Of course, a lot more complex because it wouldn't be Android otherwise. So you begin by, okay, we have an application, so now we need to build a library target. Now, at the time, I know things have changed a little, but remember, we started with React Native 0.27. There was this Gradle config that was targeting apps, so it wouldn't work it was targeting applications, not libraries. So we had to get a bit creative, and we have to do manual linking, at least for now, which is, we don't change dependencies so often, but it is something. And all this logic to glue up all the React stuff, like bundling the JavaScript and moving things around into your SDK, like all the sounds and assets, was handled by a React Gradle plugin that did not work at all for libraries. It was only focused on apps. You can actually tell by looking at the Android code that they really didn't have this use case in mind, but that has never stopped us, has it? So we went for it. Then obviously, all your Java dependencies, they need to be somewhere. And because of, how Android works, you will end up having a lot of libraries you depend on, and you need to also ship them. So we basically republish or publish all those libraries with like custom, like -Jitsi and a version number, so we can have the whole chain of dependencies on our Maven repo, and you don't need to worry about having them hosted elsewhere and problems like so. The Android Gradle plugin has also been a pain in the rear. Often, like every time we had to update it, we needed to manually go and change how on earth all these merged assets in the APK end up so that the SDK wouldn't miss like the sound files or the picture files or the JavaScript bundle. So it was a fun sort of road. This is how your library target would look like, as I said, because we have manual linking and we want to skip out some dependencies. You end up with a maze of them, in our case. This is a little bit of how our shenanigans for managing all the dependencies and adding them to our SDK with a custom version number so that we can have the full chain of dependencies that we have controlled. And every SDK has all the dependencies that we depend on republished in the same Maven repo with a version that we control. This is the part that we do here. We also need to publish them, and this is kind of how we handle that. But there is more. Android is always interesting. There's some troublesome, and again, going back to how React Native really catered for apps, there is this React application that your app needs to implement. An SDK cannot ask an Android app, please, can you modify your application implementation to inherit from React application, please and thank you. Not going to happen. And that is a problem with certain dependencies. And maybe some of you are familiar with React Native Reanimated, built by the great folks here at Software Mention. Thankfully, this was fixed at one point in time, but I remember people like us in the community that were building brownfield apps running into this problem where your application does not inherit from React application. So finding specifically the React Native Instance Manager was interesting. Also on Android, just a view is not enough because you need to wire it to like the activity. You need a lot of lifecycle hooks to, for instance, get the permissions and stuff, handle linking. So we ended up settling on a high-level API, which is an activity, and a lower-level API, which is a view, in case you want to do the wiring, plus some auxiliary classes so that you can glue the two together. The way it looks like a little bit is, so first of all, we have our little thing to hold on to the React Native Instance Manager because we don't have React application. We then have our Jitsi meet activity, which gets like a very simple static launch method, gets a lot of options, and it launches, does its thing. The idea with this API is you're in your app doing, I don't know what, launch a meeting, Jitsi takes over, finish your meeting, Jitsi goes away. And if you want to go a bit the lower level, this would be our view, which is just a simple frame layout. And as you can see right here, we basically have a single subview, which is the React Native root view. In that regard, it's very similar to iOS. So the result is that it's virtually the same as in iOS, but because of how Android dependencies work, everything is like a flat kind of dependency tree in the end. The use of React Native is not hidden in a way, so there is a chance for collisions to some extent. It's rare, but it can happen, and I have heard from some people that, for instance, they want to use our SDK for meetings and some other SDK that uses WebRTC for like calling. And that means that you need to sort of agree on what version of WebRTC you're using under the hood, or it's going to be a little problem. So at this point, you know, achievement unlocked. We got native mobile SDKs. The teams that were using them have been doing so since 2017, somewhere mid-2017. Since I'm here, I'd like to take a chance to thank the good folks here at Software Mention for building some cool libraries that I've been using for many years now, like the gesture handler, SVG, and the screens since we introduced navigation. So we wouldn't have done it without you. It's been really great to use. Thank you. Now, things moved since, and a new player entered the game, this Flutter thing, with a weird programming language to go with. And the community had already created some Flutter packages, but, you know, they eventually became unmaintained, and we got, like, you know, customers and users in our community wanted to use Flutter for some reason, so we ended up making our own. And we built our own Flutter plugin by wrapping our native SDKs. So at this point, you can see this is kind of an onion kind of situation. We got the Flutter layer, the native layer, hiding the React Native layer. Works beautifully. And if anybody familiar with Flutter in the house? Not me, so I won't lie. All right. So in Flutter, this is how our API looks like, by the way. It's kind of imperative. So when you say, hey, you know, like join a meeting, like a new view controller or a new activity takes over, does its thing, and then it's dismissed. Flutter has this idea of platform views. So you can do like a component that you could put in the middle of the screen, but that doesn't work very well for Android because it needs to latch itself to the activity lifecycle stuff. So we decided that for now, we're not going to do platform views and kind of wait and see. Since Flutter is not our mother tongue, we're waiting to see if, how much interest there is and if we want to venture there. But then, of course, we got to circle back. So people were interested in consuming our SDK directly in another React Native app instead of a native or Flutter app. So, okay, let's go ahead and export our component the whole thing as a component you can consume. How hard can it be, right? Well, the problem is that when you have like 100+ dependencies, like your SDK is fat as fuck. So it was rough handling the building side of things and all the dependencies. I'm not sure anybody here has had the trouble of dealing with like peer dependencies plus automatic linking. It does not work. So we needed to be a bit creative and add a post-install script that would, tell you what to do. Otherwise, you wouldn't be able to get linking working. And we were lucky enough to get help from Philip Raimus, a Google Summer of Code student last year. And we got almost all the way to the finish line. And then with a little bit of elbow grease, we got there. And now, you have a Jitsi meeting component, pass in some flags, some options, and, Bob's your uncle. So you get what you would expect, which is a component you can put anywhere. This is not a whole thing that takes over. You could put it anywhere in your view hierarchy. But it was a lot more complex than we thought, going sort of back to where we started with just with React Native. So I said we've been building these ones for a while. So you can actually go and check the source code or consume them right now. We publish the Android builds in our own Maven repo, iOS in CocoaPods, which is kind of where people expect it. Flutter has its own marketplace thingamajig. And React Native, of course, NPM. You can find source code for all of these things in our Jitsi org. And there's more information about all the SDKs we have, also for web stuff like Electron and Pure React and the iframe, everything in our SDKs category in the handbook. And honestly, as I was writing this talk, I was thinking, I'm not sure if there is any other way that we could have approached this problem and kind of get where we got supporting all these platforms in a simpler way. Maybe it's me rationalizing what we already did, but so I thought, talk a bit about maintenance. The team of people that work mainly on mobile is 2, if you sort of round it up. And that's not a lot, which means we try to optimize for all these sharing so that people that are not necessarily working on mobile can also contribute to this. We encourage every engineer in the team to work also on the mobile side of things. And then there's people like me that with time have, had to pop open the hood and look what's in it to do the gluing bits with system APIs and whatnot. But in general, people can contribute at the higher layers. So because we're a small team, we try to automate as much as we can of all this SDK releasing process because we don't want to be busy making fat releases. We just want to push a button and things will happen. So between Jenkins and GitHub Actions, we have automated releasing all of these things. And so far, it has gone pretty well. We don't feel like really adding more platforms is a burden, but we're mindful about this. So we are trying to only tackle and only maintain things we can afford. Time-wise. But for instance, Flutter doesn't really add a lot of maintenance cost because the API we offer is a full frame, so then it's a bit of glue code in Kotlin and Swift, and that's kind of where it's at. So the ever interesting question, so what framework do I use for my next mobile app? I hear pure native, React Native, Flutter. What do we do? Well, I'm not going to tell you. So I have more questions for anyone asking this. So I think that it widely depends on where you are and where you need to be. Do you already have a fully blown web application written in something you can share with on mobile? Because if your app is written in Vue.js, I don't know how the Vue.js ecosystem looks like on mobile. Can you bridge that gap easily? Do you have access to a lot of plugins and system libraries? Specifically, if we're talking an RTC-related product, do you have a mature WebRTC plugin? These are the kind of questions you will need to ask yourself. What team do you have to build this? Do you have mobile specialists? Then maybe you got to go full native. If you don't, and you want to be able to, basically everybody is a janitor. You just work on whatever you need to work on. Then maybe you can use something which is a bit more abstracted from the system, but then someone will eventually go deep and nail it down. And is sharing the code important to you? It might not sound super important in the beginning, but as I showed early in the presentation, like all the signaling, media handling, simulcasting, dealing with statistics so you can measure quality and everything, like that's a lot of code. And ideally, you don't want to write that multiple times. And if you have written it in something you can share across all the platforms, it might be interesting. And I think it was Jeff Atwood that said that, you know, if something can be written in JavaScript, it will. So if you already have it in JavaScript, maybe the React Native way and this crazy way to do things is something you can leverage. That's all I had for you today. That's where you can find me. And if you have some questions, I believe we have a little bit of time.
Thank you, Saúl. Any questions? Oh yeah, one. Paulina?
Second.
Hey, Saúl, thank you for the talk. At a high level, can you talk about, you know, what were the reasons originally to build the mobile app as opposed to using WebView or as opposed to using just the browser app on mobile? And then are there also limitations once you wanted to embed it into an existing native app?
That is a great question. I should have covered that for the next time. So why not use a browser? So the reality is that even though browsers have grown a lot on mobile, and much to our own reluctance, we have finally enabled, like a few years ago, that you can actually use Jitsi on the mobile browser already. So, but it's not ideal. So you're lacking critical platform integration features. You don't have deep linking, so you can't just pick a link and go straight to a given part of your app. You don't have, for example, in iOS, you don't have CallKit integration. So integrating with a system calling mechanism is something pretty important if you're doing a calling app. That's also virtually the only way to keep your app alive if you're doing a calling thing. When you go into the background, browsers will stop timers and your web app will start to be frozen. So some audio will keep going, and then eventually fade out. In fact, one of our customers for Jazz is the Brave browser. And they have an integration. They have Brave Talk as their product that uses Jitsi. And on the iOS application, they used to just run it in the browser. And since a few versions, they integrated the SDK. So whenever you go to Brave Talk, you actually open the SDK on top of the browser and do this dance that we've talked about with show the view, then vanish the view. And that has resolved all the problems they had with audio issues and what have you. Device management is a lot easier. Well, not easier, but you have a lot more control over when you are on a native app, really. For example, on Android, on Android 12, Bluetooth devices don't show up in media devices.enumerate devices. Why? Because. So we have our own little audio device management module. We decide what type, you cannot decide on any browser API what type of audio you're playing. Is this calling audio? Is this like, you know, a music thing? So they tune the microphones differently. You don't have control over any of this. You don't have proximity APIs. So if you take your phone to your ear, the screen will not dim, so you will be pressing shit with your ear. You don't have control over any of this. And one more important thing you don't have control over is WebRTC itself. When you ship an app, you know exactly what version ships, what codecs it ships with, and what bugs and features it has. If you're using the browser, you're at the mercy of whatever Chrome or Apple, well, Google or Apple do, and you know sometimes they mess it up. And you don't have the flexibility to do anything about it. So that's why we went native.
Cool, thank you.
Cheers. All right. I'll be around if you have more questions later in the day. Thanks, everybody.
Thank you. So, Our next speaker, Pickering, will tell us a bit about transcription of audio, I assume, in WebRTC based apps. So, yeah.
Always. You know what? Let's just do it this way. Who wanted to start the presentation at the start anyway? That's always a bad idea. I'm going to, just by way of introduction, tell a kind of an interesting story, which may embarrass Marcin, but he's gone now, so that's no good at all. I'm a greybeard software developer, packet mover kind of guy, and about 5 years ago, I was running a voice-over IP company. So I come from voice-over IP industry, which you'll kind of get. And CEO of the company, I'm tearing my hair out at midnight because one of our customers said, 3 weeks, I need this new dashboard. We're building a new call center. If you guys can't deliver it, I'm going to go somewhere else and use someone else's solution. So I'm tearing my hair out and looking around. I found this company called Software Mansion, who seemed to have really quite a good reputation in this space. So I pinged an email out. I found a few others as well, sent them all emails saying, look, I've got this problem. How do you fancy building me a React dashboard? It's got to be done in 2 sprints. We'll do all the state management, so we'll give you a bunch of state, and you just do a front end. Reason for that is all my software developers were committed, and the only software developer left to develop this thing was kind of me, and I'm not a front end guy. Marcin was the only person who was daft enough to reply to that, and we got the project up and running with Alec in about 3 days from that initial email. And I didn't tell him about the 3-week deadline. I said, we'll do it in 2 sprints until we get there. We delivered something to the customer at the end of the first sprint in 2 weeks. They were so impressed that a few months later they bought my company, which was fantastic because it meant that I could get out of the VoIP industry and run around Europe doing crazy things like building voice transcription in WASM modules. So, thank you, Software Mansion. You're like more than 2 of the reasons I'm here for today. So let's talk about cloud transcription, or rather why we don't need cloud transcription. So why do we want to do any kind of transcription in WebRTC? So the object of this project was to build a facility to allow us to transcript any WebRTC stream that the user can see in the browser. Reasons you want to do that are things like note-taking, summarization, intent recognition, even some of the content moderation reasons. So if you're trying to architect something like that, there are a few different ways you could do it. So in theory, you could use the speech recognition API because it's a standard, it's a W3C thing. It's pretty well implemented in browsers. Problem is, you can't actually use that in anything other than the system audio input, the microphone. There's kind of a good reason for that, and that is that in most of the implementations, it's using a cloud service to do the transcription. So if you use the Cloud Speech API, what's actually happening is your audio is getting sent to Google, using their APIs for free, effectively, and then sending the transcription back down to you. So there's kind of a bit of a problem with that. That you can't use it to hook into an arbitrary WebRTC stream, but there's also a privacy issue there that if you're using the Web Speech API, all of your data's going up to Google and coming back again, which, depending on your application, may be a problem. But it doesn't matter because it's not usable in this context anyway. So the other way you can do it is using cloud service. So you write an extension. It hooks the audio. You send the audio stream to one of the many cloud services. Google seemed to lead this space for accessibility. There are lots of others. There's the OpenAI commercial Whisper service. There's Azure. All of the cloud services have a voice transcription API that costs an amount of money. There's an interesting entrant called Banafo, who've got an interesting model. And one of the things that they will do is on-prem. So, you know, all of this stuff, it costs some money. There's a privacy issue because you're sending all of the speech from your user's desktop up to a cloud service, getting the transcriptions back. So what are the other options? Well, you can do it on your own servers. That's good. So that gets rid of the per minute cost for running your transcriptions. And, you know, you may trust your own server infrastructure more than you trust the cloud service providers. Your users may trust you more than cloud service providers. So you've got a couple of ways of doing that. You can use one of the many open source models that are out there. Speech recognition is a really venerable sphere of endeavor in AI. There are some models now that are, you know, nearly a decade old that have worked very well. They tend to be the older models that rely on having grammars, so you're effectively giving them constrained dictionary to start with. Coley is a good example of that. But they work really well. There's Deep Speech, which was the Mozilla initiative. They spent a lot of time and money on that, I think in a window kind of from about 5-6 years ago through to about 2-3 years ago where they stopped funding the project, and that was based on an earlier project. There's kind of a successor to that called Paddle Speech now, which has sort of had the moniker Deep Speech too. So there are all these different open source models that you can go and look at. You can run them up on your servers, and okay, it's going to cost you a bit in compute and GPU, but you can actually build yourself a transcription engine, say for your note-taking or summarization service, and do it on your own hardware. That works just fine, or on your own leased cloud servers. There are a couple of turnkey services. I mentioned Banafo earlier. They're kind of interesting because they will sell you a bring your own hardware license. There's a UK company called Speechmatics who will do a similar thing. So it's a perfectly viable way of doing that. It gets rid of kind of the unit per minute cost. But you've still got substantial cost there. So, you know, if you're scaling this to hundreds of thousands, millions of users, you're going to be spending a lot of money on that compute cost to do the transcription. So we'd got a project in mind inside one of our companies, Applice, to do this, but it was kind of contingent on basically having a near zero incremental cost for the transcription. So I figured, you know, can we push this out to the client? Because in any kind of cloud model, the best possible place to use compute is on the client's desktop, right? Because then your scaling cost is minimal. So, okay, crazy idea. Can we effectively do our transcription, but do it within the browser? And the obvious way to do that is to use WebAssembly, which allows you to push a model down there. Started playing with this and found this excellent repo by Georgi Gagarov, who has basically done CPP, C++ versions of of a lot of the major models, and one of them was the OpenAI Whisper, the original open source version. So we had to play with that, and indeed, even within there's a little proof of concept, an example using WebAssembly with an example, you know, kind of index.js there that actually works, and it works with, you know, straight out of the package. You can just clone the repo, run it, great. So we figured, okay, let's have a go at putting that inside a Chrome extension and see if it works. So I'll kind of cut to the chase, really. It does. And we built a Chrome extension to do it. Let's have a play with that, actually. Most people do the demo at the end, but let's do it in the middle here. So all I'm going to do is, there's a little VoIP industry joke in the video that I've chosen here, but we'll just choose a YouTube video. And we'll play the YouTube video.
Hi, everybody.
We'll
How are you?
the
Thank you so much for that introduction. That was great.
Go back to the transcription.
Yeah, exactly. So those of you who have attended my talks before at Astracon or IT Expo probably know that in this environment, I'm qualified to speak about one thing and one thing only, and that is IVR. So that is what I do pretty much every day, all day. IVR is my passion and it's my focus. And
This is
a
where I
few
get
years ago,
nervous,
it became
but it's
clear to
fine.
me that my job is so much more than just recording IVR and sending it back to clients.
So let's,
More and more
stop
people are
this now.
asking me for my opinion about.
So as you can see, we got quite a reasonable transcription there until I exited early. So that exists. It's on the Chrome Web Store as a 1.0, and I horrifyingly looked at this repo when I came to refresh this talk and realized the last commit was in July this year. We're moving it on a little bit from there shortly, but it is something that you can download and play with and find. Yes, I definitely don't want to do that. Thank you very much. Okay, so what challenges did we find while we were developing this? So one of the issues, actually, the little example WebAssembly module kind of ducks this issue by effectively using the recording interface. But one of the challenges is getting the streaming audio into the Whisper model. And the web audio API isn't fantastically brilliant for the use case of I want to get hold of raw data because I want to feed it into something that's got side effects locally within the browser. So the model they used was to use the web recording API, which is brilliant. What it effectively does is hands you a sequence of blobs as your web recording goes on. But then because that's a complete web recording inside a container, they basically then have to do a local render of that to get it into a buffer of, I think, float 32s that the model actually uses. And that's reasonably expensive, but it also leaks memory like heck over time, which means that you've then got to stop and restart the recording so it glitches. So that process was not going to work for our application. So we looked at a different approach where we could get direct access to streaming samples, which is what we really want. Script processor would have been ideal for this, but it's deprecated. So that allows you to effectively get called with an array of samples on the main thread. But as I say, it's now a deprecated interface. There's a good reason it's deprecated interface. It runs on the main thread. So audio worklets is a better solution. Audio worklets are kind of cool. You register a plugin. That plugin gets handed arrays of samples in a streaming fashion. The only problem with that is that it runs in a very limited context off the main thread, so you certainly can't do things like call WASM modules from it, or certainly not within a Chrome extension. But there are some reasonable things you can do with it. So one of the things you can do is post a shared buffer back to the main thread. So that kind of feels hideous in a way that you're doing this streaming, you get your samples, and then the first thing you do is post them back to the main thread. But it does work, actually. It works quite well. What it also allows us to do is some pre-processing off the main thread as well. So we can do silence detection so that we're not trying to transcribe silence. And one of the ways that we turned the plugin really into a proper streaming plugin was by doing silence detection, carving up on the silencers and feeding that to the Whisper module. One of the other issues that we hit was that Whisper isn't really a streaming model, and particularly I'll get into talking in a second about the size of the models that we're able to use in CPU in WASM. Whisper isn't a streaming model, so the ability to pre-process segments, and we were finding that if you saw that it was quite lumpy when it was coming out in the transcript output there. And kind of one of the reasons for that is that you need quite long samples. You need kind of 8, 9, 10 seconds of sample to give it some context to operate sensibly. If you start chucking 3-second samples at it, you get really bad output from the tiny models we're using. So because we were doing an audio in a worklet, what we could effectively do is chop up the audio on silencers. So we would find a chunk that was roughly in that window that we knew was optimal for the model, chunk it on silencers, do a little bit of audio overlap at both ends, and then throw away any kind of repeated words that come in. So it's a little bit hooky as a way of doing it, but it does seem to work really quite well. okay, so this stuff works, and you can just about get it working on your dev environment. Next thing is getting it up into the Chrome store as an extension. Anybody here built Chrome extensions? Okay. Anybody here built V3 manifest Chrome extensions? Anybody here built V3 Chrome extensions and enjoyed the experience? Okay. It's quite a big departure from V2, and one of the reasons for that is Google invented the V3 manifest standard to make it easier for them to audit extensions and what they do. And V3 is now mandatory, so you can't put a new extension in the Chrome store on a V2 manifest anymore. I'm not sure whether that works if you've got existing ones, but one of the things that V3 does is tries very hard to stop you executing any code that isn't in your package. That's the main kind of change with V3. So what the Google Store want to be able to do is basically see every line of code that the extension is going to be running. So what they won't let you do is the trick of having a skeleton plugin that then pulls code. So everything, the WASM code, the model, everything's got to be in your package. They tightened up a whole load of things about self-modifying code, and it's just a general nightmare to get stuff that's at all ambitious up and running in a V3 manifest. However, there is a bit of kind of wisdom out there that you can't run WebAssembly in V3 manifest extensions. That simply isn't true. Google did flip-flop on this, I think, as recently as 18 months ago, but now the incantation is within your script self-context, WASM unsafe eval, which is allowed in the content security policy for the extension. And that, by the way, is the kind of the full manifest for the extension. So you do, kind of an absolute minimal amount of permissions in the extension. You really just tab capture, which allows you to get the audio from a single tab. You don't need to worry about the microphone because of the way the microphone is handled is like any other media request. So it's just the extension is an origin, just like an HTTPS origin is. We also did some stuff. We had to do some stuff around modifying the way the WebAssembly was compiled. So standard WebAssembly, mscript and linking effectively uses dynamic execution to build the WASM module. So you have to disable that and actually going whole hog and turning the WebAssembly module into an ES6 module because it's 2023 worked quite nicely. So that can be made to work perfectly well. So if you're at the point of giving up on WebAssembly in V3 extensions, which I must admit I was several times over the course of this project, it can actually be made to work, and come and have a chat to me afterwards. Yeah, I think I've covered this anyway, actually, so that's the microphone. Joys of not bringing the speaker notes up. So is it useful? Yeah, I think it is, actually. We've got some plans about how we're going to use it, and a live project which is looking at delivering some end-user functionality rather than just that simple extension. There are, however, some limitations. So it's not, native human speaker in not real-time transcription accurate, but it's broadly as accurate as some of the bigger models. You can only really, this is a 6-year-old presentation carting around on trains in a bag laptop. It's got no GPU. As I say, sort of any sort of less than about 7-year-old hardware. I think this might even only be dual core, it's certainly not more than quad core. Runs the tiny Q5 integer quantized Whisper model. So it kind of works in most environments. One caveat actually is that I showed you that English transcription. Other languages aren't as good in the tiny module, in the tiny model. So you do kind of, we do need to find a way of running larger models to get more faithful transcription. And file size, it's not just compute, it's file size is one of the limitations on that. So the tiny model we used here is 50 meg. When you start going up to the base model, that's about 150 meg. And then the small, medium, large are between 0.5 and 2 gigs. So bundling those into a Chrome extension is going to be kind of interesting. So where do I think we will probably go next, and where's the sort of next development for this kind of technology? Well, Web GPU is clearly going to be super interesting because at the moment we're hitting, if your target model is for kind of consumer laptops, the kind of thing that might have been the bleeding edge 6 or 7 years ago, then you can get away with the tiny model and it will work. If you want to go to the base or small model, which is really essential for non-English languages or most non-English languages faithfully, then you're starting to be compute limited in that environment. And I think Web GPU is going to be the answer to that. So we're starting a bit of work at the moment of moving to a Web GPU model. And you know, the ideal scenario would be a single extension which, based on the capability of the device it's running on, either uses Web GPU if it's capable. If there is no GPU, then it uses WebAssembly C++ code. And if none of those are available or useful, then it defaults back to maybe pushing up to a server. But it does allow, if you're building a service that needs to do audio transcription at scale, you know, even if you snag 95% of your clients that way, that means that you're saving on the cloud compute resource you need or cloud GPU resource you need centrally to bring all those transcriptions in. And it's especially useful in an environment where privacy is essential, because the key property of this extension is that neither the audio nor the transcription need to leave the user's browser. So you can deliver something where the user is assured that none of their data is leaving the browser. Okay, so that's my entire presentation on the topic. Questions?
Okay, thank you. It was really interesting. Actually, why did you build the extension? Was the reason that the size of the model was too big?
Why did we build it into an extension?
Yes.
Oh, that's simply so that it can snag. So the use case involves being able to snag any WebRTC audio stream in a Chrome tab. So if it's, you know, any meeting, whether it's Zoom, Microsoft Teams, if it's running in the web client, you can snag the audio if you're running in a Chrome extension. That's the reason for it. That was the use case.
Okay, but actually it could run just as a regular website.
If you control the website.
Okay.
The use case here is about transcribing audio which is coming from and going to. And one thing I didn't actually cover in the demo was we mixed the microphone as well with some diarization to effectively work out whether it's coming from. So what this means is if you go on to a Microsoft Teams meeting, for example, actually this is a bad example because they have their own note-taking, but if you go into a meeting service that has no note-taking, you can use this technology effectively to do the note-taking adversarially in an environment that isn't designed for that.
Awesome, thanks.
Hi. Another web audio WASM script processor node worklet and so on developer here.
Okay.
So hi.
Nice to meet you. We'll have a coffee later.
Let's do that. But I wanted to pick your brain about the performance differences between script processor node and worklet, because my findings were the exact opposite of the marketing, which was that the worklet was going to be more dependable and faster. But I find like if you have any animations or stuff like that on any canvases or anything like that, Chrome for some reason like really prioritize the graphics and you get lots of missed scheduling on the worklet. Was that your experience as well, or maybe you got around it somehow? Or?
No, we didn't get around it somehow. It's less important because we don't need the worklet to fire real time. All we're using the worklet for is to collect samples. You just need a streaming way of getting those arrays of data that you can push into the WebAssembly. And because, yes, the transcription is real time, but it's not real time. If I miss a load of samples, it still gets into Whisper in the end. And, you know, at first I was kind of horrified by this approach of taking data. I mean, worklets are designed for passing data through, right? They're designed for transforming it. You transform the data, you pass it through to the output. So the idea of kind of perverting that in a way to grab the samples on the way through, just chuck them straight back to the output, and then post them back onto the main thread so that you can push them into WebAssembly and then from the web. I had this fantastic view that you would just use a worklet. You would take the audio in, and your transformation would be turn it into, UTF-8 or something coming out. That seemed architecturally quite nice, but you can't do that because you can't access anything in the context the worklet's running in. Which I think I kind of perverted the question you asked into a different question, but
No,
there you go.
It's fine. So, say a ring buffer between the worklet and whatever is doing the processing.
Yeah.
Something like that, right?
Yeah.
And you're definitely not missing any of the buffers coming in, because we are.
No.
Okay.
Okay. I mean, it may be just because we're not working it hard enough. And in this context, all we're literally doing is sitting in a tab which has got one meeting open, probably from a meeting service that's only rendering one video. I can imagine, if you're doing a load of video processing as well, or you're on a 10-year-old laptop, I am sure that would become a thing. And one of the challenges of this actually is going to be detecting environments where we are CPU constrained and just go,
Right.
this isn't going to work. Let's stuff the audio stream up to the server, or just hook the audio stream before it comes from the server.
Okay, yeah, just some heads up, if you have something like 10 or
Yeah.
20 canvases on there doing some
Yeah.
sort of animation, for example, some metering or something like
Yeah.
that, that doesn't work on anything that has, for example, dual screens. For some reason, Chrome really slows down when it has more than one display that
Yeah.
it's driving. And such things. So there's lots of corner cases where animation and graphics will take over the priority for some reason. Just a heads up.
Yeah, I'm sure. And in this case, if the CPU is dead anyway, then there's nothing we can do, right?
Right, thank you.
Thank you.
Okay, thank you, Rob. So great presentation. So we have our next speaker, Bartosz Studnik from Flip, will tell us a little bit about handling user-generated content. So, yeah.
All right, video problems. Okay, so let's get the ball rolling. So the user has generated content, so what now? My name is Bartosz Studnik. I am video engineering lead at Flip. Flip is a social commerce platform, so something like TikTok but for shopping, but we build it everything from scratch. So our content are the video reviews, so users buy our products or on our store. Then they make the reviews, the video reviews, so they upload the files to us and we are processing them. And well, what I'm trying to do in my job, I'm trying to make the videos rather like the one on the left than the one on the right. Yeah. So today on my agenda, we'll speak about this mysterious content. Yes. So the videos that actually our users are sending us. Well, sometimes they are not very technically appropriate. So we'll speak about it. I have some examples of it. Then we'll speak about how our approach, so how our video processing pipeline actually needed to be changed according to this mysterious input. And well, we'll speak about some other challenges that the user-generated content, environment, this whole world actually requires from us. So we're all here because we love video, right? Or at least we are interested in it, yeah? But what would love be without the pain you need to go through, right? So all the problems, all the issues, the artifacts, the broken videos, not playing videos, empty manifests, and so on, right? So, yeah, I have some examples of this mysterious content, so let's start with the first one. Right, where would the fun be if everything was so simple, right? So let's not be negative, but let's make it a challenge for us. And actually, it's super satisfying when you have really crappy content and you actually manage to process it. So the first one, I call it the silence, right? Because, well, the user uploaded the video. It had sound indeed, but we processed it and there was no sound. So what would you do in such case? Well, definitely check some FFPro output, right? play the video actually with some player, and check the manifest. We are delivering HLS manifest, so we are checking this one. So yeah, even though the manifest said, well, everything is all right, the audio is there, well, there was no audio in the playback, and the FFmpeg gave some unusual output. So as you can see, well, there was some weird audio codec, actually, and the only information that we knew that it is a PCM audio format, but well, there's a problem. There is a bunch of PCM audio formats, and if you do it wrong, well, the good part is that we didn't have sound, because the other part is that you have such a glitchy sound, really terrible sounds, and I needed to go through all of them, not pleasant experience. So we needed to figure something out. Where our solution is adding a new tool, which is EXIF tool. Maybe you are familiar with it, but it doesn't really solve the problem at all, because it just adds some more information about this format. It doesn't really tell us what's the case. So later, based on this PCM audio new metadata, we need to determine which exactly format it is. And well, we need to change it to some friendly format like AAC or Opus, right? So moving to the next one, I call it Jumper. I play the video in a second. Well, the video was jumping. We were missing some frames. So I slowed it down for you so you can easily see what was happening. Yeah, exactly. I hope you have seen that one. Is it visible? Yeah, pretty clear. So what was the case? When you are packaging video, you are expecting segments of the same length. The manifest is saying, yeah, everyone is 2 seconds, right? But not in our case. Well, the segments were, in this example, 5 seconds long, even though the manifest said they are 2 seconds long. And sometimes they were 20 seconds, 30 seconds, 1 minute. Well, it really depends on the content. And what our players said, okay, 2 seconds is 2 seconds. So it was playing only 2 seconds of this 5-second segment and was skipping the rest. That was causing this jump. And some other player, by the way, was playing it just as usual. So it didn't really care what manifest said and said, okay, I paid for the whole segment. I'm going to play it all, right? So, but this is just a side effect. It's not really the case. It was not, in my opinion, it was not the problem with the player. So it was the timing issue. Yeah, we all love timing issues. So the green line on this visualization is the presentation timestamps, the PTS, of the regular video. Yeah, it's just rising. It's monotonically rising. And well, our jumper video was dropping, which should basically never be the case. And well, FFmpeg wasn't handling as well. As you can see in this example, the frame number 2, 5, and 11 wanted to be displayed at the same exact time. Well, that is technically not possible, probably. So yeah, that was the case here. So resetting the PTS helps most of the times, but not always, because when you have, for example, variable frame rate videos, you cannot just guess what frame rate is at a given moment of time. So it's not the case here. So moving on to the next one, pretty similar. I call it the single framer. I see my team is already smiling. They love this one. It's not necessarily single frame, but yeah, this is the whole content, the whole video. It is some still image, beautiful, super low quality, and some music in the background, right? So the case here is pretty similar. Again, the timing problem. But as you can see, in this case, there is some kind of pattern of here. So frames 1 to 6 in this example and 7 to 12 have exactly the same presentation timestamps. I think someone thought that looping a video looks like this, but it really doesn't and shouldn't. But why the video was shorter? Because, well, I didn't say that the video was actually shorter than the original, right? That was our symptom. So we have the original video, for example, 10 seconds long. The PTS starts to loop in some moment, and the rest was actually skipped. So again, resetting the PTS actually helps here, but well, I don't even know which kind of program is able to make such output. I was trying to reproduce it, and yeah, no luck here. FFmpeg just told me, go away, man, it's not possible to make such PDS. Okay, moving on to the next one. Yeah, beautiful dog. I call it empty framer because, well, we have beautiful footage on the frame number 1. Then we have frame number 2, which is empty. Not necessarily black, sometimes green, red, yeah, it depends, and so on and so on. And that was our content. So it's really hard to notice, actually, when you're looking at it, and it is a high frame rate video, sometimes it's really hard to notice with your bare eye. So the case here was that the quality was super low and the bitrate was super high because the compression between the frames was actually not existing, because what do you refer to? The void, right? So yeah, that was the case. Fixing these videos, removing the empty frames, actually, as you can see, the quality was much, much bigger and the bitrate actually dropped. Right. Sometimes there is a problem with color. So on the left side, you can see the video that was processed by us, and on the right side was the original. I have some more examples that you maybe can see it much brighter what was happening here, right? So HDR to SDR translation is not always straightforward, and well, you need to handle it somehow, right? And it's not straightforward, especially when you have a ton of combinations of the parameters that are related to colors, right? It's pixel format, color spaces, and so on and so on. Well, we need to deal with it, but sometimes it's not just straightforward. Sometimes it's the user's encoder. Yeah, this is some test video, beautiful frame, and some broken frame. And actually, the whole video is broken because there was no iframes later to reset the stream. So each frame was referring to this broken frame that you can see in the middle, and well, the whole video is broken. Of course, we can do nothing about it, but actually you need to deal with such content as well. Yeah, we are receiving such videos, and we need to tell the user, well, sorry, it's not us, right? So what else have we made? I think the variable frame rate is my favorite, and we had a video that was spiking from 0.1 to 80,000 frames per second in one single video. We had a video that was had much more frames per second, by the way, but there was no such a big difference, right? So metadata different than the coded bitstream. I love this one. Empty move atom, missing move atom. I don't know how users are playing those videos, but they were saying that they can play this video. I don't know how it's possible. The variable resolution, yeah, I know it happens sometimes in live streaming, but our users proved us that the variable resolution is also possible with static VOD files. So yeah, again, something unusual. Streams length, right? The MP4 file says it's 10 seconds long. The streams actually are much different length, and the output is even different length of any of those, right? Multiple video streams in single file. Okay, sometimes it's actually the case, and we need to handle it, but sometimes those are two separate videos and one audio stream. So yeah, please, Mr. Encoder, pick the best one. Basically, that's it. Unknown stream types. Well, even though there is nothing in those streams, the FFmpeg was processing our videos for hours instead of minutes, right? Super weird thing. And trust me, many, many more. I could probably go here for hours to speaking about what went wrong, what mysterious content did we receive. So yeah. But how did our processing pipeline change according to all those challenges? So at the very beginning, it was pretty straightforward. Right, some video upload, some brief analysis, and encoding and packaging in one step, by the way. So a lot of things were happening in this last step, so encoding and packaging. So we needed to deal with all the things that I just mentioned to you. We needed to prepare the content, so the HDR to SDR translation, this weird audio format, and so on and so on. Well, that was super difficult to actually maintain. Debugging was a real nightmare because anytime something went wrong, we needed to evaluate the whole thing again, and it was super slow because there were no parallel steps actually. So what we've done, we enhanced our video processing pipeline by adjusting our, extending our analysis step. So we extracted a lot more metadata right here. We added a new step which we call normalization. So what goes in this crappy video, right? And what goes out is something that is ready to encode, to process, and we don't need to care about all those stuff. So single point of failure. Then we are just doing the regular things, so write some thumbnail GIFs, encoding packaging, right? It's orchestrator by our microservice. And well, later we measure the video quality, so we are using the VMAF Netflix metric for the video quality. And well, what I think is unique in our video processing pipeline is that we verify the packaged output. So what we are doing is that we are fetching the manifest, the playlist, the segments, and we are making a bunch of checks on them to actually make sure or just check if the video is going to play well, right? So we are doing our best to actually, before we deliver the video to the user, we are making those checks to actually look at this content, whether everything is all right. So this step actually saved us a lot of time because most of the issues that I've just presented to you were discovered by this exact piece of software. So a pretty big value coming from there. So what are challenges are here in the UGC word, so user-generated word, right? So users scroll fast, like, you know, when you have the TikTok, YouTube Shorts, things like that, you're just scrolling. And well, our videos are short as well, up to 1 minute, so the users are also scrolling really fast, and we need to deliver this video quickly. We have the product reviews. We cannot cheap out on the video quality, right? There is no way to do it. And well, the user also wants this video to be processed as soon as possible, so yeah, we need to process the video quickly. And on top of that things, well, we have this normalization, verification, dealing with all this UGC stuff. The content is extremely diverse, so one video is super different than another, and actually encoding is a very big challenge. So looking at this problem from some other perspective, well, video processing takes too long, right? What do? We encode it quickly, right? So what happens? The video loads too slowly, and we need to spend more time on encoding. It's a cycle, one problem causing another, and we are not even speaking about the video quality yet. So we needed to figure something out. So as you can see in this triangle, you can only focus on one side of this. You need to make some compromise. So what do? At the very beginning, we are focusing on the processing time and the bitrate. So we are delivering the AVC stream. The video quality is, well, okay, but the processing time is as low as possible, and the bitrate is also okay. Later what we do, we are delivering the new codec stream. So as you can see, the video quality is much better, the bitrate is also optimized, but we are sacrificing a lot of processing time because it just takes longer. And what we do as last step, and we don't always do this, is the optimized encoding. So we only do it when we see that the video quality is low, or the content is or going to be popular enough. So it's a win-win situation. We pay less for the transfers, and the users are getting higher quality videos with lower bitrate. To do this, to achieve it actually, we use per-title encoding. And in my opinion, there is no other way around than using the per-title encoding for the perfect content in the UGC world. Well, per-title encoding is something that each video asset is treated differently. So you encode it with totally different encoding settings, right? And what we do, we don't really focus on the H.264 or the AVC codec because the gains 3 to 7% aren't really the thing that we are going for. We are focusing on the VP9, and we hope to use AV1 soon, especially after the latest Apple's announcement that they are going to support it on iPhones and the latest software. So I think moving forward to this per title encoding, if you want to do this, you need to start slow. So it took our team around thousands of encodes to just have the basic understanding what is possible to achieve with per title encoding. Yes, it was a brute force method. There are tools designed to actually do that for you, so find the best or optimal encoding settings. But to understand it, we needed to check everything, right? Everything that came to our mind, the resolution, the speeds, the bit rates, and so on and so on. And that is costly, right? Because, well, when you are encoding one single piece of content thousands of times, it takes a lot of time. So it takes a lot of server time. So it costs something, right? You need to understand what you want to achieve. So whether you want higher video quality, or you want lower bit rates, or you want the processing time. Well, maybe the processing time isn't for the per title encoding, right? But you need to understand your content. And when we did the same thing for some other video, well, as you can imagine, the results were totally different. So that's the case. You need to understand your content and focus on the things that you want to optimize. And speaking about the optimizations, I think the last thing that I want to mention is that you can actually optimize beyond encoding, right? So a lot of things can be optimized on the client side, on the transport side. So what we are doing in our case, we are fetching the content in the background. So again, when you are scrolling this feed, right, you see the video number 1, and you are going to see the videos 2, 3, 4, and so on. And what we do, we are fetching those videos in the background before you actually see them. So again, when you are scrolling fast, you will receive them quicker, right? And our metric shows that over 90% of content is fetched in the background, and the video start time, well, they are really, really good thanks to that. And last thought that I have, according to the UGC and all those mysteries that you actually need to deal with, is the observability, taking care about your errors. Well, when you have such a weird inputs, you need to take care whether they are playing, if they are buffering for some unknown reason. We had that as well. And you need to also understand how long the users are going to wait before the video starts, right? So this metric left before video start, or as maybe more of you know, exited before video start, right? So I think that was everything that I wanted to cover today. So if you have any questions, that's the best moment. I also will be around here today and tomorrow. And I have some bunch of stats in the background. So if you are not interested in the questions, we all like fancy numbers. So that's for you. Thank you.
Any questions? Okay, this one.
Yeah, thanks a lot. Very insightful talk. Also, a lot of it was very relatable. I've been struggling a lot with converting the HDR content to regular dynamic range. Do you have any tips for that?
We are using definitely the FFmpeg with libzync. Maybe you are familiar with this one. So that was our solution for that. And actually, in my opinion, there is no other way around than reading those specifications. And well, as I said in one of the slides, where we have a lot of those color-related parameters and the combinations of them. So it's adding a lot of trouble here. And while we are just playing with it, trying our best to achieve it. So yeah, reading the standards, understanding what's beneath that. That's the best I can say right now, because that's a really long story, right?
Thank you.
Okay. Any other questions? If not, well, thank you, Bartosz. Very, very interesting talk.
Thank you as well.
Yeah, we'll have a short break for coffee. There is coffee and drinks and some snacks just around this corner. And we'll restart at 11:30. So, yeah, thank you.
Thank you very much.
Really cool. Yeah.
Works?
Yeah, yeah,
oh,
sure,
okay.
it works. Do you have a sound in presentation?
No, I'm just
No,
going to
okay.
talk.
Okay, thank you.
Thank you. question. After your talk, do not instantly take away your microphone, but if you could go just to the back of the room to the audience.
Of course, we will. Thank you.
Okay, can you hear me now? Yeah. Okay, so welcome back after the break. Yeah, I guess almost everyone is in. So the next speaker, Lorenzo Miniero from Miteco, will talk about Janus, WebRTC server. We had some experience with that. Yeah, so go ahead.
Thank you. Thank you very much. First of all, yeah, I'm really excited to be here. It's my first time in Poland, and so I'm doubly excited because it's my first time here and it's my first time at a brand new RTC event, which is always a nice thing to do. So I do feel the pressure, but I hope I will not, I will not disappoint you. And today I'll be talking about some new things I've been working on in Janus, and specifically bandwidth estimation, which is kind of a big mystery in WebRTC that I'll try to demystify a bit if I can. And I'm Lorenzo Miniero. I'm from Naples in the south of Italy. I got my PhD at the university there, and with some colleagues, I co-founded a small company called Miteco. I'm the main author of Janus. That's what I do all days mostly, and those are a few links that you can refer to if you want to learn a bit more about me, including some ugly music that I like to write. And this picture comes from one of the ComCon editions. If you don't know what ComCon is, it's a really cool event that happens in the UK every year. Find Dan Jenkins around and he'll tell you about it. It's going to happen soon again. It's really an event that I recommend. And my company is a small company that was started as an academic spin-off because we all got our PhDs there. We worked a lot with real-time multimedia from a standard perspective, do the usual things, and our office is somewhere over here, so definitely not a bad place to be, as you can see. It's quite sunny and quite nice. But coming to the actual topic, so what is bandwidth estimation? Because it can be a bit confusing in its definition itself, and in general, it's a matter of figuring out how much you can send within a so-called unit of time. For instance, within a second, how much data you can send, because of course you don't want to send more than you can send because maybe you have local constraints, or no more than the network itself can accommodate because there may be some bottlenecks somewhere in the network, or more than the receiver on the other side can receive. So you definitely don't want any of those things, which is why bandwidth estimation is useful. It's important not to confuse it with congestion control. They sometimes work together, but they're not the same thing, because bandwidth estimation is the estimation of how much you can send, and then congestion control is what kicks in order to avoid leading to congestion and avoid issues like packets getting someplace too late or not going there at all. And of course, it's important to do those things because otherwise you can incur in congestion, you can incur in failures and stuff like this. And it is doubly important for WebRTC because in general, whenever you're doing, for instance, you're downloading a file or uploading a file, you really don't care about delays. The same amount of data may take more or less depending on how much bandwidth you have available. It doesn't really matter. You slow or speed up depending on the congestion window. With WebRTC, you really don't have the same luxury. So everything is real time. Anything that gets there 1 second later is too late and is useless, which means that typically you do need to adapt the data itself that you are sending in order to avoid congestion and try to fit in whatever in the channel that you have available somehow, which typically requires exchanging some live feedback among the peers of the conversation. And we'll share a few words about this later. Typically, it requires some messages being exchanged between the two parties. And of course, how you adapt can vary wildly, because, for instance, browsers have access to the encoder and so can tweak things very easily. When you're working with an SFU, it's different because you don't encode things yourself. You're just relaying media coming from different places, and so you have less flexibility in what things you can do, but we'll see how that can be solved anyway. Which means that the idea is doing something like this. Maybe you are sending something that is very high quality, the subscriber doesn't have enough bandwidth to receive that, and so somehow you need to make sure that the other peer receives something meaningful, which can be done, again, by just re-encoding that stream, reducing the bitrate, or possibly playing with simulcast and SVC by sending a lower quality version of the same stream and then just switching between layers somehow. The idea is that bandwidth estimation should allow you to do both things depending on how you are actually encoding things. And it is, of course, not an easy problem to solve. There was a working group in the ITF called RMCAT that was specifically created to tailor exactly that. A few algorithms were discussed during those efforts. The most known are Scream, NADA, and GCC, which stands for Google Congestion Control. And NADA was the main outcome of that working group, but if you look at it in practice, basically, when you look at libWebRTC, which is one of the thing that basically all browsers use to actually implement WebRTC, you see that they use GCC, which typically leverages a specific RTCP message for feedback, and which is documented there. And it basically uses a combined usage of RTP extensions and RTP feedback. So for outgoing RTP packets, you put a label, and this label is then used in the feedback so that you know as a sender which packets were received, which were the inter-arrival delays and stuff like this. All information that is very useful for the algorithm to figure out the available bandwidth somehow. And I'll explain how I use that information for the same thing. Which brings to Janus, of course. So just out of curiosity, how many of you already know Janus or have heard of it? Okay, so more people than I expected, which is really cool. So it's a WebRTC open source server, and you can find some links over there if you are not familiar with it. And of course, we are talking about doing things in a server rather than in a browser. So a few things change. As I mentioned, a browser generates media and so can fine-tune the bitrate of the stream they're encoding. They can encode the stream with a slightly higher bitrate over time to do some tweaking. With the server, you cannot do that. So you have to work with the streams that you are receiving. And so I started by having a look at how the existing congestion control algorithms work. And the problem is that if you specifically look at GCC, there are drafts, there are papers, but they are very outdated. So what you find in documents is not what is actually implemented in browsers. And NADA itself, which again is the main outcome of RMCAT, is interesting, but is not usable at the moment because it does make use of a specific RTCP message that none of the browsers implement, so you cannot really consume that. There are ways to use the existing TWCC with NADA as well, but they are a bit of a hacks. The other problem is that when you start looking at how those algorithms work, this was basically my reaction. So there's a lot of complex math in there. I'm an engineer, so I should know, I understand how all that works, but it is indeed complicated, sometimes overly complicated. And when you start asking around with other people that work in the WebRTC field how bandwidth estimation works, you typically get something like this. So you feel like you're in the Twin Peaks Black Lodge, well, very old reference. I see a lot of young people that may not even know what they are looking at right now. But basically, it is, you start asking questions and you get very cryptic responses back. So it's very hard to figure out how bandwidth estimation works by just asking around. You have to do a lot of homework. And luckily, I mean, I have a lot of smart friends in the WebRTC world. I exchanged some feedbacks with them, some discussions, and so on. And so I did figure out that, again, the first thing to understand is that we are working in an SFU, which means working with existing media streams, for instance, simulcast layers that have different bitrate ranges that you can use to jump from one layer to the other to simulate increasing and lowering the quality. I also figured out that Google Congestion Control is not a common choice for a bandwidth estimation algorithm for SFUs, because again, it's very poorly documented. So, and also too complicated. So it's hard to basically figure out how to use it for the usage within a server. And besides, many of those that did try to do the same thing that I did discarded eventually GCC also because it didn't seem to fit well the requirements of an SFU rather than a complete endpoint that needs to work with media. And so I decided to do something different. So I followed the advice of Sergio Garcia Murillo from Dolby, who did a similar thing. So he said, rather than using one of the algorithms, why better to try and come up with your own? So it may be less efficient than existing ones, but then it will be something that you know how it works, you know what to tweak, you know when, how to change some things here and there when things don't behave correctly, and which is what I eventually tried to do as well, by starting by some important key points. So these are the main important things to know when working with something like this. So you do need to start from acknowledged rate, and I'll go in detail about all of this in a second, but acknowledged rate is very important. You need to know how losses impact may impact your estimate. Even more important, you need to know how delays can impact this as well. And then you need to involve probing so that, again, we don't have access to an encoder. So if we want to know whether or not we can send more than we can, and we have a static group of simulcast layers that always send pretty much an average amount of bit rates, if we want to know if we can jump from layer 1 to layer 2, we need to inject some let's say some generic traffic in the middle that doesn't belong to the RTP traffic, but is just used to figure out if we can send more, basically. And the acknowledged rate is the very foundation of that, because, and it is, let's say, an imprecise, let's say, a very rough estimate of source, but it is very important because, again, I mentioned that with, for instance, with GCC, you put a label in RTP packets, and then you receive an RTCP feedback about those packets that you sent, which means that if you know which packets you sent, you know how large they were. When you receive feedback, you also have an idea of how many bytes the peer actually received. And that is your acknowledged rate. So this is the amount of data that the peer acknowledged they received, which means that you have an idea of how much data actually managed to get there, which is very important because it gives you a foundation. So let's say, at the very least, a minimum of the estimates that you can use. And again, it's very rough because it depends on how much you send, not really how much the channel allows you to send. But it is still quite important because, first of all, it gives you a number to start from. As soon as you start, you have an idea of what your estimate may be. And then when you encounter problems, maybe there's congestion and so on, you know that the acknowledged rate you can fall back to that for an estimate because at least that managed to get through, and so that's a good value. Losses are, of course, important because the moment the peer tells you that they lost some packets, you may know that it may be related to congestion, and so that you may have to slow down. At the same time, it is a reactive mechanism. So it means that you do something, but only after a problem happens. And this is, of course, something that can help, but it's not really that interesting, especially if you want to avoid things like video freezes, artifacts, or stuff like this. And besides, losses may not even be related to congestion. You may be on a Wi-Fi that always drops some packets because it does, so and not really because of congestion. So you need to be aware of this in order not to overreact to too many losses and not treat them as a symptom of congestion. But that said, there are different ways by which you can get info on losses, and it is still important to have at least an idea of the percentage of packets that you lost along the way. Much more important is working with delays instead, which is less intuitive but also much more powerful, and in fact it is at the basis of several of the algorithms that are out there. So for instance, in BBR, it's very much used. And the idea is that you start to analyze the inter-arrival delay patterns of packets, which is one of the info that we get back from feedback. So if we send some packets that have some delay in between them, I send a packet now, a packet now, a packet now. And then for those packets, the peer tells me that they received the packets here, here, and here. I know that there is more delay in between those packets than the delay that I sent them at, which may be an indication of potential congestion, which means that it's a powerful tool to have because it means that you could actually anticipate congestion if done right. It means that somewhere over the network there may be buffers that are filling up, which are slowly going to introduce delay, which means that then the moment that you know, you slow down and you send less in order to avoid that from happening. And of course, there's different problems here. So figuring out how to analyze this delay and what to use as a trigger to say, oh, okay, I'm encountering a problem or not. And this was very much a part of my tweaking part. But the most important part is that we do have information on the raw delays in those feedback messages, which is quite important. And of course, I'm just rushing through the descriptions of all this because I don't have enough time to explain how it works specifically, but there is this cool presentation from Matis from the Pion team who actually explains this very much in detail and shows, for instance, an example of packets that are arriving with more delay than they were sent at, as an idea. And for instance, if you look at the BBR specification as well, they also have an interesting graph that explains this more in practice, showing how loss-based things work more from the right and so are maybe too late. And you want to be as close as possible to that junction point over there in order to anticipate congestion instead. And finally, we have bandwidth probing, because so far we've only seen how we can go down, so how we can slow down because problems occurred, because there were losses or there were delays and so on. But we also want to know when we can go up, because maybe we're sending less than we could. And since we don't have access to the encoder ourselves, we do have a foundation because we have the acknowledged rate, but bandwidth probing helps with the going up part, because we can just inject artificial packets that are not the RTP traffic, so the audio and video that we're sending normally, but just traffic that we add that is part of the bandwidth estimation part, though, so that we start to try and send more and more and more and more. And if we never encounter that problem of the delays increasing, which may indicate congestion, it means that we can send more. At a certain point, we'll reach to a point where the estimate says, oh, okay, you can switch to this higher layer now. And okay, I'll do that, and the quality will improve as a consequence. And again, bandwidth probing is another of the big mysteries of bandwidth estimation usually, because then you start asking yourselves, how do I do this? How do I do this? Which packets do I send? How often do I send them? How much should I send? And it's really a matter of experimentation. I personally used retransmission packets for the purpose because they were easier to work with. But just to give you an idea, this is how it works from a graphical perspective. So if the dark blue line is your RTP traffic and you want to send more, you start sending some probing that is not video traffic itself. Everything is fine. You decide to start sending more RTP traffic, and then you start sending more probing to see if you can send more and more. That's basically the idea. And so coming to how I used all of this in Janus, first of all, I had to take into account that Janus is a modular component and has a particular architecture. Because basically it has a WebRTC core that takes care of all the WebRTC stuff, but then how you handle all the media, what to do with the media is all part of plugins that do not interact directly with the core, which meant that I had to split a bit the bandwidth estimation algorithm that I described before into at least two different parts. So I had the Janus core handle all the feedback itself, monitor losses, delay, handle probing, that sort of things, and also come up with the estimate, of course. But then leave it up to the plugins to actually enforce the bandwidth estimate, because of course it's plugins that know what they want to do with the media. It's plugins that know if a user is using simulcast, for instance, how much media a specific user is sending and stuff like this. Which meant adding some controls for plugins so that they can decide whether or not they want to use bandwidth estimation, because of course it's useless to use it unless you actually have a use for it. And most importantly, also to notify the target of the bit rate to the core so that we can implement probing as needed, because the core can do probing, but it won't know how much to probe until the plugin tells them, this is where I want to go. And there is a pull request that I created like 20 minutes ago or something like this just for you to access. And so, of course, there were a lot of efforts already. There were a lot of commits. There was a branch, but there was no pull request. So if you're interested in testing this, you can find more information there, and that's also where I'd like feedback to appear. And basically, in a nutshell, I created a new bandwidth estimation context in the peer connection object in Janus. Every time we send a packet, we keep track of it so that we know how it is, what it is, how its size, its delays, and so on. Anytime we receive a feedback, we reference those packets that we sent in order to create that acknowledged rate basis that I mentioned. monitor losses, inter-arrival delays and stuff, and update the current estimate. Once we have an estimate, we can involve plugins as well, and we have a loop that takes care of everything that needs to happen on a regular basis, including probing, for instance. So anytime a plugin notifies the Janus core that there is a specific target, we'll start probing on a regular basis, maybe stop when there is congestion, maybe stop when there is a change, these sort of things. And then, of course, we need to notify plugins about the current estimate so that they can do something about it. And the only plugin I started from is the SFU plugin, so the one that takes care of distributing media streams, for instance, for conferencing purposes. And I kept it simple for now. So I decided to only work with a single simulcast video stream per peer connection. So you create a subscriber. If that subscription is for a simulcast stream, then the plugin tells the core to enable bandwidth estimation. We start keeping track of the published stream, so the video that the user is subscribed to, so that we know the different profiles of the simulcast streams. We know that the highest quality is 1 megabit. If you use one less temporal layer, it's 800 kilobits, and then so on and so forth. And that gives you the different levels at which you can do the switching, and gives you an idea of when you can switch depending on the estimate. Which means that as soon as we do have an estimate, we can actually use that information for something. And I did make some tests with a single publisher and a single subscriber, of course, with a subscriber getting video from a simulcast publisher and asking for the highest quality as possible. And then, of course, I simulated some issues. So in simulating network constraints, I used Comcast as a tool on Linux, which is just a wrapper around TC and IP tables. So if you're familiar with those tools, you can do the same. And the outcome was quite interesting because, of course, it still doesn't work great because there is tweaking that needs to be done, but it does what it needs to do. So it goes down to a lower layer when there are issues. As soon as the issues disappear, it goes back where it should go. So it's definitely a good start, which I appreciated, but there is work to do. And I'm also basically saving statistics for all of that in real time so that I can graph everything that has happened so that I know how much I'm sending at any given time, how much I'm receiving at any given time, how much of that is RTP, how much of that is probing, which are the targets. These graphs are very useful when you want to figure out why things are not working as expected. And in this case, for instance, this is where I introduced the limitation, and so why the estimate stayed at a lower level, and why eventually I lifted the limitations and the estimate goes back up. And this is a graph of how I'm tracking when I'm going into a congested state, how I'm monitoring delays. And this is, again, very helpful because it can give you an idea of, from a graphical perspective, when the delays are telling you that there is congestion happening. So it's a really useful thing to have. And this is where I'm at, and of course there is work to do because basically I created the testbed right now that allows me to play with bandwidth estimation, which is really cool. But there is a lot of fine-tuning that needs to happen to make it more stable than it currently is. There are some issues related to different browsers because, for instance, Firefox doesn't use the feedback stuff for audio, so it can be tricky if you want to handle both audio and video as part of your estimate. And more importantly, I need to make sure that the video room is much more smart than it currently is, because you could create a subscription where you want to receive 10 different simulcast streams, and then you need to know how to distribute the available estimate among all of them, maybe involve priorities, maybe use something different. It's really complex. And this is really it, but before I'm done here, I want to make an important announcement for us, because JanusCon is our conference, and basically, we did our first edition 5 years ago. We were excited. We said, we'll do it again next year. Then the pandemic started hit, and it did happen. And so after 5 years, we're finally back. At the end of April, we'll do a new event around Janus and WebRTC. So if you're interested about it, we'll do it right in front of this beautiful castle on the sea. So it's definitely a nice place to be. And that's the link if you're interested in more information. There's some cool pictures, some cool information. So please join us if you want. And now I'm done, and also because I'm a bit late as well. So sorry about that. Thank you.
Thank you for the talk. Any questions?
Hi, great talk. Thanks, Lorenzo. I have a question. So initially, you said you look at the algorithms that were there. Could you give us an example of how, what you mean when you say they were overly complicated and over-engineered? And also, as you get into the rabbit hole, do you see your own algorithm getting more and more complicated and almost getting there?
I'll start from the last question. Yes, it does get slightly more complicated over time. The moment you start making some tweakings or start to make it more complex the way that you do probing in order not to step on your own foot and cause congestion where it shouldn't happen, it does get a bit more complex after that, but in that case, it's a complexity that I'm more aware of because I started from scratch. I know how I got there, and so I know how to get back and take a different path. I didn't have the same luxury with GCC because, for instance, just to make a very simple example, in GCC, to track delays and keep track of delays, they make use of a Kalman filter, which doesn't necessarily mean it's too complicated, but it's still a more complex algorithm that may be needed to actually track delays and do things. And most of the over-engineering in those algorithms comes from a lot of experimentation that Google did. So they had millions of deployments, so they had millions of use cases that they were working with, and so they fine-tuned it so much that eventually it gets very complicated very fast. But in that case, you end up looking at some very complex choices that you don't know how to work with. If you need to tweak something for your own uses, you don't know what to tweak because you don't know what box A does or what box B does. And you could look at the specification where they may explain it, but then you have a look at it and it's a very outdated document, and what is in the browser right now is completely different. So for instance, I know that, I know there's people in this room that did use GCC as well, and so they may have had better luck with it and in understanding it as well. But for me, when I tried to look at it, it was basically too overwhelming for me, and I really didn't know how I could fit this all within the Janus architecture, which is why I decided to just do something else instead.
Thanks.
Any other questions? There is one.
So I wanted to ask about the connection probing. What data do you use for connection probing, and what do you use when you start the communication? So do you probe the connection when someone joins the room, or you start with the highest possible resolution and see what happens?
Yeah, the idea is that for probing, I'm using RTX. So I do have already packets ready for retransmissions because the subscriber may need to retransmit a packet using NACs and so on. So I already have those packets. And so what I do is that on a regular basis, I just take a packet from the RTX queue and then send multiple copies on it depending on how much I need to send for probing. And as soon as I start, I don't do any probing at all because at least for the first couple of seconds, I'm in an initial stage where I just observe things. And to just observe things, I just send whatever I can. And this is because the acknowledged rate is what matters to me at the very beginning. So I need to have a rough feeling of how much I can send right away. So if in this case, I was subscribing to the highest quality as possible and it worked, and so I was sending everything, if I was encountering issues right away, I would be in a case where right away the send and the hacked rates are not where they should be, which means that I encounter congestion and I soon need to go back to it. And this initial stage allows me to get the acknowledged rate as a basis and use that as an estimate. And after that, I decide when to do probing, and even deciding when to do probing is a different choice of itself, because for probing, I use a slowly increasing curve because I don't want to start probing too much right away. If this is the target, I'll start, but I'll start slow and I'll try to get to the target slowly. Then as soon as I change simulcast layer, I stop probing because I'm there. And then even if they immediately tell me what the next level is, I don't do probing right away. I want to check if I'm stable where I am. And then after a few seconds, I can start probing. Anytime I get congestion, I stop probing and do a freeze period of a few seconds so that I don't try to do any more probing until a few seconds pass to see if I can start doing things again. So there's really a lot to talk about probing, and it's one of the things where I did fine-tuning the most because it's one of the most delicate parts of the algorithm.
Thank you.
Thanks.
Okay. Thank you. Thank you very much. So the next speaker.
Oh, thank you.
The next speaker is Rishit Bansal from Dite, who will be talking about recording in WebRTC. So, yeah, leaving the stage to Rishit.
Sorry. Yep, that's working. Is this working? Can you hear me? Yeah. Okay, yeah, thank you for the intro. And thank you for having me here. So I'll talk about how do you build media pipelines to basically record video calls. So I'm from a startup called Dite. We basically give a video and audio calling SDKs for you to integrate calls into your app. So, this is one of the features I worked on in Dite. So what will we go over in this talk? So I'll talk about 3 approaches we sort of iterated over at Dite, things we learned along the ways, pros and cons of each approach that we found. And also, finally, which approach I think is the best to use for each use case. So yeah, so first let's try to figure out what is exactly recording. So according to me, a recording is basically on the high level a sequence of 3 steps. So the first step is capture. So capture is figuring out what parts of the video conference basically you want to record. So it might sometimes be just video audio, but it can also be things like chat, for example, right? So the second step is transcode. So it's about taking this raw video and audio data and transforming it into a format that is easier to store. And the third step is storage. So yeah, storage is about where do you store the file, and it also will matter on how do you serve the file in the end. So if you want users to be able to download this file easily, so you would pick a storage which basically supports that. So yeah, and for each of these blocks, you have sort of many choices. So we had clients which came and told us, hey, we have a use case where we have 2 people on a call, and we want the videos of each person as separate files. So I want peer A.mp4 and peer B.mp4 as 2 separate files. The most common use cases, of course, most clients want to record the whole video as one grid. So they want the actual UI, what you see when you enter the call. And also in the storage type, the most common use case we see is to store to a file in multiple formats. Of course, if it's audio, it might be MP3 or MP4 for video. Some clients want to stream to a third-party platform. So it could be YouTube or Twitch. And also, we have our own live streaming infra. So we also sort of reuse our a pipeline for also that. So yeah, so let's go over the ways you can sort of tackle all of these problems. So the first iteration we did was right when we started. So we didn't really know about the whole space yet. So we learned about, so I call this approach client-side recording. So there's this API on the browser called a media recorder, which basically gives you really easy-to-use interfaces to record media. So you can pass this any kind of media stream object. So it could be from a canvas, it could be from a raw video audio track from your SFU. So, and it supports a few video encoding options. So you can set the MIME type, you can have a WebM with X264 inside it, or VP8 or 9. And also you can set the video and audio bitrate. So yeah, you have a few options to basically tweak. And this happens on the client side. So basically it's this JS API, which runs in the context of the browser. So yeah, I've linked the docs for the API. We'll just go over how this looks sort of in code. So yeah, I have I make a call to get media, which will basically get the screen share track for the user. So you might have like seen on Meet, for example, when you click share screen, it shows that prompt where you have to choose the screen which you want to share. So this is basically that step. So once you do that, you get the media stream, and then you can simply pass this to the media recorder API. You can attach a few callbacks to basically get the final video that was recorded. Yeah, and in this example, I sort of just make some kind of link for the user to download that video on their browser. So yeah, if you want to visualize how the end-to-end flow sort of would look like, so you would have some kind of record button on your browser, and yeah, as I said, a prompt would open up, and you would use the APIs I showed on the previous slides to basically record the video, and then you get a file which you send to your storage. Yeah, and one very crucial part which sort of affects where you can use this approach is that it runs on the client side. So for a normal video conferencing application, since you have multiple peers joining a meeting, if you do the recording locally, you get these multiple sources of truth for what gets recorded, because you're doing it on every peer's context, right? So, and you have issues like if the peer drops out of the meeting, you basically lose all the context. So I would say it's, I will also go over where you can use this approach, but yeah, that's something to keep in mind. So yeah, let's talk about the good and the bad about this approach. So first of all, it's really easy to build. If you want something fast and easy, you can use this. So it's completely on the client side. There's absolutely no server cost. That's if that's something you want, you can use this. There is no extra bandwidth required for download because it happens completely on the client side. It's already on your browser. And one cool thing, obviously, since you're working on the browser context, you get access to CSS and JS APIs, so you can easily sort of build layouts using those to show things in the recording, and you can use HTML5 canvas, for example, to generate a media stream track. Yeah, and the bad part, I think the first thing I already went over, if the browser sort of crashes, you don't have any recording. One thing I think that was mentioned in one previous talk as well, so the media recorder API basically stores the video chunks on your browser's RAM. So this is bad because as the length of the recording increases, it will take more and more RAM in your browser, so that's not ideal. And also, you have limited transcoding options. So, one of the issues we saw was certain players, like, for example, a QuickTime on Mac, they may not be able to play this video in the right way for all kind of cases. So, yeah. So that's when we sort of tried to mess with this approach a bit. So we tried to move these APIs, but to the server side. So the idea was very simple. You run like virtual Chrome browsers on the cloud, and you basically, you can use any sort of hosting like VM on some a cloud platform like K8 or ECS or Cloud Run. So yeah, you run the browser there, and you join the meeting, and then you use the media recorder API there to basically record the browser. So the benefit is, of course, you sort of move away from all of those client-side issues I talked about, where sort of if the peer drops or drops from the meeting, they will not be basically there won't be one source of truth for the recording. So, but there was one thing we had to handle. So I talked about that screen share prompt that shows up when you record the screen. So we actually had to use a hack to sort of go around that. So Chrome extensions, yeah, so that was the prompt. So Chrome extensions have access to this special API where you can directly access the stream from the tab. So you don't really need to show that prompt, right? And since in this use case, we are running our own browser on the server, we can pre-install this Chrome extension on the browser and use these APIs. So yeah, for example, in this code sample, I sort of use chrome.tabcapture to get the stream of what the tab is showing. And then I can use the same approach to pass this to the media recorder APIs and to record the screen. So yeah, the good part is, of course, from the previous approach, since it's now on the server side, we can sort of handle more things on there. So if the browser, for example, crashes, we could restart it if that's the approach. So yeah, and it's still easy to build. So you didn't really get into the mess about video transcoding because the media recorder API handled all of these things for you. The bad part is this. So Chrome takes a lot of RAM. So by our readings, even to do a 720p recording with the media recorder API, you need at least 4 cores and 8 GB of RAM per recording. So yeah, so if you had like 1,000 recordings running on your service, it would be 4,000 cores, which is a lot. So that's sort of one bad thing. And one thing I think I missed is, yeah, the transcode options are sort of limited. So we'll also talk about how to solve that. So So the second approach we sort of migrated to because it was an easy migration was the idea was simple. We don't use the media recorder API, but we use our own transcoder based on FFmpeg to basically capture the screen of the browser, right? So the main benefit is we sort of get more of these granular arguments we can pass to the encode process, which can help us tweak these small things to make the process faster. One thing we could also do to make the service more reliable is sort of save these what do you call segments of videos while the recording is going on. So, and we could save these in some shared storage. So this was really helpful because if the process did crash, we would still have these segments, and we could sort of re-invoke that recording somewhere else on some other VM, and then sort of re-record segments from that point. In the end, we can just join all of these. So yeah, that was what I just spoke about. So you have an X11 server running Chrome on your VM, and you have a pulse audio, which will capture the audio from the browser. You can use FFmpeg to sort of read these video and audio tracks, and then you can transcode it according to options you pass, and you get segments out. And you can finally join all of these segments to get your final recording file. One thing I should talk about here is how do you scale something like this on the cloud? So spawning a VM on the cloud, and this also matters on what's the sizing of the VM and what you're using. So, but on general, it takes about 40 to 200 seconds. So this is not ideal, of course. So you can't have an approach where you start a recording and then you spawn a VM. So of course, one good thing to do here is to maintain a pool of free machines, and then you sort of make the recording go on those. So that will speed up your process of starting recordings. And at Diet, we had this sort of high-level structure of how we handle this. So we had this master process where you can send a recording task to this worker. So we had a pool of workers always running, and we had a scaler which would scale this up and down based on various data fields. So it would see how many recordings are active, how many meetings are active, so on. Right, and we upload the segments to a bucket. So, and then you can sort of access those segments later and join the recording into a final video file. The good part about this is if you tweak those options on the transcode process well, you can actually get the usage down all the way to 2 cores. So that is, again, for a 720p recording. That's something we could use to reduce our server costs a bit. The bad part is you have to still suffer this extra overhead of running Chrome. So in this whole process, we had to still run a Chrome browser, even though the actual thing we're trying to achieve is just to record video, right? And it's sort of limited to screen capture. If you use the approach I said, you could get around this by sort of transporting the raw tracks to your encoder, which will be the next approach I will talk about. But yeah, it would require extra steps. So yeah, and the third approach, and it's something we built I think a month ago, is to sort of directly process these video packets, all the streams from your a media server. So you can directly process these, and you can use a tool like a GStreamer to basically build your whole media pipeline where you transform these packets and route it to various places. Right? So one thing to note over here is this scales on a per stream basis. So it's not like something per browser anymore. And you could, of course, use this along with the other approaches we spoke about. So you could hook it up to any kind of audio-video source in your whole infra. A small intro about GStreamer for the people who haven't used it here. So it has these bins, which are basically simple sort of building blocks for media pipelines. And you can also build your own bins. So we also built this sort of bin to a mux video on this kind of a grid, so you can have it on the recording. This is an example GStreamer pipeline. So you have your SFU here, which you sort of route the video audio packets from there to your GStreamer pipeline. And you can use bins like RTP bin to sort of parse this packet into multiple RTP sessions, and then you can decode the audio packets from it using the Opus decode payload element. And finally, there's this really handy element called T, where you can sort of branch out this track to whatever you want to do with this audio file. So for example, you could use Audio Mixer to sort of mux all the audio as one file, or you could store it in a file directly, or you could encode it into some other format, right? So yeah, scaling on the cloud here is really similar. So you can have that same master worker approach I spoke about. Of course, now you scale on a per stream basis. So I can route, I don't need to route streams onto the same server. I could route them to more than one server. So you have that new feature. And yeah, for the use case of recording raw tracks, so I talked about that on the second slide. So let's say a client wants separate tracks for each person on the call. You can almost do this at zero cost. So it's basically just taking already a video sent from the browser and just dumping it in a file. So yeah. So yeah, the good part about this approach is you have no overhead of sort of running Chrome. It's really low CPU usage. Recording, as I said, individual tracks is very efficient. And it's really flexible on what you do with this video and audio. So as I said, I could stream it somewhere else. And the main benefit is I just need to read the packets once, and then I can route it anywhere. Of course, you might need to still transcode more than once based on what the client wants. So yeah, and the bad part is to write anything which is not there, as you know, a GStreamer plugin already. You'll have to sort of go into their docs and figure out how to handle this complex video transcode process. Of course, if you have the manpower to do it, you should, because it is the best approach, I would say. But yeah, that's just something to think about if you're looking for a fast POC versus something that requires more effort. Right, so which one do you use? So I would say for any use case where you need to record really short clips on the client side, I would say it's OK to use the Media Stream Recorder API as long as you know about those client-side faults and you're OK with them. If you need any kind of use case where you need to record a browser web page or some sort of grid layout with a complex UI, then I would say the cloud browser approach has some kind of a merit, because CSS and JavaScript do let you create nice to see things. So as opposed to dealing with really low-level APIs, which might take more work. And of course, if it's some kind of browser web page, you have to basically run some kind of a browser. And yeah, if you are recording individual tracks, or if you have really simple sort of grid layouts where you want to show the recording, the best approach would be to use the stream-based recording and to build your own pipeline on top of that. So yeah, that's my talk. Thank you. And if you have any questions, you can.
Any questions? Questions? If not, we can maybe. Yeah, one question.
Thanks for the talk. I think it was very comprehensive. We followed very, very similar path. I wanted to share a trick with you. In approach number 2, one of the reasons why Chrome takes time to start is because it needs to build a profile.
Yep.
So when you build the image or the container, you can run Chrome for 1 second, and then the profile is built, and then it starts up in like 1/10 of the time.
Okay, that's interesting. So, yeah. In our use case, like we sort of would pre-scale these browsers. As I said, so we would have like a pre-built pool of sort of Chrome browsers. So we didn't really need to think about the startup time of Chrome. So it would be an already loaded Chrome browser, and we just pass it this meeting to join. So yeah, but that's really interesting. For sure, it would speed up our startup times.
Yeah, thank you for the talk. I wanted to ask, because you mentioned GStreamer and FFmpeg, did you make a comparison in terms of utility, in terms of memory usage, or did you just choose it because of familiarity?
So in terms of CPU and memory usage, I would say it's similar. FFmpeg is slightly better. But the thing is, GStreamer gives much better, I think, APIs for you to build pipelines. So FFmpeg is slightly more complex to use, I would say. So in terms of the dev experience, I would say GStreamer is a better sort of library. But if you really care about that small amount of CPU usage that you save, FFmpeg might hold some merit, you know. So.
Okay, thank you very much. It was a very interesting talk. The next speaker, it's Javi, who will be talking about CDN logs. All right? Yes. Okay, go ahead.
Nice presentation. Okay. Okay, so finally I'm finished the setup. Now we're ready to go. Today we are going to talk about CDN logs. I just name it like this because there are a lot of lies in the industry and it's always regarding video. But yeah, mainly it will be about logs, but we will make it a bit fun. For those who don't know me, I've been for a while in the broadcasting and especially in the video streaming industry. I teach at the Pompeu Fabra University. I'm one of the organizers of the Barcelona Videotech meetup. So if you ever come to Barcelona, you are more than invited. And if you want to give a talk there, just send me by email. I support the best football club in the world, which is Football Club Barcelona. And I love music. I have a huge collection of vinyls and also another collection of old retro video games. As I said, I collaborate a lot with the community, and this is something I encourage all of you to do, to give talks in meetups and in local communities, because it's something that it's really rewarding and it's really good for us that we all share the knowledge and build good things. So we'll start with, just for those who don't know, what's a CDN? Somebody in the audience? Oh, very shy people. Okay, it's the content delivery networks. It's basically a network you build where you have a main server. This is very used in video on demand mostly, but can it be also in peer-to-peer connections, but normally it's more with video on demand, some live sport which are not live, or that kind of. You have some servers that cache the content or the video chunks, and then they send it to the other servers. So with this network, you save costs and you get better efficiency. So let's start with some common issues or industry known secrets. The difference between the low viewers and a big concurrency. So the CDN is designed to serve a huge audience and to serve the video massively. So it's quite common that you have more errors when you have low viewers, maybe during the night or something that some content that nobody is watching it. I mean, if you have low viewers, it makes sense that you have some small errors. I mean, that's inside the CDN theory. Oh, this was a video, but it's not playing. Well, but basically I was saying that as the designers as the network is designed with servers with time to live, with the caching information, if you have more concurrent viewers or more users you have, there are more cache servers and the information flows better. So makes sense when they are like during the night, like 2 a.m., like these hours that nobody is awake and watching TV or watching your content, makes sense to have more errors. Regarding with this, the hourly daytime pattern issue, sometimes we see a lot of startup errors, exit before video start errors, just at concrete hour or daytime. Even sometimes same day of the week. So what does that mean? That the problem is on you full. When this happens, is that you are not scaling correctly. So if you face that, don't look for other place because the problem is on you. You need to revisit your architecture, think how you design everything, because if there's this kind of pattern, this pattern is when you have the most audience, and that means that you cannot serve them correctly. Sometimes bad design or poor infrastructure, but as I said, this is quite common, especially in small companies or people that aren't so much used to deliver huge video at scale. Unless one exception, the 4 a.m., the darkest hour. So what happens at 4 a.m.? Well, it's a convention. I mean, it's not a strict rule, but there's a convention in data centers, NOC, POPs, anywhere where there are physical servers, and especially if we talk about cloud, because the cloud is somebody else's computer. At 4 a.m., it's a classical window for maintenance. What means maintenance? Connecting, disconnecting, rebooting, switching things, changing networks. So at 4 a.m. or near that hour, you can see some weird things in your logs. This was a real-life example that just at 4 a.m. there was a peak and one certain part of the content was delivered not correctly. Plus, don't forget that 4 a.m. it's also, you can have the low viewer thing. So it can be a deadly combination sometimes. So you just need to be aware. And I have an anecdote with this. Is the first time I did this talk, after the talk, we were having beers and one sales guy from a big CDN supplier in the world, top 5, with the beer, he came like, Javi, you were right. We ran some backups at the first Monday of the month at 4 a.m. and it breaks everything. Like, we don't know why. So yeah, this is true. And especially in the local time zone, remember, like this is not if you are the user at 4 a.m. No, like where the server is at that country at that daytime, 4 a.m. can happen strange things. More tips, the distance matters. We always, one of the lies in this industry is about connectivity. Everybody says, yeah, everything is so fast, we have 5G, we have... Distance still matters. And this is especially important when you run a CDN. Because you are delivering content, and sometimes the countries are different. The server, they are in different countries. Origin is another one. So all that things they introduce you some delays in the signal that can end up in buffering errors. And what mean buffering errors? Stall video errors. One of the truths of the industry: don't trust never your ISPs. The internet services providers. Raise your hand if you struggle sometime with an ISP. They always lie. So normally they don't fail, but the day they fail, it's really tricky. You have everything perfectly settled. You did a really huge work. You are monitoring everything. And then you find strange issues that you really don't know what's happening, and at a certain point you have the guessing that it's on the ISP. And you reach them, and they follow normally a kind of helping protocols, like if you are switching your your router at home and they say like, okay, have you tried to reboot? They will start doing like a lot of battery questions, and then they will reach you to a higher level, and until they fix it, it will be really bad. So their first answer is always that they are not wrong, but if you are really pretty sure, they are always lying. So mail them as fast as possible, because it's also a problem with ISPs. Normally they are big telcos, they don't solve things fast. So if you have the guessing of them, mail them directly. Don't lose any time. Now let's go into how I recommend my approach, but I think this is more like in the industry, like how the things should be in an ideal world. So I've called the 10 CDN commandments in a homage to Notorious B.I.G., rest in peace, Christopher Wallace. The first of all, always be redundancy. Because if you have good alarms, you are monitoring the CDN, so what comes next if something gets wrong? The solution. So most important, and I think some of the tips I'm going to give, they go even beyond CDNs and are more into the IT world where you have a lot of servers. So you need always to be redundant, because if you see some place where something is wrong, you just can switch quickly and fix in the meantime. The second, multi-CDN configuration. Don't put all your eggs in the same tortilla. So it can be slightly a bit more costly, but if you have several CDN providers, or even if you have your own CDN, you can ask another providers to serve part of your traffic too. Why? Because as I was explaining, if there's some error with one of them, you just can change the load balancing, and you take that CDN out of the mix, and you keep delivering with the other two. Maybe it's not the most optimistical solution, because those other two, they don't serve pretty well to certain regions or certain devices or whatever, but at least in terms of business, you are still delivering the video to your users. Because the final users, they don't understand when they click or they put play and it's not working. They don't understand that. So we need to avoid that. Another thing is we always think about setting good alarms. But what is a good alarm? So there's a bad practice, and I'm one that I've been doing it bad in the past. That is to put all the alarms at the same level, like you send, for example, some emails, and sometimes they are just known alarms, or sometimes it's just information and it's not an alarm. Like, I won't take attention. So this is a mistake, and we never do it correctly. So I come with two solutions which might sound obvious, but we always tend to forget, so I'm just reminding. First, establish alarm levels. What is information? What is the bug? What is warning? What is error? And the second is the error, you need to notify it in a different channel. It can be whatever you want, email, Slack, phone messages, like, it doesn't matter that. The important thing is that the error should be notified completely different to the rest of notifications. So that's when they will get all your good attention to it. But as I said, we all have these bad practices in the industry, and I know sometimes it's even difficult to change because there's always some old thing running that nobody can stop, and it's sending you information emails, or every time you reboot, yeah, I know this error. But the good practice and the recommendation is to configure your alarms properly. It will help you a lot. So another thing, test everything, even production environment. So obviously, and as I said, there are some tips here that go beyond CDNs, but especially with CDN, you need to have everything properly settled. So everything ending with the word test, unit test, smoke test, stress test, run integration test, like anything you can imagine. If you have it, run it before the deploys. And there's other thing that I've seen a lot in the industry, that nobody tests the production environment, is that you have that environment already there, so you just deploy there, but you never try to test it, or even to have the possibility of redundancy, to switch off production and go into other place, so you can test it in that production environment. I don't know. I think that we are very lazy in the industry, so when production runs well, okay, just merge the pull request and run it. But sometimes we should even test the production environment. And obviously, the Big Bang Bunny, your interns should start using it, and if they are not, you are late, like putting the video to them to start generating the big trauma in the industry. So those were the first 5. Now we'll go on with 5 more. First one, synthetic monitoring, real user monitoring, or both? A lot of people ask me this question. I've been being user of real user monitoring. I've been working in a synthetic monitoring company. My real answer is that it depends on the budget. How much do you have and how much do you want to spend? Like, obviously, if you are like a big player in the industry, you work with a lot of CDNs, like the big ones, normally they do both. In case you have to choose one, I will go rather for the real user monitoring. Why? Because for those who don't know, synthetic monitoring is when you try to emulate the calls to the video files or the chunks, and you get an HTTP response and you can analyze it. Like not even sometimes downloading fully the chunks or just downloading a small part. Like that's why it's called synthetic monitoring. And the real user monitoring are the companies that have this kind of plugin, or you can do it by yourself, that you develop a plugin that you put in the browser, so you get the info from the final user of your service. If I have to choose one, that's why I would go with the real user monitoring. Why? Because not only to make happy the marketing teams and all people that want to have all the insights from the user profile, just because it's the point where the video is finally delivered. So if you don't have budget for both, you will get maybe more interesting information in the real user monitoring. Even sometimes you will miss some good information on the CDN. If I have to choose only one, I would go with real user monitoring. If you have good budget, or maybe you are you serve the technology and you have clients who pay for that, then just put both, so you will sleep. You will sleep better. And now I'm making like a small break inside the CDN commandments. So this is one of the insights of what I've seen inside the industry when I was working, especially in a big video-on-demand company. Most of the errors come in the CDN, because there's always packages missing at certain point, somewhere, you don't know why. Theoretically, it's 1 and 0s, you don't know where it's losing the information, but this happens. So I would say, in my opinion, that 95% of the errors are generated in the CDN. I mean, with this, I mean, like, where's the origin of the error? Because these kind of errors, maybe you will find them in the final user having a 400, a startup error, but that comes because at a certain point of the signal, the packages were wrong. Then I would say there are a bit more of errors, normally on the encoding or packaging stage, especially because these ones sometimes are false positives, that you have glitches, that you break some video headers, but when you try to monitor, you don't see any error, you deliver, and finally the player gets broke. But in this case, you deliver perfectly the signal. It's just that something happened at some stage that you weren't able to detect, unless you do this kind of video quality assessment or this kind of stuff. And then, in rare occasions, we have the ISP problems, your own problems because you have deployed badly a new player or whatever. But I would say more or less the percentages of the origin of errors in this industry normally are like this. And a second small thing I want to mention, which is really interesting, is the CMCD, the Common Media Client Data. It's a new protocol. It's a standard. It's open source. It was developed by Akamai in collaboration in the CTA Wave. It's kind of secret of the industry. I don't know why, but all the big players, big broadcasters worldwide, they are starting to implement it. So basically, it's that at each time the chunks pass through the servers, they are adding like more text into the same URL, but with this you get information. And this is interesting, and the reason I bring it here because probably future versions will let you to start adding some cool information that you can get on the player, and you can have your own real user monitoring really cheap and really efficient, and even get insights from some parts of the CDN which normally people didn't used to know. Let's get back. As I said, when there are mistakes, if you have the multi-CDN configuration, really easy. You just take out of the mix, you keep delivering the video. As I said, sometimes we are engineers, we don't know the business part, but business part is important because that's where we get our salary. So we need to have our final users happy. And when you are starting to stop, I said, okay, where was the problem? Not only with monitoring tools, but the best information you can get, it's in the headers. This is simple HTTP, it's something really basic, and information was always there. It's just sometimes that we don't know how to interpret or how to understand, but information was always there. So if you look at them consciously when you are having some kind of errors, you can get some really interesting insights. And now that you have detected what's the error, really easy. While you are still delivering your video to your users, you fix while nobody notices, and you just do the deploy, then you start to add again the problematic CDN. Now it's a working CDN, you put into the mix, and now you save the world, so enjoy your beer. So to end the presentation, sorry because I'm a bit late, I'm going to try to be quick. I have two real-life use cases where these were big companies, they also had big budgets, so they had good practices, and they did more or less the same the same 10 commandments, more or less. This case, I don't have the rights to mention. Watch a sport event is just something people do with helmets in the US, and they put a lot of commercial breaks, and they have a 4.1 concurrent million viewers online on streaming. So what happened? Just 3 hours before the game starts, the big broadcaster, which was going to have the 4.1 million concurrent viewers, found some errors serving the US West Coast. That means New York, Miami, like not small cities precisely. So they started to check the error, like what was happening. They had everything redundant, and really cool, interesting switching way of that. It's a pity I don't have the rights to tell that, but they had something really cool. So for them it was really easy. Just switch it, and nobody knew. I think in this case that it was a record this year when this happened of concurrent viewers even. So nobody knew anything about this, just the ones that we were behind. And the second one, it's a live video platform, Peacock, really big one in United States too. I bring this because they were really serious with everything and testing everything, and even production environment. And this is when they found, because they had everything perfectly settled after all the testings, except production environment. And the thing was a small problem about connectivity between CDN providers. So they fixed everything, and when they did the launch, you see all green. Like everything was perfectly, it was a new platform, and it worked pretty well. So if you have good data, you can go deeper, as I said, and if you test everything, you can live better. As I said, what were in common in these two use cases? They had the synthetic monitoring and real user monitoring. They had redundancy plus multi-CDN well-configured alarms, test everything, take first problematic CDN out of the mix, keep delivering video, and fix while meanwhile nobody notices. Conclusion of this industry, everybody lies. Like, don't trust anybody, just yourself, your logs, and that will be the real truth. Or even sometimes your own developers, like, yeah, I did the pull request, I've checked there's no book, I've run the test. Like, everybody lies, so just to be aware of everything, try to have everything, all your alarms were well settled, check all the production, test everything, and that's it. And the classical slide, but I'm giving it a twist, because rather than hiring, I'm open to opportunities. So if you hear about anything, just tell me later. Thank you all.
Wait, yeah, oh, okay. Thank you, Javi, for your presentation. Any questions, maybe? Yeah?
So I have a question regarding the challenges with the CDN. So basing on your experience, is it more challenging to have a lot of small content or one super big event? What is easier, in your opinion, to scale, for example, or prepare for? So let's make an example. We have an application that has a lot of videos, and well, you cannot really say which one will be often viewed. And we have some other products. So we have some big live streaming company, and they have, well, basically just one match today, and I don't know, 10 million people will watch it. So what would you say? What is easier to prepare for?
I think, well, if we think just mathematically, obviously it's the big one, because you just need to test everything, have everything switched, everything redundant, test everything. But even that, like I was in a meetup remotely for Montevideo, and one guy he talked about how they were doing live streaming of the Qatar World Cup. And they had a problem like 30 minutes before the match starting, everything went black. They had an internal problem. And so if you think of that, it's obviously, if you have everything really, really well configured, you can scale. As one friend used to say, you can scale as large as Amazon Web Services is. Like, someday that will be finite too. If you have a small content, I mean, theoretically, that shouldn't be so problematic, just because, I mean, when you have the CDN, you are always catching. So I think the challenge here is about how much are we scaling or not. But as I said, if you have like one live sport that, I mean, obviously you have to put a lot of effort in both. But I guess the difficult part here is the infrastructure and the design of the architecture. If you have that good, you can do whatever you want. And as I said, as long as AWS can scale, you can do whatever you want. But obviously, if you are just spending on one thing, it can be easier because you have all eyes put on that. But even that, as I said, for fellow colleagues in the industry, shit happens. So.
Thank you.
Thank you. Any other questions? Yeah, there's one. Another one?
Okay. So firstly, thank you for your presentation. Very cool material. And I wanted to ask you about testing, because you mentioned that it's very important to test our CDNs. But how would you approach testing CDN when you are using an external provider?
you can run this kind of fake calls, like you can create your own stress testing, like putting some instances, making all the instances to call simultaneously to the same stream, check if they are broken or not. Like you can do this kind of own stress testing for the CDN. And obviously what you cannot, unless it's your own CDN, it's like the tires, like the origin, the middle tire, because sometimes you don't even know. So the best approach might be to do this kind of final user testing with fake users, like just getting something that scales a lot, and you do this kind of fake calls to the stream. And well, that's how I've seen that people try to do it. And also, if you have like virtual machines, that can also help because you can test several regions, and with the same approach. Like, I would say that for testing CDN performance of providers, I would go with stress testing.
Okay, thank you.
Okay, thank you very much. I would like to invite the next speaker, my colleague Łukasz, who will be talking about membrane and the basics. Yeah, go ahead.
Hello everybody, welcome to my today's talk. My name is Łukasz and I work at Software Mention, and for the last almost 2 years I've been working on development of membrane multimedia processing framework. And today I would like to share some of my experience with you. Okay, so just to start with a brief agenda of my today's presentation. First, we will try to answer the question what pipeline is. Then, and especially, we will try to focus on the usage of pipelines in multimedia processing. Then we will answer the question what membrane is. And I will try to somehow leave this with a live demonstration. And then I will talk about how we solve some problems with pipelines in membrane. Okay, so let's get started. So generally, what are we going to talk today? We will be talking about pipelines. What are pipelines? Actually, this is a pipeline. Here is a pipeline. Here used to be a pipeline. And some. But we want to discuss pipelines in context of computing. So I have found some nice definition, and I would like to quote it. But the pipeline consists of a chain of processing elements that can be like processes, threads, coroutines, functions, arranged so that the output of each element is the input to the next. And as you can see on this picture here, we have some kind of data source that reads the data from some kind of outside world, then a couple of processing elements, and finally some kind of data sink that is capable of writing this data to the outer world. And pipelines are all about data processing. And these abstract concepts of a pipe, which is like between particular elements of a pipeline, is a representation of this interface that you are putting the output of one element as an input to the other. Okay, so in case you are not encouraged that pipelines are cool, I would like to highlight some cool features of pipelines. So apart that they deliver gas, they also encourage composability. And we can see that we might have like a couple of small components that are linked together. And the cool feature of a pipeline is that first, we can link these elements like seamlessly because no adapters are needed because the pipeline's interface already defines that they can be connected together. And another cool feature is that such a big component can be treated as in the same manner as some small components. So the user of such a big component only needs to know how does this big component transform the input and what is put on output. On the other hand, pipelines also encourage decomposition. So you might have some complicated stuff and split them into several independent steps. And in case you're familiar with like a design of concurrent algorithms, you probably know that the very first step of designing such an algorithm is to perform a partitioning of this problem. You can do it either in a domain way or in a functional way. And pipelines are a way to actually perform this functional decomposition. No wonder pipelines are used in multimedia. Here are some examples like GStreamers, Microsoft Media Foundation, and before mentioned Membrane. So just to give you like a view on how such a pipeline can work, here is like a very basic, however commonly used example from GStreamer. So we have like a kind of file source that reads data from file system. Then this data is put to a demaxer that separates two tracks, audio track and video track. And both these tracks are then put to appropriate decoders. And once we have decoded data, we can play it with an appropriate player, like audio sync player or video sync player. OK, when it comes to Microsoft Media Foundation, let's just skip it. Actually, I have put this picture here because when I was searching for some kind of information about it, to give you like a nice example, I think the third result in Google that has appeared was an eBay action that sells this Media Cream Foundation. So I've just put it here. So we won't go deeper into it. However, we will look under, now I would like you to wave hello to Membrane. So how many of you have heard about Membrane like before this presentation? Yes, I can see my clip. OK, great. So what Membrane is? Membrane is an open source multimedia processing framework. It's written in Elixir and run on Erlang's virtual machine, which is called Beam. And it consists of two main parts. The first part is Membrane Core, which somehow delivers tool to create your own processing elements, as well as to connect these elements and force some kind of pipelines. When it comes to the second part, it's called plugins. And these are like these are some kind of processing elements that can be used by the user of a framework. So what plugins do we have? We have a couple of them. You can see here that there is a bunch of plugins. To summarize, I have prepared this slide. So we support multiple network protocols. You can read them names if you want. I don't feel like doing so. We also support multiple both audio and video codecs. So we deliver encoders and decoders of these codecs. We also support different multimedia container formats. We also allow for some multimedia manipulation, both for audio tracks and video tracks, as well as we deliver some common functionalities that are more like media agnostic. So we can have like a real timer that turns the offline processing into online processing, file source, and the T and the funnel. What is T and the funnel? Well, actually, this is T, and this is funnel. And I think that based on the shape of these elements, you can guess what kind of processing happens with the stream that is put into them. Or at least I hope so. So now let's look under the Membrane's hood. You need to know that since Membrane is written in Elixir and run on Erlang's virtual machine, is somehow dipped into the actors model. And actors model of processing is a concurrency model of concurrency, actually. And it relies on like some fundamental rules. So the first rule is that there are like multiple actors that are running concurrently, as you can see on this picture. For each of these actors, there are some events that are happening. And when we consider events that happen for a particular actor, we can determine their order. That's not necessarily true when it comes to events that happen among different actors. Another thing is that actors can also determine their behavior as a way to react for event. And also actors can send messages to each other, so they can communicate as well as an actor is allowed to spawn another actors. So how can we use this concurrency model to model media processing? Well, this is how. This is like the very basic scheme of an element's lifecycle. So first, after some initialization of this element, we enter such a loop. First, we wait for some data to be received. Then we process this data. Then we send this data to some other element, for instance, and we update our behavior. So what the user is actually interested in doing is this processing part. And this is why in Membrane, we allow user to define his or her own processing method. It's done with the use of callbacks. So this is like the code snippet with an exemplary callback implementation. And this function will be called each time a new data arrives for some element. Some important things to note here is that this is like a pure function, or at least it's good when it's a pure function, because it simplifies the debugging. And when we want to have some side effects, like communication, we only declare our will to do so. So as you can see, as a part of return value, we declare that we want to communicate with the other element and send the data further. Once we have a couple of such processing elements, we can connect them together. And here is a code snippet that shows how the elements can be connected. Like an important thing to notice here is this pipe operator, which is actually something that builds our pipeline. And this is what happens under the hood when we extend these life cycles, or at least a couple of these cycles. We can see that, for instance, we have the first element, the data is delivered to this element, processed, and sent further. And this is how basically pipeline works. OK, so let's continue with a live demo. I have prepared actually 2 pipelines. And we will be sending data with the use of RTMP. So we're going to have an RTMP sender and RTMP receiver. OK, so this is how our first pipeline looks like. This is the sender. So we basically fetch some encoded video and audio representation with the use of HTTP source. Then we fetch some interesting information, for instance, sample rate for audio track or resolution for video track. Then we turn the processing into online one with the use of real-timer. And then we use RTMP sync to send it via network. And here is the other side of our system. So here we read the data from network with the use of RTMP source. Then, since this data is already muxed into a container, we demux it. We have 2 separate tracks. We add this additional information like resolution and sample rate for the appropriate tracks, and we play it with a player. OK, so now I will make an attempt to run it. Actually, what happens here is basically definition of this pipeline. And here is the structure of a pipeline. So this is basically something that reflects the structure I have discovered. I have discussed previously. Here is just a way to listen at a particular port. So we're just gonna skip it and run our sender. And when it comes to the receiver, we can see that in our player, which is visible on in this lives book, something starts playing. OK? Yeah? I think you might be familiar with this track. OK. So let's continue with the presentation. I hope it will start displaying here. OK, here we are. OK, so let's go to the Pimp My Pipeline section. And I will try to show you how we solve some problems with pipelines in Membrane. So as you can see, pipelines might be complicated. This is a complicated pipeline, and I won't point with a finger which products that is based on membrane actually has such an internal structure. However, it has already been discussed today. But let's go further. So let's design a very simple processing pipeline. So as we can see, we have 11 processing filters. Let's also set some time constraints so that we can reason about this processing. And let's assume that each filter processes a particular buffer with data within 200 milliseconds. And in order to be able to tell whether the processing happens at a satisfactory pace, we need to define some kind of metrics. And I would like to propose two of them. The first is throughput, which is a number of buffers that are processed by a pipeline in a given time. And the other one has a long name, however, I think it reflects what it is, which is the average time spent by buffer in a pipeline, so the time that has elapsed between the buffer was sent by a source and received by a sink. So here is how the value of the throughput metric changes overall the runtime of pipeline. And we can see that after some initial warm-up, it converges to a very particular value of 5 buffers per second. Why 5 buffers per second, you might ask? Well, you cannot actually exceed the throughput of the slowest element of the pipeline. And in our case, each element is processing 1 buffer per 200 milliseconds, which adds up to 5 buffers per second. So this is why we stabilize at this value. And here is the other metric, average time spent by buffer in pipeline. And it's also not surprising that this value will be something around 2,200 milliseconds, because all the time spent by buffer in the pipeline was spent on processing it, and we had 11 elements that were processing 200 milliseconds each. So this is the result. However, it was a perfect situation. All the processing was perfectly synchronized, and it doesn't happen in real life. In real life, we almost always have this one lazy element that is processing much slower than the others. So here is a visualization of this problem. We can see that the last filter, the 11th filter, is now processing a buffer within 500 milliseconds. And what consequences does it have? Basically, when it comes to throughput, we can expect that it will decrease, and now it stabilizes at around 2 buffers per second. But that's also something we can expect, because now the slowest element processes 2 buffers per second, so we cannot exceed this limit. However, when it comes to average time spent by buffer, we can see some unwanted tendency, because this value doesn't seem to converge at any point. It simply steadily increases. And it might, well, of course, this is connected because now the buffers with data are waiting before the slowest element. And the longer the pipeline runs, the more buffers will be in that queue. So that's because this value increases. However, it might have some other consequences, like increase in memory usage, because of course this queue also is somewhere in the memory. So when we need to have the bigger queue, we end up with a greater memory usage. So how can we solve this problem? Well, we can solve it. Oh, I thought that it will be visible better. However, I can tell you that we can solve it with a back pressure mechanism. So what is a back pressure mechanism? We need to now change. We now need to prevent buffers from sending, prevent the filters, of course, from sending buffers until they are explicitly told to do so. And this way to tell a filter to send buffer is sending a kind of a message. In membrane, we called it a demand, and this is represented here with this blue arrow, which is traveling through the pipeline. So as you can see, at first, things want a buffer from the last filter, so it sends this demand message to this filter. The filter does not have this buffer, so it propagates it up until source. And then source sends the first buffer, which travels the whole pipeline. So it has solved our problem. Now the average time spent by buffer is stabilized. Also, it means that our memory usage is no longer increasing. However, another problem appears here, which is the problem with the throughput. Because, as you could see on this illustration, the elements now are working more like synchronously. At first, things sends a demand message to the source, and then one buffer is sent from source to the sink. So this is not what we want to have, because we do not leverage the fact that we have like concurrent elements that are running. So here's what happens with our throughput. We no longer have the throughput of value like 2 buffers per second, but now it's reduced to not even half a buffer per second. So how can we solve this problem? We can introduce so-called input queue. And here is the illustration of an input queue. So before each element, each processing element, each filter, we want to have a queue, and we want that queue to be of a particular size. So for instance, initially we send some demands so that to fill that queue, and once its size is smaller than the desired one, we also send the demand messages in advance. And here is how does it make our throughput increase. So you can see here like 2 lines. One is orange line and one is a green line. And they describe different queue sizes. And of course, in this very particular case, the pace at which the throughput converges to the desired value is almost the same for both these queue sizes. However, when we take under consideration the average time spent by a buffer in a pipeline, we can see that for a bigger input queue, it's bigger because there are more like places in the queues where the particular buffer needs to wait. So in this particular example, we would, of course, choose the queue of size 1. However, for your case, you always need to somehow adjust this value of a queue to have the expected result. Okay, however, we remain silent about the fact that sometimes it's not possible for some elements to slow down. I mean, for instance, you might have a live streaming case, and in such a case, you cannot simply tell this data source to send buffers with data only when it's demanded, because it's live stream, yeah? So what can happen in such a case, and how can we deal with it? Well, there's not much that we can do with such a problem. And here is the illustration of this problem, by the way. So this is like our live streaming element, which is, yeah, it is speed. And the solution here will be to simply deal with it and turn the back pressure mechanism off, because it makes no sense to send these demands. So in Membrane, we have such a mechanism that when all the sources are in push mode, so the ones that we cannot stop, we simply turn off the back pressure mechanism. However, once a source that is capable of receiving these demand messages appears at the beginning of the pipeline, we turn it on. So this is basically what happens under the hood. Okay, so that's actually almost all I wanted to say today. So if you want to learn more about Membrane, I invite you to our website and our GitHub organization. And like the very last thing I wanted to do was to introduce to you a new version of Membrane Core, because you can probably guess that having like a stable API which allows you to create your own processing elements is something we actually want. And it wasn't possible until now, because I would like to do it right now here. So yeah, we'll all participate in the release of the Membrane Core version 1.0 with a first time with a stable API. So let me publish it. Oh, I have already like dry drummed it, so almost. Okay, and here I have like this big button I'm gonna use. Okay, so I think we are ready. Are we? Let's go. Oh, come on. Come on. Wait for it. Yeah.
Okay. Thank you, Łukasz. That was great publishing. Any questions? Yeah?
Thank you for your presentation. I'm really excited about Membrane because I hopefully will be able to use it at work. So it's a big thing for me. I wanted to ask you, because you talked about the slow elements. How, if I compose a pipeline, how would you approach in debugging which is the slowest part of the whole pipeline that might be the bottleneck?
Actually, lately we have delivered a kind of tool for Membrane. It's called like Kino Membrane, I believe, because it's a kind of a dashboard that allows you to see some kind of plots that display, for instance, the number of buffers that are produced in given time by a particular element. So of course you would need to consider the fact that like it does not only always mean that when there is like a slower number of buffers processed, that it's something which is unwanted. However, it might be like the clue, like the very first step to find out what's going on there. And you can do it in like real time, so you can always also apply some changes and see how it reflects.
Any other questions? Yeah.
Hi. So, kind of like GStreamer, but in Elixir and stuff like that. Okay. I have one question. So, I've got a use case that I want to run with you later because it's complicated.
Sure.
But first question, really easy. Does it do things like seeking and transport control, things like that? So if you have like file sources or things that will, as you said, can generate buffers really fast, and then you have the min flight, and then you want to do something like seeking while you're playing and things like that. Is that handled as well? So it's kind of synchronous. That's why
yes, actually, you can send some events throughout the pipeline, and they are not like explicitly. They do not need to be joined with some buffers flowing there. So you can, for instance, send some SIG event. We do it with, for instance, a file source when we want to read the MP4 file.
Right.
And we want to skip the MDAT part when it's not like the fast start MP4. So it is possible to do so. And you need to more like, because this membrane gives you an opportunity like to create your own elements also. So in case you need to perform such a seeking, for instance, you can write your element in that way.
Right. So what I'm thinking, like, let's say you have 20 files, and they might read at different speeds even, let's say.
Mm-hmm.
And I want to seek while it's playing.
While it is?
Yes, while it is streaming. I want to change the position of where I'm reading from. So I decide, like, I'm at second 10, and I want to jump back to second 2.
Actually, I don't think we have like the particular element that is capable of doing so, but it should be possible to do it with the framework.
Right, but the buffers already in the queues?
Yeah, but we do not need to like read all of the buffers to the queue, and actually, once we read it and one is like already in the you mean you're like concerned about the fact that it might be already somewhere in the input queue of the element?
So will it be aligned again when I seek?
Oh, actually, it won't be, and that is why, for instance, with the case I have mentioned of this MP4 demaxer, because that's where we use this seeking, you need to handle it appropriately in the MP4.
Gotcha. Thank you.
Thank you.
Okay. Any last question before the lunch break? Everyone wants to have lunch. Yeah, so thank you, Łukasz, very much. If you have any more questions about membrane, well, if you have any questions about membrane, you can not only ask Łukasz, but there are a couple of people here from Software Mansion that are or have been working on it. So most of them will have yellow badges, I think. So yeah, just ask us. Not me. I just can't point you to the right person. So yeah. So thank you for watching. The lunch break. The lunch is downstairs in the hotel restaurant. So I think if you go just one floor down, you will see it. And we will reconvene in about 1 hour and 7 minutes. Is that right? Okay. Thank you very much.
1, 2, 1, 2.
Yeah. I think it's okay.
Nice.
Yeah,
Thanks a
thank
lot.
you, Thank you.
One, two, 1, 2, 1, 2.
front row, Rob. Oh, it's already on.
Yes. Okay. Hello, everyone. My name is Bartek. I'm part of the membrane team, so hence the shirt. And I'll be hosting for the rest of the conference. And hope you all enjoyed the lunch. And it's time to start with another presentation. Our next speaker is Jonny Berger, who's going to take us to the world of JavaScript and show us how to generate video with React. Jonny, you can start.
Hello, everyone. Thanks a lot for giving me the opportunity to talk to you, even though, as you can see, I am a JavaScript developer, and therefore not the highest of powers are available to me. This is probably not the best language to crunch pixels and do everything super efficient. But JavaScript is still very important for two reasons. The first one is there are many of us, big community of developers, and they also want a piece of the video pie. And the second part is the web. An empty index.html file is a canvas where you can draw almost anything. We have vector graphics, you can render text, and it's all so easy, relatively. I am one of those people who at one point realized, actually it's easier for me to draw on the web using CSS than it is for me to use a program like Photoshop or After Effects. And yeah, so we can also animate on the web. Now the question is, what is the easiest way to turn this into a video? The easiest way that I could think of is, we open up a cool JavaScript animation and think Command, Shift, 5, and we start screen recording. And in the end, we have generated a video. Let's talk about what is good and bad about this. The good thing is, we have generated the video, so this is completely viable. Many people do this and post their videos, I believe. The bad thing is the video resolution is limited to the resolution of your display. So I noticed this projector is like 960 pixels high, so we can almost create a full HD video, but not quite. So that's for sure one restriction of this approach. Then how would we automate this? How could we programmatically screen record to browser. That's for sure another thing to ponder about. And also, what if we drop a frame? What if we have expensive graphics and they take longer to render than 33.33 milliseconds in the case of us wanting to create a 30 FPS video? So based on these questions, how could we do it a bit better? Who knows this legendary FFmpeg command? So I think it's been used billions of times. It takes a series of images and converts them to a video. And to generate these images, it's also relatively easy. We can take screenshots with Puppeteer, right? So this is the concept that I've taken and taken to a certain point. This is my framework Remotion, and now we are entering the React phase. In here, we have a React component, and at the top, we always use a hook, use current frame. That is a time value. And so let's say we take control of the time and pause the video, and for whichever time we are currently at, it is now our responsibility to render an image. It can be any DOM content. Here, as you will see shortly, I've just rendered the RTC.On logo. And using this simple math function, we can interpolate the time. Here, I have said that in the first 10 frames, the image should scale from 0 to 1, and then at the end, it should scale down again. Now, I have made a preview editor for this. And we have a timeline where we can scrub through, but also we can play and pause the video, and we can increase and decrease the speed. Because we have taken control of the time, because we have used this hook, this would not be possible with normal CSS animations. Yes. And that is the whole concept of Remotion, the library that I maintain. And of course, just this is pretty hard to do, so we also develop a whole ecosystem of packages. So whether it's about how to synchronize a GIF or a 3JS animation with this use current frame hook, we ship many packages for that. And based with this primitive, which is essentially just screenshotting frames and then encoding them using FFmpeg, we can create videos. The easiest way to render is using this render button. We have a variety of options here. Essentially just a wrapper around FFmpeg flags. And we can render this into a video and play it back. There are also other ways to render using the CLI, using a Node.js API, in the cloud, and Docker using Lambda functions, which I'm going to demo later. So yeah, now that I've explained what Remotion is, I mean, for you, this is baby steps, right? Many of you are solving much more difficult problems. And I've thought about what could I talk about that could be of interest for you. And I've decided to just briefly mention 2 areas of work that I am doing, where I go deeper into the video creation pipeline, explain a bit what I did there, and then if you are more interested in it, then we can talk about it later. One big challenge is embedding videos into our video. So we have an existing video, we could use a video tag and maybe add some overlays. That would be a use case for it. And how we solved it initially is just using the regular HTML5 video tag and then making a component which synchronizes the video tag's frame with our hook. And this worked well. It also worked well for 2 videos. It worked kind of well for 4 videos. But then there are always the people, they want to render 16 videos or 32 videos at the same time. At some point, Google Chrome just says, no, stop, I will not render any more video tags. And a significant amount of people wanted to do that, so that pushed us to research how could we do this better. We created another component called off-thread video, and what it would do is, in the preview, it would still use the video tag because there's nothing better we can do, I think. But while you are rendering the video, we are actually rendering an image. That image has a source which calls a server of ours, and that server then uses FFmpeg to extract the video frames. And that worked. Now you could actually render a video with 32 other images in it, but from a performance perspective, it was not so good. Because if we use the FFmpeg CLI, we extract one frame at a time, and the user could also play the video in reverse. We don't know what the next frame is going to be. So we would extract one frame at a time, then the CLI would quit, the stream gets closed, and for the next frame, we have to do the same thing again. And many frames in videos are just interpolations of the previous frame, so we also have to do all of this work again. So this meant that using the FFmpeg CLI was also not good enough for us. And so I've dug deeper and started using C, or just the FFmpeg C API in Rust, but nonetheless, I'm proud of it. And what I have built is a Rust program which uses the FFmpeg C API to open a video, extract frames whenever it is needed, can also already take the next frame based on, most likely it's going to be the actual next frame in the video, and then does some in-memory caching, which is also tricky because although a video file is small, once you extract the bitmap from it in a full HD video, it's 8 megabytes. So you really have to manage the memory well, otherwise people have to buy a lot of RAM sticks. And yeah, that is now available in Remotion. I think the coolest thing about it is that we have managed to cross-compile this for 7 platforms, all major operating systems, for both x86 and ARM, and kept the option to use the FFmpeg CLI alive. So the FFmpeg libraries are one thing, and then we have a tiny Rust program that depends on these libraries, as well as the CLI, without having to double the disk size. And then, so I think that is something pretty cool, and if you're interested, then I will be happy to talk to you about it. Up next, oh no, first, I wanted to mention that when going deeper and using this FFmpeg C API, you really start to realize the complexity that a video format has. I really was so naive and thought, okay, I could just play this video in a video tag and everything would be fine. But the deeper you go, the more control you have over things like pixel formats, color spaces, presentation timestamps, and we have already heard earlier today about how cursed they are if they are non-monotonous. And I could also tell you many more horror stories about this, but I think I will not take the time to rant now, but if you want to hear a horror story about this, you can go to Twitter and search Rusty Jonny and the cursed MP4 file, and then I will tell you a story about a really cursed MP4 file and how I solved the problem with Rust. All right. Another area that I'm focusing on is rendering in the cloud. because I think that is the biggest strength of free motion. Unlike programs like After Effects and Premiere that are used for motion graphics, usually we can run this on regular Linux environments. And one opportunity that I saw was to create a distributed video renderer on AWS Lambda. And this, I would like to show to you how it works. So the video that I've shown to you before, I've made it now 15 minutes long and used our loop component. So it's a pretty long video. And now what we are going to do is we're going to render this 15-minute long video on AWS Lambda. We're first going to spawn one single Lambda function. And this Lambda function is going to recursively call itself 150 times. Each one of these Lambda functions will render a few seconds of video. They will send the video back to the original Lambda function. And if everything goes well, we will have a 15-minute long video. So I'm starting it now. Meanwhile, you can see we get some logs as well that we can look at later. And now we are rendering the frames. All 150 Lambda functions are now alive. And we are already nearing the end of the rendering the frames with Puppeteer phase. Now the chunks have been encoded into MP4. And here we go. In just 30 seconds, we have rendered a 15-minute long video for 10 cents. And now the Lambdas are all shut down again, and we don't need to pay anymore. So I have to admit, though, that I cheated a little bit because I didn't render the audio of the video. If I were to do that, it would take maybe like twice as long. This is because combining the H.264 chunks into a long video is really fast. There's almost no overhead. But for the audio, it is a bit more tricky. If we render AAC chunks and then stitch them together, we get this tiny popping, crackling sounds in the seams at the points where it's being stitched together. And that doesn't sound nice. So what we do instead is we create PCM audio, first stitch together the uncompressed audio, and then in this combining video phase, we re-encode the whole 15 minutes of audio into AAC. So then it takes usually twice as long. Now it was a bit faster because now the Lambdas are warm. Yeah, if anybody knows how to solve that, I would for sure it would be a game changer to us. Maybe someone is good enough. And looking at the logs, you can see that we really spawned the Lambda function 150 times. And that we rendered all the frames using ffmpeg command. And yeah, I think that's a pretty new way that we developed over the past 1.5 years, and that seems to work out, except the things we haven't yet figured out, the audio and also like the color space stuff and that. I'm still learning about it, but how I'm developing I'm just putting out new releases like every 2 days or so, waiting for feedback from people to use it. They also send a lot of cursed videos, which I then try to handle, and that is how we somehow managed to create a pretty scalable system. And yesterday I got a message from a customer. They rendered 400,000 videos using this Lambda solution in the past 30 days. So yeah, that is for sure, one thing that I'm also happy to have discourse about afterwards. If you want to follow me, then, like I said, I'm actually here until Monday morning, so come talk to me. I'm on X. I have a YouTube channel. If you want to learn more about Remotion, you may visit our website, or make your first video today by typing in npm init video to the command line. On our YouTube, we also have more tutorials, and we are also on X, Instagram, and TikTok, where we are trying to capture the Gen Z JavaScript programmers. Thanks a lot.
Thank you very much. All right, are there any questions for Jonny?
So, I would like to ask why you have decided to use Lambda functions instead of, for example, node groups and like some kind of microservices on the AC2.
Instead of coroutines?
Instead of node groups on AWS.
Node groups. I don't even know what it is. We have also experimented with Cloud Run just to diversify a bit. Some people don't like AWS. This is just the first thing that we've tried. We went for Lambda functions because AWS is the biggest cloud, and it seemed the most obvious. But I could imagine doing other types of orchestration as well.
Okay. Is there anyone else who would like to ask a question?
Thank you for the talk. You mentioned Puppeteer. I have actually two questions. So first one, what role did it take in the process? And second question, do you know any alternatives to Puppeteer? That would be interesting.
Yeah. So the first question was, how does our process work? So with Puppeteer, you can open a page, you can screenshot it. Actually, what we do is we open 4 tabs and then screenshot all of them in parallel, so the video can render even faster. We first bundle our React code. That is also a requirement before you can send it to the, before you can render the cloud, because your node modules folder is way too big. And alternative to Puppeteer, I mean, how you interface with the browser is actually the Chrome DevTools protocol that is implemented even in other browsers. And so you could implement this yourself or use Playwright. It's all the same thing, all the same protocol. That's also a limitation, I have to say, because when we get the screenshots, what Chrome will actually do, and there is no other way currently, is it will encode it into a JPEG and then base 64 encode it, and then you get the picture back. So I see a huge opportunity to make it even faster, for example, by forking Chrome or using, we've actually thought about it, or using like Chrome driver or I think there are other C++ projects where you can embed Chrome.
Thanks. Any more questions? Okay, so let's thank Jonny for the presentation once again. And now a time for another speaker. Wojtek, you can come in. Wojtek Barczyński, who is a colleague of mine working at Software Mansion. For the last year, he's been struggling with technologies like FFmpeg, OpenGL, Vulkan, working on the real-time composition. And he's going to share the lessons learned while developing VideoCompositor. If you're ready, you can start.
Yeah, thanks for the intro. So the VideoCompositor is basically a language-agnostic tool that allows you to do live video composing. So what is live video composing? You have 2 parts. First is video composing, and it's pretty much putting multiple videos with some cool effects like grids or like transitions. And we'll show you in a minute how it looks like. But the second part is live part. And it's the tricky part because you have very limited time to do that. From 10 seconds, like in HLS, to 50 milliseconds in live sources like video conferencing. So, what were the key challenges that we had to deal with? First one was that raw video is really, really large. And if you want to do some of the composing, you firstly have to decode the video that you receive, then perform some transformations on them, and then encode it and send it back. Because if you want to receive video in raw format, it basically too big, copying it would kill your machine. So also CPU decoding and encoding costs a lot. Actually, currently, it's most of our computing cost is the encoding. So we wanted to choose technology that in the future would allow us to move that part to the GPU side, and we could send our H.264 streams or any other format to the GPU, decode it there, perform any operations, encode it back, and send back to the CPU the H.264 format or any lighter format than the raw video. Because if you want to send it to the GPU, it's also really, really slow. So how we went about it? So we started with, whenever every multimedia project starts, with FFmpeg. And FFmpeg is a great tool for performing a lot of operations, encoding, decoding, and all that stuff, but it has really limited options when it comes to the composing part. You can do basic stuff like V-stacks, H-stacks, stacking videos in the grid, or overlaying one over the other, but as soon as you start doing really complex stuff like transitions and so on, it stops being a good abstraction over that. So we thought, well, just use a browser. And here comes the tricky part. Because if you want to use a browser, you can either send header strings encoded and handle everything by the browser, but then you don't have any control over the enqueuing process of the frames. And if you don't have the control over the enqueuing of the frames, then you lose a lot of on synchronization of those strings. You can't tune those algorithms to your use case. So, and also the other option is to decode it firstly, enqueue those frames and send them decoded to the Chrome. But then it's you have to copy the memory and you lose a lot of computing power. So we started researching graphical APIs. First one was OpenGL, and GL stands for good luck. It's been quite long with us, but it has really bad developer experience. It lacks many safety features, but it works almost everywhere. It's well-developed ecosystem. You can easily find web developer, any game dev developers out there willing to come to your project if they don't have to work 12 hours a day. And it's basically a decent abstraction for graphical rendering, but we couldn't find a way to decode the video on the GPU with OpenGL. And there comes a Vulkan. So OpenGL was the first thing that Cron's group produced, and the second was Vulkan. And this slide explains the complexity of the Vulkan. Safe to say, we spent like few weeks to just render a single triangle, and it was like over 2,000 lines of code. So we figured out that even though Vulkan can give us a lot of decoding and coding part, because it already has implemented features for it, it's probably too complex for our project. We are not building a video game after all, yet. So we search further, and we find WebGPU. And WebGPU is another standard that replace WebGL, and it's still in progress, like many Google stuff things. It's relatively new ecosystem. It has great implementation, WGPU, the REST implementation, that is cross-platform, so you can basically write your code once and then run it on multiple backends. So like on Linux devices with AMD and NVIDIA cards, also you can run it on Mac devices and so on. It has pretty good documentation, but it lacks a lot of things in ecosystem, like previewing how your shaders would look like and stuff like that. And WebGPU gave us the second option to decode video using decode and encode video using Vulkan, because in the future, because under the hood, it actually on some platforms uses Vulkan and Vulkan buffers, so we could use Vulkan for decoding and coding and use WebGPU for all other stuff. So we use it in our own app, like you've seen before. So how it works like? So basically, VideoCompositor is really related to Membrane and how it processes the video. So you have input streams that are basically videos received over the RTP streams, over the RTP streams. You have some transition nodes that perform some operations, and then the output stream. And this is fairly simple pipeline, but you can get a lot more complex with that. So firstly, I want to show you some quick presentation, how live demo, if you say, how it could work like. So this is simple video room, like video conferencing app. The video will start appearing in a moment. You basically have multiple videos streamed to the compositor. It composes it into a simple grid, adds some text, stuff like that, and sends it back. And you can change the way how your streams can look like. Okay. We have also an option to write your own shaders. So shader is basically a code executed on GPU to customize VideoCompositor to your business use case. And here is the example of simple shader written like this. It's basically two streams streamed to the compositor. We have some overlaying them. We are overlaying them and performing some simple operation on one of them with custom shader that basically merges, makes some part of it invisible. And as I said, it's language agnostic, so you can basically, because you send stream through RTP, and the definition of what VideoCompositor should perform via HTTP. Therefore, you can use it in any language you like. And so here we see the same stuff in REST. Okay. And the last example, it's the web. We talked before about porting the browser. We actually did something like this, because we made embeddings for Chrome engine in Rust to be able to basically embed your videos into any website you want. But it has some downside, because you have to copy memory between CPU and GPU. Therefore, it's hard to scale that. It should appear in a minute. But you can perform any CSS operation you would like on live videos. So other stuff that you can do is like text rendering, adding images, some basic basic transformations like corners rounding, gridding, and so on are already there. For others, you can write your own code to do that. I encourage you to check out the repo. We have a wiki and examples out there. And see you on workshops tomorrow, where I hope we will teach you a little bit how rendering works. You can write there your own shaders and basically play with it a little bit. Thank you.
Thank you very much.
All right, so now a round of questions. Is there anyone who'd like to ask something, Wojtek?
Where is Big Bang Bunny video?
So you said you use the GPU and you use also the browser. So I can choose whether to use one or the other?
OK, so from the user perspective, you don't see how it's implemented underneath. So basically, you don't need to worry about the shader stuff, the GPU stuff, if you just want to merge a couple of videos, right? This was one of the goals of the tool, creating the tool to abstract it from the users. So in the pipeline, you have multiple nodes. And some of those nodes perform operations on the GPU, like the shaders. You can remove green screens and stuff like that. And we have special component in that special type of node in that pipeline, which is web renderer. And you can use it for rendering web stuff, but it has to copy memory from the GPU to the CPU, send it to the share the memory with Chrome Engine, renders it with Chrome Engine, and upload it back to GPU. So it's not the best solution for scaling, but you can easily develop well-looking app quite quickly, because you can use already the abstraction that you know from creating websites and stuff like this.
Great, thanks.
OK, any other questions?
OK, I'll be around and on workshops if you want to talk.
Thank you very much. All right, and now it is time for another speaker, Paula Osés. Welcome. Paula is an AI engineer working at Numena. I hope I get it right. Developing cutting-edge deep learning and computer vision algorithms. And Paula is going to take us on a journey beyond the frame, exploring the exciting field of video analysis and examining the use of computer vision and data processing techniques. OK, just a minute to set up. You can start whenever you're ready.
OK. OK, so hello, everyone. Thank you for coming to my talk. So the talk is about computer vision, and it's titled Beyond the Brain, Using Computer Vision to Unlock the Potential of Video Data. So first of all, my name is Paula. I'm a computer engineer in Numena. And to give some notes about my background, I studied audiovisual systems engineering, and then I'm doing a master's degree also on deep learning. And I have been working in a hospital doing disease detection algorithms, and now I'm working in Numena, which I will explain now what it is. So Numena is a startup in Barcelona that basically its mission is to develop metrics and instruments to empower decision-making towards more efficient, resilient, and sustainable spatial solutions. So the way that I structured this talk is that first I'm going to give a brief introduction about computer vision, and then I will explain in more details how we did one project in my company. So first of all, what is computer vision? How come computers are able to understand images? So for me, this is a very interesting topic. And the answer to this is that computer vision is a field of artificial intelligence and computer science that focuses on enabling machines to understand the visual content around us. These algorithms, what they do is that they analyze the content of the images, like including shapes, colors, and motions, and from that they extract features. That these features then can be labeled and used to train different algorithms that are powered with machine learning techniques. So a workflow of a computer vision algorithm is the following. First of all, you have the data collection, then you do usually some pre-processing to this data, you apply the algorithm, and then you do some post-processing to this data to extract meaning to it. So first of all, the data collection. And this is a key factor of computer vision and any of artificial intelligence algorithms, because of course your model learns from the data that you provide, so you need good data. And to have good data, what does it mean? So first of all, you have a list of requirements that you can see here. That the first one is that you need large amounts of data. So for instance, the model that we will use in the further example was trained, I think, with around 1 million images or something like that. Then, of course, you need a variety in the dataset. So you want your dataset to have as multiple and different images as possible. So you build robust algorithms. Then you want it to be balanced. So for instance, in this case that I put here an example, you have dogs and cats. So it's a multi-class model. So you want to have more or less the same amount of cats and dogs, so your model doesn't have any biases. Then you want your images to be representative of whatever you want to detect. And of course, this is obvious, but you need it to be well labeled. Okay, and to have all this data set is normally kind of expensive, or maybe you just don't have it in your company. So what we use a lot is to use open source data sets. That the most common one is Coco. Well, here I put some links. But what you can do is that you can use open source data sets that you found online, that they are already labeled, so it's easy to use. And then if you want to train your models for different classes, for instance, you can apply transfer learning, so you already have a good base of images, and then you don't need to apply to do so much manual labeling. And this is a way that you can gain some time. Now we go to the step of pre-processing of the data. So normally I categorize it into steps. First of all, well, if you work with images or videos, first normally you check the images. So you see if the images have good colors, if you're able to distinguish the classes, if they are of good quality. So depending on your data set, you will apply different things. So for instance, if you're recording videos in the street, maybe the colors are not good, so you apply some normalization or you enhance some images. And then in the case of video, what is very common to apply is almost always we do some subsampling of the frame rates, because now cameras record very high frames per second, but usually you don't need as many, and you are like just inputting a lot of images to your algorithm. So normally we do a subsampling. Then of course, depending on the quality that you want of the image or like your objective, you can rescale the videos and make it smaller. So for instance, if you're doing object detection, you will not do that because you need a lot of definition, but if you're doing object detection, maybe yes. You can normalize the videos, and of course then you encode it and feed it to the algorithm. So now it will come the part of the algorithms, that this is the tricky part, and I could be like a whole presentation just talking about one. So what I did is that I put here the ones that are more used, that for instance are object detection. Then you can do post-estimation for person or for animals. You can do semantic segmentation, instance segmentation, face recognition, that you can see there my face, and it's pretty accurate. Then you can do tracking as well. So you, depending on your use case, you can develop an algorithm or use some that are online, open source, and there are many of them. And then, of course, you do the post-processing of the data. So normally, what you do is that you apply the algorithm, then you get some results back, but you have to check the results. First, check that if they are all right, and then maybe you take out the outliers, you do some thresholding, and from that you try to extract meaning, and usually you do some visualization so the client is able to understand all of these numbers. Okay. Now what I will do is that I will explain the real case scenario, so a project that we did in our company. That is actually the first one that I did when I came to the company, so for me it was kind of special. And this project is about the monitoring urban spaces in Barcelona. So basically this is a project that we did together with the municipality of Barcelona, and the idea is that they want to understand how people, bicycles, and vehicles are interacting with each other. And this is because now in Barcelona we are changing the structure of some streets, so they wanted to know how the people are interacting before they change the streets, and then they want to know what is going to happen after and how the people change their flows of movement. Okay, so of course, to do this project, we followed the structure that I just explained to you. And the first step was the data collection. In this case, what we did for the dataset for training was to use the open source dataset that I was mentioned, that is Coco, that I think everyone that is in this industry is using it. And then we have the prediction data, so the data that we used to analyze the data, that was the one that we recorded from the streets of Barcelona. So here you can see an example of the, well, this is the Coco dataset, and then you can see the type of images that you can get and that they are labeled. And what we did in this case, that the classes that we are interested in were the cars, the bikes, the motorbikes, trucks, and pedestrians. And so you have this dataset, you can download it and use it. And then for the data collection of the prediction data, and what you see here is a picture of the streets of Barcelona, and the green dots is the places where we installed cameras. In this case, what we did is that we installed normal RGB cameras, 7 of them, and we were recording for 3 days. These 3 days were Monday, Thursday, and Sunday, just because we wanted to understand how the people are moving in the different days of the week. And also, it's important to take into consideration that this was August. So people in August move in a ways that they don't move in winter because of temperatures and so different things. And what we did is that we were monitoring 2 streets, so like both that are the one that is in the top in the bottom, because this one here, this one here is the one that is going under construction, that is actually this year has finished, so now it's a completely different street, and this one is staying the same. So in this way, we're able to compare how the people are moving. Okay, well, here you can see the cameras and my colleague installing them. And okay, so we recorded the videos, and we had around 6 gigabytes of data. And this data that we recorded, also, we applied some pre-processing, which in this case was that we reduced the frames per second, because I think we were recording at 30 frames per second, but then testing the algorithms, they were working just as fine with 15 frames per second, so we reduced all of them. And then we also correct the distortion. So I don't know if you can notice, but in the image of the top, what we did is that we, like normally all the cameras have some kind of fisheye effect, and you don't want that because they distort the persons and the cars and the bicycles. So in order to increase the accuracy, you normally flatten the image, so you have a perfectly normal shape of the classes. And then here we also implemented this that we call that they are corridors, that you can see that there is the pink, the blue, and the yellow. And this is because in the city of Barcelona is kind of a complex environment, because, well, in every city, because people move weirdly, bikes are parked everywhere, motorbikes are parked everywhere, maybe a truck is in the middle of the camera, you don't see anything. So this was like a little trick that helped the algorithm improve the accuracy, because with these colors, we said to the algorithm, what are you expecting to find in these places? So in the pink, you're expecting to find persons. Of course, you can find it in different places, but in this way, these detections had much weight than the others that that they were not in the expected places. Okay, now for the part of the algorithm. So we have done the data collection and the pre-processing. And now for the algorithm, what we did is that we decided to use YOLO, in this case YOLO 7, which was the one that was available at the moment. That is an open source project, and it's trained with the Coco dataset, that is one of the most used, and I think it's the one that works best in the industry now. And so what we did is that we downloaded this pre-trained model, and then choose to detect the classes that I showed you before. And then so this was just to detect if it was in the image a bicycle, a car, or a person. And then what we wanted to do is to track them over the frames, and also how it is moving. So we applied a tracker that in this case was Norfair, that is a tracker that is very used in Python because it's kind of lightweight, so you are able to put it in any model that you are using. And then we implemented both of these algorithms and created a code that was able to extract the data that we wanted. And we also implemented a counter, because the municipality of Barcelona was very interested in knowing the amount of persons that were in the street at every 5 minutes, or like in a given amount of time. Okay, so now we ran the algorithms that it took like kind of a lot of time to run. And then we had the data. The data set, this is a capture of the data set that we got. That was, we had the time, the amount of cars, persons, and bicycles, because this was the first step of the algorithm. Then in further iterations that we have been doing, we also have the points in the tracking, so we can plot in the map how the people were actually moving. But for this iteration, we did the counting. And the first step was to check the data, make sure that it's all right, clean if there is something that is not okay. And then what we did is that we created some visualization for the people to understand what is happening. So here you can see some of the visualizations, and basically what this represents is that, well, these are the streets, and then you can see the amount of people, bicycles and cars that I think you cannot see it very much, but that they were in each street. And for instance, the last image is Sunday, that you can see that there is much more people, because on Sundays people don't work, so they are out in the street. And then you see that more or less now the amount of bicycles and cars are kind of the same. There are more cars than bicycles, which is something that they are trying to change with this restructure of the streets. And well, and the amount of people varies a lot with the hour of the day, because I don't know, at 11 everyone is working, in the afternoon there is more people, so it depends. And then what was also very interesting for this project is that we had to calculate the accuracy. Well, you normally know the accuracy of the algorithms and you calculate it, but in this case, the municipality was very intrigued because they wanted to know if they can apply this usually, or they need to find other ways to maybe put sensoric on the ground, or different ways that they can do it. So what we did is that we calculated the accuracy of this algorithm. So basically this means that we took videos that were run in the algorithms, and then a person was labeling them and counting the people, and then we could compare how the model was working versus how the persons I don't know, are able to see it. And what we saw is that we have pretty good accuracies, because of course you can always improve, but given that it's in a state in Barcelona, that there are a lot of shadows, that people are moving, the trucks are in front of the camera, that we were not able to put the camera in the ideal place, because normally you have to use, well, they give you designated places. So in our case was in the top of a lamp, so you have like a weird perspective. So there's a lot of things. But given that we had this situation, the accuracies were very good, but the one that was worse was the one about the bikes. And this is because since we had the camera from the top to the bottom, you can see the person in the bike, but sometimes you cannot see the bike. So to solve these things, normally you can do some labeling of this data set and then retrain your model, so it's able to understand that this is a bike, even though there is a person above the bike. But the results were quite good, and people were happy about it, so we were happy. And well, this was the end of the computer vision projects. And now I will explain like some lessons learned and what will be the next steps that we should do to improve this model. So first of all, one thing that was very tricky to us is that of course, you calculate the time of execution of your algorithm, so it depends on the GPUs that you have, the amount of videos. So we did our calculus, and we had, I don't know, maybe 3 or 4 days of running algorithms. But then, and we did some tests, and it was fine. But then when we put all the videos to run, so we created like the flow, so I don't know, we will start with Monday, and then we go with Thursday, and so on, we saw that the algorithm kept crashing. So we revisit the algorithm, go step by step, and so everything seemed to be fine. And finally, we look at the videos, and they were corrupted. But of course, the videos that we did the test were perfectly fine, but all the rest of the video apparently were corrupted. So we had to run some ffmpeg commands to decorrupt them, which is not a big deal, but the deal was that we had said that we will have this in this amount of time. And now, when we have to run this decorruption step, it took the same amount of time that we had planned to run the whole algorithm. So in the end, we were like just stealing computers in the office and make it work. But of course, seeing this now in perspective, it's better to have double the time and you're fine. Then also, since there is this weird situation that there is a lot of shadow, trees, and I don't know, kids running around, we decided in the next step we will try with higher definition cameras, because in this case I think we were running the cameras at 640 by 480, so very low definition because the classes are pretty big, so you can see a truck from a distance. But giving, like now understanding the context of it, maybe we will try something with more definition. And the last one is the most important one, and this is that this type of projects depend a lot in the space that you're monitoring. So if we were monitoring only 2 streets, with 7 cameras was okay, but if we wanted to do it in the whole Barcelona, we need, I don't know, 1,000 cameras. So if we need 1,000 cameras, we need a full room in the office full of GPUs. Or like, you have to think a lot about the infrastructure and do put our money and then change the structure of your company, maybe. So what we are now implementing is just to run these algorithms on the edge, so meaning that since we are already developing the cameras that we use for recording, what we want to do is that while recording the videos, we are already processing these images, so meaning that we will run the object detection algorithm and the tracking in the camera, and then when you are sending to the database is just the information. So maybe a car in this position at this time, but you are not sending more information or saving the videos, which also is a lot of memory. And now we're developing this, and that's it. That is the end of my presentation. I hope you like it, and if you have any questions, please.
As usual, now is the time to ask questions. Are there any? Thank you. Okay, first one.
The last bit was fascinating about effectively doing the detection at the edge and then just streaming the data rather than the raw video. And what kind of hardware do you need out at the camera end to be able to do that?
Now, I'm not the one developing the camera, but I know that we are using, so just to record a video and save it, we were using Raspberry Zero, I think. But now these ones are going to crash with the algorithms that we have, so now I think they are trying with bigger ones. I don't know which one actually. I think they tried with Nano, was kind of not working, and I think now they will put, I don't know, maybe Raspberry. I think we have Raspberry 4, but maybe this is too powerful, so it's, you have to find like a balance, because also you are putting these cameras on the street, so you don't want them to get like, if they are too expensive, maybe you don't want to set in this, like, there's like a fine line, you know? Like if you have good hardware in the street, maybe, yeah.
Hello. So you talk about like the Coco dataset and like the image processing, like in the like you just process a video as a bunch of like a single frames, and they are like learned from the like Coco or ImageNet. But then, have you thought about does that algorithm takes like the context of like the other frames? I mean, when you like see a bike and a person as like a single frame, it may be hard to like see that, for example, from some height, to see that it is a person. But if you have a context of video that the bike is quite faster, then maybe it's like easier to predict that something is a bike. So my question is, does that yellow algorithm just take like the videos as videos, or just frame by frame?
Now, what I understand is that it goes frame by frame. So then you apply your tracker, and then you're able to see where is it going. So you could do it this like in pre-processing steps. So maybe if a class is going this distance in this amount of frames, it's probably not a person or a very fast person.
Yeah.
You know, Usain Bolt, but
yeah.
But you could do this.
Back to the moving the computing to the edge. So it makes total sense that you want to do that and then just have the result in your server. But I suppose on the other hand, you have to trust that the recognition was right, etc. Do you have like any way to
know,
or either to know or maybe to save some of the video just for later analysis, just to make sure, or how do you do it?
Yeah, like now, like also depends on the project, because for instance, in urban spaces, now we have been doing a lot of them, so now we are pretty sure how our algorithm works. So we could try, well, I think you will save some videos just to check, but you are comfortable, you feel comfortable about the algorithm, so maybe you just implement it, and I don't know. You have also multiple cameras, so maybe if one crashes, it's not so bad. But depending on this is the thing, that depending on the project, maybe it's too risky to not save the data. So we were also investigating the possibility that maybe the camera, so we had, for instance, a room, so we installed 5 cameras, and then these cameras are sending the videos to a centralized unit, and then this unit is the one that is processing. So maybe in a given moment, we can enter this unit and check that everything is right, and even see the videos. So it depends how comfortable or how is the space for you. Like, I don't know, depending on your models as well. For us now, like we will do it in urban spaces because we have the models trained and we are sure how they are doing it, but for a new project, maybe, I don't know, maybe we will save the data first and then check.
Thanks.
Well, I've got a question, because you've, on the graphic, there were shown 6 points or something that you're training on the detection of people that. My question is, have you tested it on other points, maybe not streets? How does your algorithm is your algorithm very, does it handle other scenes well, or have you tried this?
So I think now the worst scenario is like in Barcelona, possibly because of the shadows, the trees, and the people. But for instance, if we test the same algorithm in highways, like the accuracies are higher because the highways have like the same color in the ground. There are no trees above them. So I think normally, like if you start from highways and then you go to a city or something like that your algorithm is not going to perform as expected. But if you're already in a difficult situation, it's good. Also, this was trained also, well, this was also trained with images at night at the end because we were recording 24 hours. So in this way now this algorithm is kind of robust because it has been fed with a lot of images. But this is a thing that you do either all at once, but with time you start to see which type of images you have not processed or have not trained the algorithms, and so you see that it's failing there. So you can just retrain it and improve the accuracies with the different projects that you have or like different necessities.
You've mentioned you've tested it on the highways, yes? And what other places have you tried it?
Well, this one just because it's urban spaces, so to have cars, it's only our cities or highways. But for instance, if we were monitoring a room, we will use a different algorithm, or we will apply transfer learning, because in this case, you are just monitoring people in different conditions and in different spaces. So it will not perform as good here.
Yes, thank you.
One more question there.
You mentioned, I guess, running the models on the edge. Do you have plans for I guess, deploying different models, like over-the-air updates and things like that to the cameras or things like that? Or maybe reusing the cameras for other projects in the future? Or maybe you're looking for different things?
Yeah, this depends on the project, because there are some projects, like we also do this in retail, so in retail stores. And in this case, you cannot reuse the cameras because the people of the store keep the camera. But when we install the cameras in Barcelona, we can reuse them because we install them and then we take it out. Because depends on also the agreement that you have with the partner in that case.
So if you can take them out, is that how you service them and upgrade the software, or do you have over-the-air updates?
Usually, we just enter the cameras from our space and we are able to change whatever we want.
Okay, so you do have to pull them down to change them, and okay, thank you.
Okay, so I think are there any other questions? As I haven't seen any hands. Okay, so let's give another round of applause for Paula. Thank you very much. Yeah, I think we're ready to go to. Let's continue our AI track here. Next up is Wojtek Jasiński with the presentation that I believe was developed behind my back at Software Mention Office. And Wojtek is going to speak about performance challenges with the live processing using the artificial intelligence. Okay, I think we're ready to go, so the stage is yours.
Hi guys, it's great to be here. I prepared a short talk about the things I learned.
Can you wait a bit? How we have an issue with the microphone?
So, first of all, let me ask you, how many of you are familiar with machine learning? For example, how many of you have trained a model in your life? Yes, that's good. That's more than I expected. Okay, so to be clear, you don't need to be an AI expert to understand what I am going to talk about. Really, you don't need to understand all the things I will be saying. You just vibe with me, okay? So, for all of you working with multimedia, why should you care about AI models and efficiency? AI is all the hype right now. You all know large language models, ChatGPT, the diffusion models, all the generative AI, and these are remarkable achievements, and the AI progress is stunning. So you can ask yourself, what's next? And I don't really know, but sometime AI is coming for multimedia. Real-time applications for computer vision are becoming more popular, and a lot of cool stuff is going on. Let me go over with some examples of how real-time AI is already used for video processing. You all know this kind of face mesh and pose estimation from Snapchat if you used it. This is not a new technology. You're probably familiar with segmentation models, you know, from conference calls. If you ever used green screen, virtual green screen on your Microsoft Teams or Google Meets, this is AI working in the background. As well as your smartphone camera. There's a lot of AI magic going on that's responsible for your pictures looking this crisp and low light enhancement and this kind of stuff is like really working their way in the background of your smartphone cameras. There's more examples. How many of you are familiar with this DLSS from NVIDIA? This is really cool. You can render a game at a lower resolution and upscale it using AI in real time. Turns out it's much more efficient. It's much faster than rendering in higher resolutions. And this allows you to do complex stuff like ray tracing and then just upscale it. Use the AI magic, right? There's also some generative tools. Another one from NVIDIA. This one takes your eyes from your computer screen up to your camera, so your conference calls don't feel so awkward. More is coming. You know, there's a lot of hardware support being built in newer devices, like newest notebooks or smartphones are equipped with tensor processing chips, basically AI computing chips, which in the near future will allow us to run bigger and stronger models in real time. If you strip down a VR headset, you're soon going to find some special AI chips too. So the tools and libraries for AI development are also maturing. In future, development of AI software will be much easier. And that's why you should care. In real-time applications, model efficiency matters quite a lot, obviously. That's not so obvious in scientific literature, where you can often find that in papers, the focus is primarily on scoring higher on benchmarks, not really at making the model go faster to be applicable in real time. So let's go over some model metrics that you can find in scientific literature. They often promise to reflect on its efficiency, but that's not always the case. You're probably all familiar with parameter count. If you've got a neural network, you have some weights and biases and other params that, if you count them, that's basically your model size. You know, large language models have a lot of parameters, hence the name. They're counted in billions or hundreds of billions. Typical CNNs, like computer vision neural networks, are not as big, with their parameter count ranging from hundreds of thousands to hundreds of millions. You don't really need to know all that, but this is just for reference to know what kind of values we're talking about. Does parameter count matter? I have a spoiler. Yes, it does. It's not crucial for efficiency, but you generally, the bigger the model, the better the accuracy. We all know that. If you had a lot of data, a lot of compute power, if you train a bigger model, it's going to do better. But it may not go as fast as you want it. If you deploy on edge, meaning your smartphone or notebooks or your watch or whatever, the network should be rather small to fit into memory. So while parameter count is not a great metric for efficiency, it does matter, and you should, if you want your model to be efficient, you should keep it small. There are flops, floating point operations. Basically, how many operations you need to complete for the model to give you predictions. Not to be confused with flops, which is floating point operations per second, with the capital S. This is a measure of computational power. You may say that a GPU has a capability of running 80 teraflops. When we're talking about a model, we use flops. That's the total computations you need to run. And it might be slightly better for measuring efficiency, since parameters can be shared between layers, and they're not as good. You can see this chart right here just for reference. More parameters usually translates to more flops and a lower error rate. But we don't really see the efficiency right here. We care about, there's max. Max are multiply accumulate operations. They can be used instead of flops, because most of modern architectures, CPUs or GPUs, use FMA. This is fused multiply add operation. This is like one operation instead of two. So it's much more relevant to talk about max when we're talking about machine learning models, because they use rely overwhelmingly on this multiply accumulate operations. Roughly, you get twice as many flops as max. And they are sometimes confused. If you go over to original ResNet paper, like big paper, right? Some of you may know it. How many of you know it? ResNet, nice. They state their number of flops, but they really meant max. That's why this may be kind of confusing. Still not good enough. Max, flops, and param count can be useful and can give you a hint about model speed, but they are indirect metrics for efficiency. As you can see on this table right here, this is a comparison of various model architectures. The correlations are much lower than we might anticipate. The correlation between mobile latency and flops. It's even worse with parameter count. So why are they bad at predicting the speed of the model? Let's find out. Now, let me bore you to death with some heavy machine learning stuff. Let's go over some things that efficiency heavily depends upon, but the flops, max, and param count don't take into the account. The first one is memory access cost. Because if you count the operations, you don't really count how many memory access, how much time you're spending on memory access. So this should not be ignored during neural network design. Example right here. I know it may seem kind of complex, but you don't really need to get all it. This is a normal convolutional layer. It's used in neural networks for computer vision. This one is depthwise separable convolution layer. It's basically sparse version of the one on the right. It has less connections, takes much less operations, and is famously used in mobile nets, like the neural network architectures developed specifically for mobile CPUs. With the same number of channels, we have 3 right here, it has much less flops, but the memory access cost is still there. Oftentimes, you can find in papers that people scale up the number of channels because the number of flops is still really low, right? So it should be efficient, but it's not. It turns out it's actually much lower. So The memory access cost should not be ignored. Right. Another thing is skip connections. The skip connection is kind of this kind of building block that ResNet neural networks are all about. Basically, you go sequentially with the layers, but you add a second path for your data to run without obstacles. This makes your information travel through your neural network without obstacles, makes learning much more stable. It basically allows your neural network to have many more layers than it would be possible without it. This right here is even crazier. I don't know what's going on here. But you may expect that it comes at the cost of memory. If we want to add this value of a tensor later on, we need to store a copy of it. I'm not even talking about what's going on here, right? So while this may improve the accuracy of your network, stabilize the training, it sucks during inference. It makes your model slow. Yeah, this one is a beautiful inception network developed by Google a few years back. And we can see that it's made out of this kind of building blocks. Instead of one layer, we have a bunch of branches running through different kinds of convolutions. You don't worry about it. And we may guess that it's going hard on the memory, right? There's one thing that, one more reason why it's slow, especially in GPUs. It's the degree of parallelism. Basically, if you have one big task, it's much easier to parallelize than if you had a bunch of smaller, different tasks. GPUs are great at parallelizing computation, but there's one thing they hate, and that's synchronization. This thing forces the GPU to synchronize. That's why it's mad at this kind of architectures. So if we want to make our models faster, we should try to avoid this branching, this complex kind of patterns. We should keep it simple. And obviously, there's platform characteristics. You can't expect a neural network to behave the same way on CPU, on a GPU, mobile GPU, TPU, or whatever. Operations with the same number of flops could have different running time depending on the platform. Oftentimes, low-level libraries like QDNN on NVIDIA cards will be specially optimized for common operations like 3x3 convolutions. And this basically makes predicting runtime speed really hard because you don't know what's optimized to what extent. So what are the conclusions for this, or guidelines for you to either design or pick the right model? The most important one is latency and throughput are the only reliable metrics. If you're an ML engineer and you design a model architecture, or you are a software engineer browsing through the models, comparing them, if you care about efficiency, you should measure the latency or throughput on your target platform, because that's like the only reliable way to do it. This is like the most important conclusion here. But I have our guidelines. Oh, so I talked about model being that it's better to keep your model simple, while the branching and the complex skip connections can make the training smoother. It makes the model slower. Well, you can have your cake and eat it too. There's this trick called reparametrization. You can have a bunch of branches with convolutions and batch normalizations and tensor additions. These are all linear operations. So you can transform them, fuse them into mathematically equivalent single convolutional layer. So you train this kind of network, and then you calculate the equivalent network, like this one on the right. This one, the training goes smoothly, and it's like, you can see that the green line is lower than the blue line. And I don't know if you can see from all the back here. So the blue line is the same network, but without those additional branches. The train loss, meaning the error rate, is much lower for the network with those blocks that are reparametrizable. That's a hard word. And during deployment, you just cut it all out and leave it in a simple form. Another one, it's like, don't use models way too big for the use case. You don't need to overextend yourself for the few % more accuracy. You still want your model to be small and efficient. That's often more important than using the best solutions with the best scores on the market. But if you want to make a model smaller, you can use something like knowledge distillation. This is a technique to train the smaller neural network more effectively. If you have a bigger neural network, you can use it, you can employ it as a teacher for the smaller network. This way of training allows the student network, this one, to learn much better than it would all by itself. Sometimes it can match your bigger network's stats in terms of performance while being much more efficient. So this one is important to keep in mind. Also, don't forget to quantize. You basically, if you have a model with single precision floating points as weights, 32 bits per weight, you can scale it down to half precision. Usually, it does not cost you any performance degradation. It works just as it did before, but it's kind of faster, Also, the network weighs much less. You can go a few steps further and use 8-bit integers to represent those weights. Those integers correspond to the weights. That's why it's called quantization. Hence the name. And lastly, check out these tools. I know they are pain in the ass to work with, but they can do some real magic under the hood and optimize your model runtime significantly and fit it for the device you're deploying onto, like TensorRT for NVIDIA GPUs, TensorFlow Lite or PyTorch Mobile for smartphones or mobile devices, Onyx or whatever you actually wanted to, like your browser or stuff. So check them out. And that's all for today. Do you have any questions?
All right, so last portion of questions before the coffee break. Who would like to ask Wojtek a question?
I went too hard, right?
There's one.
Since there are no questions, I'm just going to share a funny story.
Yeah.
So I used to work at a startup, well-funded startup, with a leader, whoever, who was like, let's say, in love with AI and machine learning, but not necessarily an expert, okay? But he could get the money. And we were solving an interesting problem, which is that in retail, when people are buying like fruits and vegetables at large scale, they go rotten a lot, and a lot of it is thrown away. And this guy employed 10, 12, something like that, machine learning guys to create this super complicated model to predict, when's the right time to buy something. After about a half a year of experimentation, maybe even more, we found out the perfect model. It was called linear regression, and that's it. End of story.
Thanks for that. Are there any questions or funny stories to share? Okay, so let's give another round of applause for Wojtek. Thank you. Yeah, and as I said, it's now time for another coffee break. We'll get back in half an hour, like 4:30. So we'll be back. Thanks.
3.
All right. I think we're mostly ready for the last stint of our presentations. And after the coffee break, we're going to start with a presentation by Dan Jenkins, the founder and CEO of Nimble Ape and Everycast Labs, and apparently Spider-Man fan as well. Dan is going to speak about the responsibility that comes with the power of WebRTC. You can continue, Dan.
Thank you. Hello, everyone. Great to be here in Poland. First time I've been in Poland, so this is great. So yes, my talk. So a little bit of a warning. I've got 127 slides to get through in 20 minutes. So I'm going to talk fairly quickly. So yes, Spider-Man's Uncle Ben and his advice for casting your WebRTC. So a little bit about me very, very quickly. I'm Dan Jenkins, founder of Everycast Labs and Nimble Ape. I'm also the creator of a conference called ComCon, which you might have heard about today a couple of times. And I was the first Google developer expert in WebRTC. I love Lego. I love real-time media. I love developing things for the web. Has nothing to do with Spider-Man. And I haven't seen the latest Spider-Man movie. And there's my social media stuff. So Everycast Labs, we have a product called Broadcast Bridge that uses WebRTC heavily. Nimble Ape is a consultancy firm, so got a problem with real-time media and you'd like some help with it, let us know. And then ComCon is a residential event in the UK, so everyone stays in the same hotel for 3 days. Well, it's more like 4 and a bit. Top quality production values, 5 years worth of content on YouTube. And we're currently looking for sponsorship for 2024. So, public service announcement. All the images in this presentation were generated by Bing image creator. And yes, we don't have anything to fear from AI. AI will not destroy us. You'll see why. So yes, Spider-Man's Uncle Ben and his advice for casting your WebRTC. So remember, with great power comes great responsibility. Quite a few people attribute this to Spider-Man, Peter Parker, but it was actually Uncle Ben. And Uncle Ben was absolutely right. With great power comes great responsibility. So I'm going to assume that you all have a basic understanding of what WebRTC is, because we've heard about it quite a bit this morning and going into this afternoon. But a little history lesson first. May 2011, Google open sourced WebRTC. It was on the verge of being in June. Like the mailing list says the 1st of June, but it was actually in the last minutes of May 2011. What they really open sourced was libWebRTC and everything that kind of encompassed the beginnings of WebRTC. So libWebRTC is used by all of the browsers, and it mostly, because the browsers all use it in mostly the same way, everything just works magically. And as a result, we get nice W3C APIs that are built on top of libWebRTC. So we get user media, new media stream, RTC peer connection, create offer, create answer, blah, 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 right? These are all the ways that you can kind of start interacting with creating a peer connection. And ultimately, WebRTC is designed for low latency, extremely low latency. It's encrypted by default, peer-to-peer media and data. Everyone forgets about data. Like one of the biggest parts of WebRTC is the data channel. And it's got huge, huge benefits, but people forget to talk about it. NAT busting. So I think there's a stat which says like 90% of WebRTC sessions go from a client to a server now because we all talk to like an SFU. And Google Meet and Teams, etc., all use SFUs. But at its very core, you can talk to someone else that's behind a different firewall, behind a different NAT. So it's designed to be able to bust through that NAT using ICE. And it's made up of many, many different IETF specifications. So getting onto the topic of today, when you're talking to your clone pretty much understands you, right? Like if I was talking to someone else that's called Dan Jenkins, he would know exactly what I was thinking. And it would look something like this. No? Okay. libWebRTC is magic. WebRTC is magic. But yes, libWebRTC is a bit of a pain. We've heard it mentioned a couple of times today. It's absolutely huge. And to actually get going with libWebRTC, you have to go through a load of hoops to be able to download it in the right way and then to be able to compile it. It's a massive pain in the rear. But the key thing to remember is that libWebRTC doesn't equal WebRTC. If you go to WebRTC.org, you read about libWebRTC, but it's not true. WebRTC is a set of specifications. libWebRTC is just one of those implementations. So it's 2023, and we have loads of options now. So we've got something called Pion, which is written in Go. We've got WebRTC Rust. We've got a new Elixir WebRTC implementation. We've got AIORTC in Python. The Pipe team have some Java stuff that's open source, and then we've got libDataChannel. There are others as well. They're all variants of the same thing. Spider-Man in many, many, many different forms created by Bing. So now you've got loads of flexibility, and you can choose the right tool for the right job in the language that's right for the right job. And this is great. But remember, with great power comes great responsibility. If you're not careful, you're going to fall. Can anyone see what's wrong with this image? Spider-Man. I told Bing I wanted to create a picture of Spider-Man falling in New York between skyscrapers with his arms out. I mean, Bing kind of got it right. DALL-E got it kind of right. There's an arm missing. And if you look in some of the pictures, Spider-Man's got 6 fingers a lot of the time. So yeah, all those things that you take for granted because libWebRTC dealt with it, the browsers dealt with it, are now your responsibility because you're implementing your API, talking to Pion, Elixir, whatever, right? It's exciting, but it's also dangerous, right? So we use Pion at Everycast Labs, and it's part of our Broadcast Bridge product, alongside Janus and GStreamer. And we are very guilty of falling. So this is my tale of how even I, after over 10 years of working with WebRTC, fell hard. So let's take things back to basics a little bit. I'm 7 minutes in. I'm already on slide 46. This is going really, really well. So let's take it back to basics. We fell into the basic example trap. Who has taken an example off of a repo or a website and gone, this is really easy. And then a day or two later you go, there's this edge case that I haven't thought about. There's real world examples that just don't work. So for us, that was getting media from Janus as an SFU into Pion, and then getting that media from Pion into GStreamer. And then from GStreamer, we then output it in loads of different formats depending on what the user wants, whether or not that's outputting to AppSync so that we can send it over to NDI, whether or not that's sending it over to the DeckLink plugin or the AJA plugin in GStreamer. And it worked. It was really cool. So you go and make a peer connection over to Janus using Pion, and then you get the RTP out, and then you shove that into GStreamer. GStreamer does its magic, and then you chuck it out onto a sync, and it kind of just works. No, not at all. So the thing that we didn't implement was RTCP handling. So who remembers from earlier today what RTCP is? Dan, what is RTCP? Well, I mean, you obviously weren't listening to Lorenzo this morning. This is the benefit of being able to write my slides until the last minute. So RTCP provides out-of-band statistics and control information for an RTP session. So basically, it's the way that the browser or GStreamer or whatever is taking in that media and it's going, I don't have something here. I've lost it somewhere before it got to me. I don't have it. Can you give it to me again? Right? That's the very basicness of RTCP. So what happens without RTCP handling? Well, we end up with something like this. Yeah, not pretty. So this is actually an output from NDI, I think. Yeah, doesn't look very pretty at all. It's not something you'd want to put up on screen. So you get media quality issues. And ultimately, there's no way for the receiver to say, I need help, send me help, do something. Bing thought this was what I wanted. I said, Spider-Man shouting, I need help. Bing really likes Thor and Spider-Man. It gave me like 4 different options with Spider-Man and Thor. And then I told it, give me the same options, but without Thor and a different character. And it just completely and utterly didn't understand what I was asking for. We don't have anything to fear from AI. It's not coming to steal your jobs. So what did I do about it? And this was the key issue, right? As a temporary hack, so that I could continue hacking stuff together to get it all working, I increased the number of keyframes that got sent down from Janus. Janus has a really nice API and config where you can say, go give me a keyframe every 1 second. This is bad, but I did it. Bad media, no problem. We're going to get a keyframe momentarily, and it's going to fix my picture, right? No. Well, I know it did fix my problem. It did. This is from WebRTC internals of another of a different receiver receiving exactly the same that Pion and GStreamer was. So yes, keyframes decoded should not look like that. Basically, it should be like, you know, flat, 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 peak, flat, 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 peak. Keyframe means that we're sending way too much data and not relying on, you know, how things are actually meant to work. Yeah, it actually worked really, really well. A little too well, because I kind of forgot that it was there. But yeah, obviously I was wrong. RTCP exists for a reason. My friend, Sahi, has written a very good article on media resilience in WebRTC and all of the different options that are available. So go take a read of his article. Maybe I should have done that before I implemented my stuff. So why did I get it so wrong? I've been working with WebRTC for, you know, over 10 years now. How did I get it so wrong? Examples and the D word. The D word is documentation. Now, I'm not blaming Pion here. I'm the one that knows better. WebRTC is really difficult, right? WebRTC is built up of all of those individual component bits, and you forget about one of them, and it's going to come bite you in the ass. So WebRTC is made up of loads of bits, and it's really complex, and it's got so many moving parts. So where is the issue? I think this is the thing that actually made me go wrong. This is from the Pion website. It says, API you know. Pion implements the WebRTC API. Spend more time building and less time learning on a new API. Absolutely fantastic, right? It's talking about the W3C API. Saúl talked about this earlier. React Native WebRTC puts the W3C API on top of libWebRTC, just the way that we expect it to, because it's JavaScript and it's kind of pretending to be a browser, but not. So Pion's doing exactly the same thing. And WebRTC Rust has done the same thing, and lots of the other projects are kind of going down the same route. So I think, looking back on it, I expected too much magic from Pion. Let's take a very quick look at this example. This is RTX and NAC handling within RTCP, right? So I've sped this up quite a bit, and this is me kind of putting 10% packet loss on, and then trying to change it and failing. I'm going to go back in a second, restart it. But I put 10% packet loss on a Pion example that doesn't handle NACs. And hopefully, you'll see, so that's 1%. Oh, hold on, let me go back and start it again. So you can see it's kind of playing in the background, right? And then I add 10% and it just freezes. And it's not able to cope with it at all. And I turn it off and it starts playing again. I tried to take it down to 1%, but the network conditioner doesn't really understand that I changed it. And so it stayed at 10%. And this is me getting really confused with what's going on. This was me like 2 hours ago trying to record a video, and I was like, I'm not recording it again. So then we take it down to 1%, something more realistic, right? And you can see it's kind of pausing heavily. But you can still kind of like deal with it, but it's still pausing heavily. And this is the same, but with the bit of code that deals with NACs. So we're currently at 1% packet loss, and you can see no difference whatsoever. This is then me upping to 10%, the thing that caused complete and utter failure beforehand. And then this is me upping it to 30%. And when you watch it in real time, there is more stuttering, but it's completely and utterly watchable. So this is the code. This is the code that caused me so much. Well, actually, this isn't actually the code that caused so much problem. This is an example of something very, very similar. So what have we got here? So we're going to get the senders from our peer connection, and then we're going to process the RTCP. And then up there, we're saying, oh, right, process RTCP equals a function. And so we're reading from the sender, and we're not doing anything with it. Because as the comment says above, just reading it makes stuff happen. You don't have to do anything with it as a user, but we have to read it. It's not a magical thing that gets started for us. Would I have had to do any of this in JavaScript? No. I got complacent. I saw code that looked like this in the examples. So this is actually from a receiver, not a sender. And we're receiving our RTP, and then we're going to write a picture loss indication back every 3 seconds. And this is actually some of the code that I ended up using, as well as abusing Janus's kind ability to be able to send a keyframe. Yeah, send a PLI every 3 seconds. But yeah, this is an example code. This isn't production quality code, but examples are how we learn, especially when documentation is a little bit funny, because documentation is funny for Golang projects, because you're just meant to go to, the module and see loads of, function calls and like how do they actually work together. That's where examples come in. So yeah, WebRTC is by definition a group of other specifications. We've got ICE, DTLS, RTCP, RTP, and that's only naming a couple. There's a load of others that kind of go into the whole thing. This means that any of these could cause you a headache because you're implementing it, right? You're saying, go create me some RTP, send it, right? You're now having to deal with, RTP header numbers and everything else. You've got to understand what this is doing because libWebRTC isn't just, magically doing it for you. We've got people like Lorenzo in the crowd that, handle this stuff day on day because SFUs have to handle this day by day. But us client developers, we don't have to deal with this stuff usually, but it's really powerful that we can, and I'm really happy that we can. But at the same time, Uncle Ben reminds us that, that it's difficult. So yeah, we've got RTP, codec, simulcast, SVC, RTP extensions, buffering, et cetera, the list goes on. WebRTC can be really, really daunting, but it can also be really powerful. And now we've got the flexibility to be able to choose our client library, and that's a huge win. But yeah, like I say, you need to understand the core parts of WebRTC, and for us, that was RTC, that was properly handling RTCP. I mean, in your app, if you went and did it, you still need to handle RTCP too. Always handle RTCP. That's what I learned from this. Don't leave it to, I'll come back to it once I've got everything working. Don't leave it for another day. Interop is really hard, but I love that we now have it. So a world of libWebRTC only is a pretty dull one. Chad Hart has been following these trends for ages about which new libraries are coming popular, etc. So take a look at that link as well. More choice is only a good thing, but remember, think of Uncle Ben. With great power comes great responsibility. And thank you very much.
Thank you very much. All right, and now time for a question. Like, you handled that amount of slides really well, so we have some time left. Are there any questions?
Hey, Dan. Let me play devil's advocate a little bit. So as someone who also has to deal with a lot of client-side issues, you sometimes think, like, wouldn't it be easier if we all use the same damn thing? Instead of, Firefox this, Safari that.
I mean, ultimately, yeah, like you say, so Firefox is using parts of libWebRTC, Chrome is using libWebRTC, Safari is using libWebRTC. What if we all just, built libraries on top of libWebRTC? And I think this would be amazing. However, that requires certain companies giving up control that they currently have, and, actually answering questions and issues and accepting requests that, in a timely fashion. But, I mean, pigs don't fly, right? So, yes, it would be absolutely lovely, but it's not going to happen, is it? It would be nice.
It is, and it is. Great talk, Dan.
All right, any other questions? Or stories?
Or stories.
Okay. Well, thank you very much.
Thank you.
Let's give another round of applause. All right, and now is the time for another speaker, Ritvi Mishra from Dite. This is going to be a little bit about the introduction into WebRTC. If you're a bit surprised, this was originally planned to be earlier in the schedule, but we have to adjust. Do we need something?
Yes,
yeah,
I can't find
behind your back.
Thank you very much.
All right. As I said, Ritvi is from Dite. She's going to share her insights on getting started with WebRTC.
Awesome. How are we doing? Second last talk. Are you all relieved? No? Are you all enjoying? Awesome. Great. So I'm going to give you all an outsider's view into WebRTC, not specifically explain WebRTC because I know you all know way more than I possibly do. But it's more about, I think Dan already covered a lot of things that I'm going to say, but basically how difficult it is to, sometimes follow the jargon and, you tend to get lost. So this is what we're going to be covering today. I'll give you a quick intro into my background. We do a small intuition exercise and maybe build a word cloud. I'll tell you what the mistakes I've been making right now while I'm trying to learn WebRTC. I'll tell you how I would have liked to be introduced to WebRTC. And not the way I was. I'll talk about a couple of challenges, and I, of course, will take your input at most places. And then I'll talk about how I finally did figure out what I'm trying to learn, and maybe give a couple of examples into how I would ideally go about it. So, hey folks, I'm Ritvi. I'm a coach at Major League Hacking. I have a lot of obsessions once in a while. So my current obsessions are glass and scuba diving. So if y'all are into any of those, definitely come talk to me. I also have a day job. I work as a developer advocate at Dite. I think this is a good place for me to give you a little bit of a story insight as to why I even bothered coming up with this talk, right? So my background is in firmware engineering, and I've done I did like multiple internships with different design studios working on firmware. One of my favorite projects that I love talking about is a smart hookah that we made. Testing was definitely a very dedicated team that we had. But I basically switched gears into dev advocacy because I love being able to, talk about tech that I'm learning, and I am very passionate about being able to teach it. So I ended up at Diet, and I have been trying to create resources for people to learn about Diet, right? But before teaching about something that is leveraging tech below it, I need to be able to explain it to me and hence be able to break it down to, people further. So I just want to take a quick poll. How many of you all have tried to evangelize WebRTC or just, video calling tech? Okay. No one else? None of you have tried to evangelize the product you all are working on? I know there were a few talks from Membrane. I can bet it's not easy, especially as developers tend to want to use tech to basically make their life easy in terms of not having to learn the tech below it, right? So yeah, before I get started with the mistakes I made, let's do a small intuition exercise, right? So I want you all to scream, right? The first thing that comes to your head, like how when I say apple, you all get an image of Apple in your head. The first image that comes into your head when I say WebRTC, just scream. What's the first image that comes to your head? I don't want opinions. I don't want definitions. Just what's the first thing that comes to your head? Awesome. I think one of my favorite, I'll give you an example of my favorite. So I was doing this with APIs, and one of the people went them taking, doing stuff for their siblings. That was an example of the API intuition exercise. So yeah, what's the first thing that comes to your head when you hear the word WebRTC?
A wall of SDP.
Awesome! There we go. No one else? No images when you hear the word WebRTC? Rishit? Video. Awesome. Great. Cool. So this is something that we'll probably take pictures with later. So I would love for you all to scan the QR code and maybe put in your words that you all thought of when you all heard the word WebRTC. I'm going to give you all exactly 2 minutes on the clock, and then we'll look at the word cloud later when we're done with the PPT to see whether I've been making the right mistakes. Give me a heads up once you're all done. All right, folks, time's up. You all can keep entering your answers if you all want to enter it multiple times, but yeah, we'll have a look at it later. All right, so why WebRTC from an outsider's view? I've already given you quite a brief. It is for outsiders, right? You want people to use your tech, especially developers, to leverage the products that you're building upon it. It's nice for them to know what they're using. And, well, the mistakes I'm making, and it is hilarious how difficult it is to get started with something so beautiful. This tech is so great. I mean, I'm at a point where I love reading about it and, using it. But, oh, man, it was difficult. So 40 minutes, I started working at Diet a couple of months ago. And 40 minutes into trying to learn about WebRTC, these were the words I knew. Did I know what was WebRTC? No. But I knew these words. And 40 minutes later, I was brainstorming a startup idea, which I decided was too competitive. So I dropped it. But WebRTC, when you go to read about it, is basically a bunch of acronyms. Does anyone over here remember the Mozilla definition of WebRTC? Or when was the last time you read the Mozilla definition of WebRTC? It's just a bunch and bunch of, technical jargon and, acronyms. This is what, I wish somebody would have told me this. This is what WebRTC is, right? Yes? Well, I see people like, no, not really. No. But if someone would just tell me this, and this is something that, again, like Dan mentioned, and I completely agree with him, documentation does not have to be, it can start off easy. And that's what we're trying to do at DITE also, basically start off easy documentation. But basically, this is how simple WebRTC is, right? It's a good analogy to start with. Two people trying to communicate directly, and okay, this is WebRTC without the jargon. Let's look into how it works without the jargon, right? When I'm starting off with a new tech, I do not need to know the tech behind it. I can start with something of an analogy, and I can break it down pretty easily, right? So let's continue our park analogy, right? So we started off with what's WebRTC in a park analogy. We said that, okay, two people trying to communicate over a walkie-talkie. How does it work? Well, WebRTC, if we were trying to find each other, we would say something of a signal, right? That, hey, we're in the same park. Then we would want to speak the same language. That is basically ensuring that, we're using the same protocols. And ensure privacy. I did not need to know what NAT and STUN was the first time I was reading the documentation, right? So this is the Mozilla documentation definition. I use the Bionic Reader, which is why the picture's weird, but this is the definition. So I went ahead and I researched better documentation, right? Because I eventually want to create documentation for myself. So this is a documentation. This is a small definition that I found, which is so much better, right? This is just a tad bit simpler, but it makes my life so much easier. Do you all know where this definition is? It's actually on Touch Designer. Touch Designer is actually a designing tool, a node-based designing tool, which a lot of visual artists use. So if you all ever go to a concert and you all see a lot of lighting happening on the stage, I think. There we go. All right, so challenges, so that's the Touch Designer definition. It's a simple software that is basically leveraging WebRTC. And they actually bothered to break it down to the point where, okay, I do not need anyone who's reading about the definition to be a video engineer, right? It can be someone who just wants to leverage the tech, right? So this is a simpler definition. So let's talk about challenges in starting with WebRTC, right? I want stories. I know you all are mostly experienced engineers, but what was your first experience, like the first time you all, read the first WebRTC documentation? Anyone? Any story regarding how they started? Yes.
I never used it.
You never used it. Awesome. Anyone else? No stories, Rishit?
Yeah, it was hard. So I came across the Lobster Pinox. So not Pinox, but there's a WebRTC for the curious. So that was a nice resource. But yeah, before I found that, it was hard. Like it was the same experience of sort of seeing all these short forms like stun and ice, as you mentioned. But yeah, once I came across that, it became a bit easier. Yeah.
Awesome. So, basically, the point I'm trying to... You have a story as well?
Yeah, I have a story. We started to... There was the rise and interest of clients in WebRTC, and we decided we wanted to follow on those leads, and I had to deep dive into the Big Bang Bunny project and learn everything from the scratch, and try to debug the problems that the clients had. So that's kind of a nightmare, 2 months of debugging and watching Big Bang Bunny.
I'm glad that story is such a great segue into this talk. But yeah, so I think another really good takeaway, if especially you all are here, with products that leverage WebRTC, is how good documentation can be an, natural marketing agent for your product. Anyone else? Especially some of this experienced people. None of you all had any trouble starting with WebRTC? There you go.
Went the other way around. npm install peer.js. Done.
Great. So basically, that's the story that I'm trying to tell, right? We want people to use Dite in some form, but we can't really explain easily why Dite, right? For that, we need to be able to explain WebRTC. So this is one of the ways I finally got started, and this is again from Touch Designer. So like I said, right, Touch Designer is a node-based application, and they have a simple node that helps you configure WebRTC. You open this node's definition, and that's it. You configure it once, and you have a really good idea about what WebRTC is doing. You're setting a stun server, you research what's stun, you put a username, you put a URL, and you know somewhat what's happening, right? So when you define something this easily and you let people configure, is a really good example of a documentation. I see so many code sandboxes on so many products leveraging WebRTC, and none of them have actually boiled it down to something this simple, right? I'm either exposing a million APIs or sending auth tokens across, but not a single one has kept it this simple, right? All right, first steps into WebRTC. Now, this is more geared towards anyone who's, again, trying to evangelize their product, which leverages WebRTC. And this is something, again, that we're trying to do at Dite. We are trying to build, basically, instead of just blogs that, hey, which, by the way, reminds me, Dan really referenced a really nice Dite blog that we've done on similar lines. Basically, don't just talk about the tech, show how you're using it. Again, a simple definition, and it works, right? Another really good example is Dite socket.io. What we've done is basically we've rebuilt socket.io, and we're maintaining it actively. And that basically has also a live code sandbox. We also have a device emulator that's doing the same thing, by the way. So in case you all have ever worked with Videotech, and you all have had, problems with device testing, right? What we've done is basically to help you all leverage WebRTC better and test your devices better. We have an entire, how do you test audio devices, failing or being connected or disconnected, and we've basically done that. Awesome. So another really good way I found finally started learning about WebRTC was through the community. Anyone, any favorite communities for WebRTC? Yeah, I love Videodev on Slack. Yes, they're doing a great job putting resources together. Any other favorite communities for folks who like or have been learning WebRTC, or when they are lost, go to search for resources on WebRTC? I'm sorry? Pioneers. Awesome, yes. Anyone else?
Currently, it's like open space on Software Mentions second floor.
Another really cool resource that I found was community discussion. There's a really cool WebRTC live that happens on YouTube every other week, I believe. And they have some really cool resources. And so, yeah, we want to do the same thing. And we're actually having a discussion party on WebRTC and basically OSS projects and video engineering on Tuesday. So if you all want to join us, we're having that at 7 p.m. On Tuesday. And yeah, that's pretty much it for me, folks. I promised to keep it short and simple. And yeah, if you all have any questions regarding dev evangelism in video tech, I am happy to answer.
Thank you. Are there any questions right now? Anyone? Okay, I don't see any questions, so thank you very much once again. Let's give another round of applause.
Thank you.
All right. right, and now time for the last but not least. Speaking of the WebRTC community at Software Mentions office, I would say that's head of this office, Michał Śledź, who is responsible for the Jellyfish server. And he's going to speak a little bit about bringing a new kid to on the block, like another WebRTC implementation to the slides that you've seen before. So once Michał is ready, we can start.
Okay, thank you, Bartek, for introducing me. Hello, everyone. So let's dive directly into the presentation, which is about rewriting Python in Elixir. I know that you've already heard so many WebRTC talks, but I would like to start with a short reminder about WebRTC protocol stacks. So this diagram presents 10 different protocols that WebRTC consists of. Every single protocol is responsible for something different, right? So for example, ICE is used to establish peer-to-peer connection. RTP is used to transmit data as RTP to encrypt this data, and so on and so on. To fully support WebRTC, we of course have to implement all of those protocols. And the most popular WebRTC implementation is libWebRTC. It's used by web browsers, written in C++, and it's maintained by pretty big companies like Google, for example. But the problem with libWebRTC is that it's pretty hard to play with it. It's hard to install it, it's hard to compile it, it's hard to introduce any changes into it. And all of those problems are solved by Python. So Python is another WebRTC implementation written in Go. It implements everything from scratch. So every single protocol I showed you on the previous slide is provided as a separate package. It's very fast and popular. And the phenomenon of Python, I think, is that they made creating your own web applications, or in general applications based on WebRTC, much easier than this was before. They even come with WebRTC for the Curious book, so their own learning resource. And Elixir WebRTC is our attempt to create a similar project, but for the Elixir community. So we don't want to rewrite everything one-to-one from Go to Elixir. Instead, we want to take inspiration and create a similar ecosystem for the Elixir community. We don't want to follow WebRTC path where they even have the same function names in their implementations. But you might ask a question, why Elixir? Have I ever heard about this programming language? And those questions are very good questions because Elixir is not so popular. Comparing to Go, Rust, or C++ is also pretty slow. Functional and dynamically typed, most of us are used to some kind of object-oriented programming. And there already are WebRTC implementations available on the market, so why create another one? Doesn't make a lot of sense, right? I would like to leave those questions for a while and talk about bigger picture, bigger context, some problems that a lot of people face when they jump into the multimedia. So imagine that you want to create a startup, right? You want to, as in the case of every startup, you want to create a prototype pretty fast to show it to the investors. Or you have a company and you don't want to run your meetings, internal meetings on a Google Chrome, Google Meet, because you cannot host it on your own machines. Or you are a student and you want to learn something about audio and video. In general, you know you want to do something with multimedia. You decide to jump into this world and you immediately feel overwhelmed. Overwhelmed by so many weird terms, codecs, network protocols, and different RFC documents. Overwhelmed by few learning resources, legacy network stuff, or pure user experience. And in general, you have two options. You either try to jump into this world on your own and try to understand what's going on, but this will require a lot of time from you, or you pay some consultancy company to do this multimedia stuff for you. And that's something that we want to change. We want to make multimedia more accessible, easier to jump into. We want to provide you with a good learning tools, good learning resources, so that everyone can play with audio and video on their own. During those 3 years of working on multimedia projects in Software Mentions, specifically in Membrane, we had a lot of clients, everyone with custom needs, different needs. For example, a client comes and says, I want to have a video conferencing system with recordings. Or another client comes and says, I want to have a video conferencing system, but with the ability to broadcast it to a broader audience. Or another client comes and says, I want to fetch audio and video from my web browser and transmit it to the backend and apply some cool ML stuff on it. The only common thing was that people needed to use the same network or multimedia protocols, but for different purposes, for in different configurations, and with custom enhancements. So we created something called Media Engine, officially known as Membrane RTC Engine, and that's a library that allows you to combine different multimedia protocols. So once again, imagine that we want to create a video conferencing system, right? So we take the engine, we take two WebRTC endpoints, plug them into the engine. Those WebRTC endpoints will communicate with web browsers, exchange their media between each other, and that's it. We have very simple video conferencing system. Now let's assume that we want to add recordings. No problem, we just add the recorder endpoint. Maybe we want to broadcast this to a broader audience, no problem, just replace the recorder with HLS endpoint. Or even better, have both at the same time. Maybe you don't want to use WebRTC at all, no problem, replace WebRTC endpoints with RTSP endpoints. And so on and so on. There are, for example, ML endpoints, or you can create your own custom endpoint by implementing very simple interface. And everything is provided as a library. So speaking of requirements, based on our client needs that we observed during those 3 years, almost everyone searches for a customizable solution, written in a high-level programming language, so that developers can almost immediately jump into and start prototyping. A solution with built-in fundamental protocol support, intuitive API, good package manager and documentation tool, and pretty wide ecosystem. And it turns out that Elixir is a perfect choice because it's very high-level programming language with an easy-to-understand concurrency model based on message passing and data immutability. So there are no shared states, there are no mutexes. We have Phoenix for web applications, Livebook and Elixir NX for machine learning, and also Mix and XDoc tools. So to sum up, we have 3 abstraction layers. If you want to prototype, just take the engine as building blocks, including our WebRTC implementation, and do your stuff. If you want to deploy, just take Jellyfish, which is based on our RTC engine, and deploy. If you don't want to deploy or prototype, and you just want to have everything, you want to be provided with everything, just take our cloud. So Elixir WebRTC is just a small puzzle of this bigger context, bigger picture. I would even call this some kind of a vision. And we started our work on it about 3 months ago. There are currently 2 people working on this project. And going back to the diagram I showed at the beginning, we were able to implement Stantern and ICE. We also implemented RTP and RTCP parsers and serializers. Now we move to the peer connection, where we are working on DTLS handshake. So that's the current status of the project, and I would like to go through our libraries, namely Stantern and ICE, and talk a little bit about challenges we've met and how we solved them. So let's start with rel, which is a shortcut from relay, and it's our own pure Elixir Tern server. What is a Tern server? Just a short introduction. So the idea of a Tern server is pretty simple. We just want to forward traffic from the one side to the other side. When you start a Tern server, it comes with a listener socket, a client, and a peer. A client creates an allocation, which is another socket, and whatever peer sends to this allocation socket, this data will be forwarded to the client via listener socket. One client can have one allocation, and it can communicate via this allocation with multiple peers. And we can, of course, have multiple clients, but the very important thing is that every single client has to communicate via the same listener socket. So listener socket here is a potential bottleneck. And I said that Elixir is not, at least comparing to Go, Rust, or C++, the fastest language. So we did a couple of benchmarks. We picked 3 different Tern server implementations and checked which is, let's say, the most performant one. So benchmarking scenario is pretty simple. We'll have a client and a peer. Client creates an allocation. Peer starts sending data through this allocation to the client, and then client echo back this data to the peer. The questions are how many such connections we are able to handle, how big bit rates we are able to handle, and what is the impact of datagram payload size on our Tern server performance. Testbed, we have 2 pretty big machines, Big Fish and Big Cow. Both are 32 cores, 64 threads, and they are connected with 10 gigabits per second connection link. A big cow handles our turn server, a big fish handles our clients and peers. And the results. So we picked, of course, our own RHEL turn server written in Elixir, Coturn, the most popular one, currently available on the market, which is written in C, and a Turner written in Erlang. We started with a phone call-like scenario, so we sent 50 kilobits of data per second in one direction. We have 2,000 connections. Datagram payload size is 150 bytes, and the overall bitrate is about 400 megabits per second. The overall bitrate is a sum of total incoming and total outgoing bitrate on our turn server machine. And RHEL takes 25% of CPU usage, Coturn 10%, and Turner, written in Erlang, well, we were not able to set up more than 1,000 connections. I think that that's some kind of configuration problem, but that we were not able to easily fix. But I put it here because it crashes in the last scenario, and I would like to talk about this more. So I would say that the results are pretty good, pretty decent. I'm really satisfied with them. We are just 2.5 times slower than Coturn, which is written in C. But we also ask a question: what happens if we keep the bitrate but increase datagram payload size? So the second scenario is almost identical, but datagram payload size is 1,200. And the results are much different. The difference is massive. RHEL takes mostly between 2 and 4% of CPU usage. Coturn a little bit over 1%, and the Turner out of the category. As you can see, if we keep the bitrate but we decrease the number of datagrams that are sent through the network, we of course save a lot of resources. And the last scenario is a video call like scenario. So we have 1,000 connections. We send 1,500 kilobits per second of data in one direction. So this should be enough to handle HD resolution, and the overall bitrate is over 5 gigabits per second. And in this case, RHEL takes about 45% of CPU usage, and Coturn 15%, so we are about 3 times slower. A Turner crashes, but by crash I don't mean CPU usage. I mean that they are not able to read incoming traffic fast enough so that we notice a packet loss. And speaking of this, that's the initial architecture we started with in RHEL. So we have one listener process that was responsible for reading all incoming traffic and splitting this traffic across allocation processes. The problem is that this architecture doesn't scale well. So we were able to set up about 700 connections using this setup, and then our listener process was not able to read incoming data fast enough. So at this stage, we knew that we need to add more listener processes. Defined architecture is as follows. We use reuse port option for UDP socket. Thanks to this, we can open multiple sockets bound to the same IP address and port. And operating system under the hood performs splits incoming traffic across all of those sockets equally, or at least it tries to do this equally. So we get load balancing out of the box. And with this architecture, we are able to handle at least 3,000 or 4,000 connections over 5 gigabits per second. And we start as many listeners as we have threads in our operating system. So that's also the same what Coturn does. They spawn also as many listener processes, listener sockets as you have threads. And that's also why a Turner crashes, because they spawn only one listener, so they are not able to handle pretty big bit rates. RHEL is publicly available. I said that we want to make multimedia world more accessible, so we created one instance of RHEL and made it available for testing and experiment purposes. So everything you need to do is to execute a very simple post request to obtain your password, username, and just copy paste this data into RTC peer connection constructor, and this should work. So that's everything about our turn server. And the next library we implemented was XICE, which is our pure Elixir ICE implementation. Here I would like to list features that we support right now. So we are compatible both with aggressive and regular nomination. We support role conflict resolution. We support almost all types of candidates, transaction pacing, and keep alive on valid and selected pairs. I know that there are a lot of buzzwords, but for those who are familiar with ICE, now you know what you can expect from our implementation at this stage of the project. And the last library is STAN, so what is STAN protocol? STAN, you can think about STAN as a tool that is used both by a Tern server and ICE. It is, for example, used to obtain your public IP address. So let's imagine we have a client which is in a private network behind some NAT device, and we want to obtain our public IP address. We have two types of messages: binding request, binding response. Client just sends a binding request to the server. Thanks to this, it creates a mapping from private to public IP address, and then server sends a response that contains this public IP address, and that's pretty much it. Those messages, binding request, binding response, are most frequently used in the initial state of ICE when we try to establish a connection. So because of that, we did a couple of benchmarks to see how much time we need to encode and decode those messages. We once again picked 3 different implementations. So we picked our own Elixir WebRTC IORTC, which is written in Python, and Pion written in Go. Pion was, of course, the fastest implementation in every single category. We started with binding request encode, so how much time we need to encode binding requests. In this case, Elixir WebRTC is faster than IORTC. We just need about 1,700 nanoseconds. IORTC about 2,400 nanoseconds. So that's pretty, I think, significant difference. The next benchmark is binding request decode. I don't know what IORTC does in this time, but they need over 2,000 nanoseconds to decode binding requests. Elixir WebRTC takes about 150 nanoseconds, and Pion just 9. And binding response encode. And once again, I don't know why IORTC is so slow. I don't think we have a bug in our benchmarks. This code is also publicly available, so everyone can check it out. But the code is very simple. Here, Elixir WebRTC and Pion are the results are pretty similar. The last benchmark was related to new transaction ID. So when you send a binding request, you need to generate transaction ID. When you send the response, you just take the ID from the request. Here, Elixir WebRTC was the slowest implementation. But to sum up, in most cases, in most categories, we outperform Pion. I mean IORTC. So Python implementation. And as long as we outperform Python implementation, I'm satisfied with the results, and I think there is some sense in continuing this project. Yep, and we hope to be able to provide first version of peer connection in January 2024. And I also spoke about Membrane RTC engine. That is a library that allows you to combine different types of multimedia protocols. It's already available. We use it in Jellyfish, but I also think that the current API is not so intuitive. The documentation maybe is not the best. So I hope that we will rewrite it and provide a new API somehow around June 2024. Well, that's it. That's everything from me. If there are any questions, I will be happy to answer them.
All right, and the questions, are there any here? Oh, okay. Maybe I'll start here.
So, great talk.
Thank you.
I have a question about the RTP and SRTP. How is the progress with that? And are there any challenges in implementing those protocols?
So right now we were able to implement RTP parsers and serializers. We are not sure how the abstraction of data flow should look like. So we will probably start with a peer connection. we'll try to make data flowing, and then we'll try to extract something like Pion provides. They provide session bean, maybe not session bean, but RTP session or something like this. So that's how our RTP implementation looks like right now. Regarding SRTP, we'll take the implementation from already existing implementation from membrane framework, and cryptography and anything related to cryptography will stay in C. So we are not going to rewrite cryptography stuff in pure Elixir. We of course take already existing implementations and wrap them for usage in Elixir.
Thanks. Yeah, great talk. Thanks a lot. Very deep, but still very clear. Noob question, you said you're going to re-implement all the 10 transport protocols. Are you even going to rewrite UDP? That's insane.
Thanks for the question. So here I marked UDP with the gray color, because or maybe it's not visible on the presentation, but it's marked with the gray color because we are not going to rewrite it.
All right, any other questions? Okay, thank you very much.
Thank you.
And now, before I let you all go, I have a question. Who's going to join us tomorrow at our office? Please raise your hand. Okay, that's a decent number. So to those who are still hesitating, we are inviting you to join us at our office at Zabłocie 43B. Sorry about that. You should have all the details in your emails. The thing will start at 9 a.m. You can join us a bit earlier to grab a coffee, grab something to eat. There are going to be 2 sessions with the workshops, and then some spare time for hacking, maybe diving a bit deeper on the things that you may learn during the workshops. And then later, at the same spot, at our office, the after party at 8 p.m. We invite you all to join us. And thank you very much for attending our first edition of RTC.On. It's been a pleasure. Hope you enjoyed it, and see you, I hope, next year. Thank you.